live in three, two. All right. I think
Anything?
we're good to go. Yeah.
Are we good to
It's our
go?
first live podcast.
All right. I'm excited. Welcome. Good morning, everybody. This is the very first Infer Summit here. And welcome everyone joining us. Please share. We'd love to hear where people are joining from. So please share what city that you're joining from. And while we're doing that, I just want to introduce my partner in crime, Kawaja, CEO of Momento. And Kawaja, what are you excited about today? This our first Infer Summit.
Well, we've organized conferences together beforehand. When you first came up with the idea of hosting a virtual summit for Infer, I kind of thought you were just gonna organize a small summit with a couple of speakers uh, and get a few people to attend. But somehow, within a month, you got 600 people signed up.
Wow,
And
yeah.
you got some incredible speakers from Pinterest, NVIDIA, Base 10, Fireworks, all of these great speakers. How did you pull that off? That's what I'm excited about.
That's a secret. I can't tell you, but it requires a lot of work from not just me, but everybody. I see people joining from across the globe here, from Mexico, from India, Bay Area,
Nice.
and whatnot. So very excited for folks to join there. They might be late at night for them, but thank you for joining us. We are honored to spend the day with you today. So how do we go to the next slide here? Okay. So first, before we get going, I want to thank you, the speakers. Right, without them, this would not be happen. They say yes to us
Yeah.
when it's just an idea on the document. So thank you for all the speakers. And of course, the other part is all the attendees, all the people that signed up. And if they're not able to join today, that we're going to able to publish all the videos and recordings later as well. So
This is
thank
also
you
the
for that.
first event where all the speakers have been able to get their slides to us on time, and you've been able to review
Yeah.
them, rehearse them. A lot of
Kudos to them.
passion put into the day that's being put together.
Yeah, and last but not least is the Momento team behind all this. That's a lot of work behind the scene, putting all this together, believe it or not. So, and we did this in a very short amount of
I think
time.
that's about a month.
Little less than that.
Really? Alan and Hannah and Mike behind the scenes did a lot of work to get things set up. We have Evan in the studio making sure that all the live streaming is set up, and we're doing it remotely. Like I think you and I got to sit together today, but there's a lot of coordination happening behind the scenes to keep the content alive.
Yeah. And the fact that this is a weekday, Thursday, and we are talking about a very interesting topic about inference. And that itself is telling you something about the moment that we are in right now, right? And here's a slide that is, I think this is a pretty key point that Jensen Huang made at the GTC 2026 about a few months back, at the beginning of the year. He basically is saying that, and I think most people would agree, that we at a point in time where we used to focus on model training, but now it's all about real-world deployment and all these agentic applications that's being deployed and executed at scale. So this is one of the reasons why we, come up with this idea for this summit, is to have a focused discussions on this.
I mean, inference is becoming commoditized, right? Like we're seeing it in more and more pieces of the workflows, and the training has gotten us enough where we can do real things.
Yes.
So it's a pretty exciting time to be where we're at and deal with all the scale challenges, because it's very appealing to keep building more and more applications, but it takes a lot of work to run the infrastructure behind the scenes for it.
Talking about scale, this is where if you launch your application, agentic application and whatnot, the cost is a lot. It's top of mind for a lot of folks now.
Yep.
And obviously, when you have these applications user-facing, the latency is going to be a big deal, right? So there's a lot of engineering that's going on behind the scene to build the inference stack. So as an engineer, to me, this is a very exciting part. And this is also the hard and the fun part And it's happening right now. So that's why we're talking about it. Cool. So I think most of you know, all right, over the last 18 months, a lot of things have changed as we learn and practice, and a lot of things are changing in the AI space, from context window getting bigger and bigger. And when that happens, the KV cache now has become the new bottleneck. And you have been involved in that in terms of building and learning everything. So, and if you're building agents, you know that your agent is going to be doing multi-turns, and there's a lot of inference going on at every single turn, right? And the build at the end of the month is like I mentioned, is a top of mind for a lot of engineering leaders.
Well, it's two things, right? One, inference when you're building demos is very cheap. When you deploy it, it becomes you have to pay the bills. And the more complicated your inference stack gets, or your agents get, the more state has to be transferred. So it also starts to become a bottleneck. So cost and velocity start to come into play, and lots of interesting innovation to be done on every step of the stack.
Yeah. So when we put together this Infer summit, we're trying to think about like what are the different areas that we want to have talks about, right? So we came up with these 3 pillars, the engines, and there's a lot of exciting innovation in this space, right? From VLMs, SGLang, NVIDIA Dynamo, and so on. So it's coming back to more like system engineering, right? At scale, all these things, from scheduler to router and everything else in between. So it's very exciting from an engineering perspective. And if you are companies that are using these engines to serve these large language models, you have to deal with all the reliability, observability, making sure you don't get to wake up at 3 a.m., right? Running in productions. So a lot of challenges there. And the last pillar is our other area where you have all these inference providers that are building their inference stack and make it easy for other people to consume to do inference. So now we have choices of hosting the model in-house or leveraging these providers. So that's where the architecture part comes in. All right. And so we are very happy to have speakers from all these companies that you see up here. The people that are actually doing it, building engines, the companies that are actually using these engines at scale. And then there's inference provider that building the stack. So I'm very excited to able to get this diverse group of people together today. And I cannot believe that we got this group today.
Yeah, I can't believe you got all these people today.
I'm not sure how it happened, but very, very happy that we have such a diverse group of speakers today. So let's talk about how can attendees get the most out of today. It's already on the web page, but we have 10 sessions today. Each one is about 30 minutes long. It's going to be back to back. It's going to be packed. And we're going to leave about 5 to 10 minutes at the end for each session for Q&A. So during the presentation, feel free to drop questions during the talk, and then we'll pick that up at the end and serve this up to ask the speaker. Then we'll take a lunch break, about 12:15, a short lunch, 45 minutes. And by the way, so there's going to be some free credits, API credits.
Oh, yeah.
And thank you to the Double Word.
That's right.
And Fireworks. So if I were you, attendees, pay attention, because there's going to be cookies along the way, right? To get these
Everybody
API
wants free
credits.
inference these days.
Yeah. So that's...
If I could add like a couple of quick things, just when I was earlier in my career, I always used to find speakers at a talk to be pretty intimidating, right? Like it was hard for me to ask questions. And I just want to call out that pretty much every speaker that is speaking today They are very, very approachable. And even if you don't get a chance to ask your question today, I would encourage you to just find them on social media,
Yes.
connect with them, and send them your questions. It doesn't hurt to just send them a note. So I'm signing them up for a little bit of spam here potentially. So please don't send them spam. If you have genuine questions, connect with them, ask them their thoughts, and they're all very, very helpful people. So take advantage of that. We're hoping that the learnings from this Infer Summit don't end today. We're just trying to create a pipeline where you can network, meet other people, meet some experts, and continue to follow up with them over the next few months and years.
Yeah, totally. Connect with them, ask them questions on social network. I'm sure a lot of you speakers will also speak at various conferences as well. So what you see today and hear from them today is just not the only way. So do take advantage of that. And again, don't be shy to pose questions as the presenter is presenting their part. And then we'll make sure to get to those. All right, wow, I see someone from Netherlands.
Oh, wow, nice.
That's, I'm not sure what time it is over there, but probably not in the morning.
Well, we have speakers from Europe too.
Well, we get one from Abu Dhabi.
Yeah.
Wow. One from Kenya.
We're covering all the continents. We need somebody from Australia.
Pretty much. Europe, North America, Africa. So I hope speakers are aware of this, that we have a very diverse sets of attendees here. So, so let's see. We have, first we're going to have Miriam from DoubleWord. And she's going to talk about now that you have agents. So how do you do inference with async agents in production? How do you make sure that you manage the costs? Because async agent, they could go wild, they could go rogue, right? So she will share a lot of techniques and strategy, how to do that efficiently, how to manage the costs, and all other challenges there. So with that, I'm going to hand it over to Miriam. I know Miriam for a long time. She's a great speaker that I'm sure you see. And she has a lot of experience in this space. Her company has been around in this space as well. So with that, Miriam, welcome.
Hello.
Is it like dinner time in London, I believe?
6 p.m., but I'm kind of permanently on East Coast time, so it's fun.
Okay. All right, good.
But I was just thinking, as you were saying that we've known each other a long time, I remember when you took a bet on me before I'd done much public speaking at all. And I was like, I think this problem of inference will be really, really big. And about 3 years ago. And now we have whole conferences dedicated to inference. And that's
wow, 3 years ago. That's cool.
All
right, with that, Miriam, all yours.
Fantastic. Well, hello, I'm Miriam. I'm going to aim to speak for about 20 minutes to leave plenty of time for questions. If you have questions, feel free to pop them in the chat. If they're relevant, I'll bring them up kind of as I go, and otherwise we can discuss them at the end. And today I'm going to be talking about async agents and inference for async agents. Before I do that, I'll introduce myself. My name is Miriam. By background, I'm a physicist. Actually, all of my co-founding team are physicists. We've been working in inference optimization for about 3 or 4 years, far before people thought it was cool. But we kind of bet at the time that if this AI thing would be really big, the problem that would really matter was inference. We're an inference provider focused on very high throughput inference use cases. So things like not just async agents, but like data labeling, evals, data generation, embeddings, anything where kind of volume matters is the type of inference that we do. And there's a QR code to my LinkedIn. And so feel free to connect with me and send me questions there afterwards if it's interesting. So every single talk that I do feels like it starts with this chart. And this chart is essentially a representation of how good models are getting how quickly. So models are able to increasingly do much, much longer and longer running tasks. This is an evaluation suite run by Meta, and they track over time for all of the different models that come out, the types of tasks that they're able to complete. And it used to be that for GPT-3, it could do things that might take a human, 10 seconds. Then now we're in with Mythos, we have models that are able to do tasks that otherwise would take a human 20 hours or 16 hours. And as models are getting better and better, they're able to do tasks that run for long periods of time really well. In fact, they're getting so good that the length of tasks that they're able to do doubles roughly every 4 months. So it's an incredible rate of improvement. Most of the models here you can see are closed source models, but with open models, we're about 3 months behind. So open models are also now able to do tasks that would take a human, 8 to 10 hours. And every generation of AI system, as they're getting more performant, they're also getting much more token intensive. So we started off in early days of inference or early days of generative AI, kind of after the explosion of ChatGPT. It was a very simple inference profile. With ChatGPT, I sent a question and I immediately got a response. There was kind of no interesting inference time thinking happening. Then with O1, the rise of reasoning models, I sent a question and then my model would reason for a little bit of time, maybe do some deep research, maybe do some RAG, and then it would respond to me. And this uses more tokens than this, and it's also more async than this, right? As a human, I've now got to wait, maybe a couple seconds, and it's using way more tokens behind the scenes. The next generation from O1 to Claude Code is way more async than the previous generation and uses way more tokens. So Claude Code, I ask it to do essentially a whole piece of work. It can go off for comfortably 10, 20, 30 minutes, an hour, 2 hours at a time, and work to complete that task in the background. So it's working in the background and it's also the whole time generating a whole bunch of tokens. So it's a very, very intensive process. And so this kind of screenshot from Jensen's keynote at GTC is an illustration of how every generation of AI systems are getting more async and more token intensive. And that's why token spend is skyrocketing. So this is a graph from A16Z. The amount that is being spent on tokens is astronomical, and it's growing rapidly despite actual token cost for a given model falling. So you have a real Jevons paradox thing going on here. So what are async agents? So I will define async agents as work that doesn't block a human waiting on the other end. You can think of it in... Okay, my slides are broken. But you can think of it in contrast to like sync systems, like chat systems. So these chat systems, I ask a question, I get a response immediately. As the human, I'm interacting directly with that. But with a async system, I ask a question, it goes off and does something in the background, and I, as the human, can go do something else. You might have had this experience if you're using kind of Claude Code, and you go maybe start another task while it's completing that task. So what kind of inference stack do async agents need? Okay, hold on. It seems like my transitions are broken. So give me 30 seconds while I fix that. Okay, this is not working. Let me share this instead. Otherwise, we were going to have a very blank presentation if none of my transitions worked. There we go. Okay. So, there we go. So we talked about the difference between sync systems and async systems. So I mentioned that sync systems are kind of like, I'm asking you to do a thing, it does the thing. I then ask you to do the next thing, it does the thing. Async agents, I kick it off. It maybe fans out in parallel. We're big believers in parallel agentic systems, and it kind of works in the background. And these are way more token intensive. So what kind of inference stack do these async agents need? Which is going to be what the topic of the rest of my talk is about. So the difference in inference systems between sync and async are pretty stark. The first one is that you have to think about what the waiting pattern is. I wrote a blog on this a couple months ago. So with your sync and chat agents, you have your surface area of who waits is the human. It's very, very real time. If I'm waiting even a second or 2 seconds, I get out of the flow. With an async agent, no one's waiting for my answer. So I ask it to do a task. I don't care if my task comes back in 35 minutes or 45 minutes because I'm doing something else. And so that like who waits question is pretty significant. And therefore the thing you get your inference stack to optimize for is very different as well. So in my sync system, I'm optimizing for time to first token because the interactivity with the human really, really matters. With async agents, the thing I'm optimizing for is actually more my dollar per task and my throughput. So it's essentially how, what kind of volume can I run this at? And the unit economics start mattering as well with async agents because the volume of tokens I'm delivering is really high. Another thing to mention is they also have very different call patterns. So my call pattern for my sync agent is very sequential and it's very predictable as well. I ask a question, I get a response. Maybe it does a tool call or something like that, but it's actually fairly stable and predictable. My call pattern with my async agent is very unpredictable. A pattern that we're seeing more and more that we're very excited by is very parallel agents. So you have an agent that then spawns a bunch of sub-agents. Maybe they're doing a bunch of trial and error. Maybe they're all doing different parts of the task, but I have them burst off. And so I have kind of a very explosive call pattern. And then also the tools that they call and the reasoning loops that they do are very random and chaotic. And so it's actually quite difficult to predict and build for that kind of inference. So anyone who's been in inference for a while will know that inference is always a game of trade-offs. Specifically, it's a trade-off between latency, quality, and throughput. They're the three things that I think are relevant. And in this case, the thing you want to optimize for your async agents is very clearly your quality and your throughput. And I'll walk through the other combinations to convince you why that's the case. So the reason why you don't necessarily want to optimize for quality and latency is because your inter-token responsiveness doesn't actually matter that much if it's generating in the background. So for me, the difference between something finishing in 19 minutes and 20 minutes is not a big deal. But in order to get that latency, I also have to pay a lot of money. It's a very expensive thing to do. And so I probably am going to reserve my high quality, low latency inference for my premium chat. I could choose to have low latency and high throughput. This is also possible, but this tends to mean that you're sacrificing quality. So maybe in this instance, I'm using a smaller model or a quantized model, but that typically isn't good enough quality for a very long-running agent, because with long-running agents, you need the highest level of intelligence possible so they can maintain coherence. So the thing that I'm going to want to optimize for is quality and throughput. So what we say the things to optimize for are throughput. So we want like to minimize the wall clock time when we have like highly parallel agents. We care a lot about cost because the cost per task is very important as these agents are incredibly token hungry. And we also really, really care about the volume that we can deploy these things at. Just this is my very brief plug. The reason I'm talking about this is at DoubleWord, this is our bet. We have kind of throughput maxed our inference stack, optimizing for inference for these things. So how do you optimize for throughput above latency? Well, an inference stack is built of a lot of different layers. And so often I get asked the question, what's your secret sauce, or what's kind of the secret trick that you guys do at DoubleWord? And the answer is really that there isn't one secret trick. It's actually just like dozens and dozens of like engineering challenges that we've had to solve at every single layer pulled together. And that happens at hardware choice. It happens writing different kernels. It happens at the model level, the inference engine level, scheduling and orchestration, and API design. So there's no one trick to kind of building the optimal inference stack for these types of systems. It's actually just about optimizing the stack as a whole. And at every single layer of the stack, you can decide to kind of interactivity max or throughput max. So my interactivity max is the same as achieving low latency for anyone who has confusion. I've also linked to our technical blog. We write up some of the things that I'm going to talk about if you're interested in those kinds of things, so feel free to check that out as well. So at the hardware level, what are the things that we can do to throughput max? Well, A lot of it comes down to the chip choices that you make. Specialist chips like Cerebrus and Grok achieve world-beating interactivity. You can't really achieve better interactivity than on something like a Cerebrus chip. However, the cost per token on those chips are really, really high because you can't run them in parallel in the same way. And so actually opting for something like, we really are big fans of AMD or NVIDIA chips. You could even use multi-generation chips that might have better unit economics right now. You can often get much better performance per dollar. And so if you're throughput maxing or for async inference, then you might decide to optimize for performance per dollar instead of just raw performance. And often that looks like a heterogeneous or mixed cluster of AMD and multi-generation NVIDIA chips. At the kernel level, the big difference is whether you're writing and optimizing kernels to think about improving bandwidth or compute optimized kernels. At the model level, we try to not do anything at the model level to change model performance. And the reason why is we don't want our customers to be like, oh, this model worked on a different provider but doesn't work on ours. So assuming we have the same model and same performance between your interactivity maxing and your throughput maxing, but there are obviously things you can do if you're willing to degrade model quality. And there's also other things you can do like spective decoding, but these actually apply both to interactivity maxing and throughput maxing. At the inference engine level, the biggest change that you can make, and there's a lot of small optimizations that you can make, but the biggest optimization that you can make is the batch size that you're going to run at. If I'm interactivity maxing, I'm probably running at a super low batch size. So if you actually ever see providers shout about, oh, wow, I achieved like best tokens per second on the artificial analysis benchmark, blah, 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 the chances are is they're like running at like batch size 1 or something really crazy, which means their price is going to be insane. If you're throughput maxing, you can run at a really high batch size, which is actually really well suited to highly parallel agents or for supporting a lot of users. And the scheduling and orchestration layer, there's actually a lot of really interesting things you can do that I'll talk about in a second in more depth. In interactivity max scenarios for like chat and sync applications, typically I have to over provision my cluster to ensure that if I get kind of spiky requests, I'm always able to serve them with very competitive latencies. In my throughput max scenario, because I'm happy or okay for something to queue for 30 seconds or a minute because it doesn't have to be super interactive, there's lots of cool things that I can do. So for example, firstly, I can just make sure I don't over provision my hardware, but I can also do things like SLA aware routing. So if I have something that I know needs to come immediately because I've got a customer waiting, I can route that ahead of a different one. I can utilize things like spot instances to make use of excess compute. I can reorder things in a queue. So some research we did recently was about seeing if you could reorder things in a queue such that they would use the same experts in a mixture of expert model. So we didn't have to reload the experts on and off, which is quite cool. And so there's lots of things that you can do at the scheduling and orchestration layer to make your cost per dollar much, much lower. And then finally, in the API design, an obvious thing is I might be streaming native or chat completions native for sync inference. I might be looking at more async responses for my throughput max one. In fact, for our throughput max one, we do actually support chat completions as well. But actually, we find the better experiences with more async responses. And I'll go through to explain a bit more 2 of these optimizations here. So I'll go through next the optimizations that you can do at the inference engine level and then at the scheduling and orchestration level, just to give you a sense of the order of magnitude differences that you can achieve. Okay. So I'm actually going to share my screen and hope this works. Yes, it does work. Fantastic. So what I'm showing here is Inference X by semi-analysis. Inference, I'm sure other people will talk about it today, but it's run by SemiAnalysis, and they benchmark all of the different hardware at different interactivities, so you can get a sense of what hardware is performing really well. And what I'm going to show you is, I'm going to clear all of these. Actually, no, I'll leave them. So what we have here is the token throughput on the y-axis and the interactivity on the x-axis. And as I mentioned earlier, there's kind of a direct trade-off between the two. What I can see here is as my interactivity goes up, then my token throughput goes down. And essentially the reason why is because I'm having to run it at a really low batch size when I want my interactivity to be really high. So here we can see the winner for interactivity, but the lowest on throughput is this point here. And you might be able to see that this has a concurrency of only 4. This one here has a concurrency of only 1. This here has a concurrency of 5. This has a concurrency of 2. So essentially here, I'm not able to serve that many users at all. So I might be able to only serve a handful of users. And that means kind of per user that I'm serving, my tokens are really, 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 really expensive. If I, in fact, go on the other end of the spectrum, so this is me being here is me interactivity maxing, which is what I might do for a chatbot. And I'm going to get, I'm not going to be able to serve many users, but I'll serve them really, really quickly. I can, instead of doing that, I can throughput max. And so let's say my throughput max is over here. Here, my concurrency is, let's say, 2,000. And so I'm able to serve way more users, or I'm able to have way more kind of parallel agents running there. And what that means is my per token cost goes down significantly. So let me show you what that looks like. So if I instead change this to cost per million tokens, here we have interactivity. So here we are in throughput maxing, and here we are interactivity maxing. At the interactivity maxing end, so I'm running 1 user concurrently, my price per million tokens is $4.65. Really expensive. Down on this end, my concurrency is like 4,000, and my price per million tokens is 9 cents. So this is for the exact same model. The difference between interactivity maxing and throughput maxing in this case is like the difference between 9 cents and $4.50, which is really, really huge. Okay, I'll go back here. And this is basically just a matter of batch size. So this is pretty much just like a batch size argument that if you care a lot about async agents, or you care a lot about low cost inference, or you care about high volume inference, then you need to run at a very high batch size. I'm also going to talk about what we can do at the scheduling and orchestration layer to kind of give you an intuition of the problem with real-time endpoints and what you can do to make them kind of better for async agents. So first, I'll explain how people run inference for sync endpoints or real-time endpoints. And I'll kind of give you some background. So you can get real-time endpoints on loads of providers. So I think, Fireworks is a great example. They offer really great real-time endpoints. They, like most inference providers, and I won't name any ones in particular, most inference providers actually lose money on their real-time serverless endpoints. And the reason they lose money typically on these serverless endpoints is because of this problem that I'm about to explain. So I have a request volume that is pretty lumpy, right? So I, as a provider, don't know when my requests are going to come in, and I don't know how big those requests are going to be. And so I end up with this really, really lumpy situation. But if I'm promising real-time inference, let's say for a chatbot, I really, really, really don't want occasionally my inference to be really fast and occasionally my inference to be really slow. I basically always want to have decently fast inference. And that means I need to essentially over provision the GPUs that I have available in order to meet that demand. And what that means is here in red, you can see I end up with a bunch of idle compute. So this is compute that I'm not getting the request for, but I have to provision to make sure that I can scale up and scale down as needed. And so at high interactivity, when I'm interactivity maxing, I do need excess compute, and that drives up my cost per token. And so either I have a higher cost per token or I'll lose money on that as well. But for async inference, and this is true for batch inference, and it's true for kind of anything where you're not super interactivity sensitive. I should also mention, when I say interactivity sensitive, I'm not necessarily saying that these APIs are like massively slower. They're just like a bit slower. But I have the same kind of lumpy request volume, right? That I showed before. I have lumpy request volume here as well. My GPU allocation, I can actually have at a way lower volume, because I'm not trying to optimize for this peak value here. I'm trying to optimize for kind of some kind of weighted average. And actually, I could maybe even have this be a bit more dynamic, where I can spin up into spot instances and things. And what we can see here is any time where I have requests that I can't serve immediately because of my GPUs, I can just serve them later, right? I can just serve them when I have a bit less requests, few requests. So I can serve that there. Maybe I can serve this here. The way that we do this at DoubleWord is we have both a real-time endpoint, an async endpoint, and a batched endpoint. And so if we get requests here, for example, that are batched requests, I'm fine processing them in 1 hour, and maybe I'll process these requests later when I don't have that demand. And that means I'm not over provisioning those GPUs. And so any spikes in demand are processed in quieter periods. When there is spikes, what I'll do is I'll prioritize my high priority use cases, and I'll do my lower priority use cases later. This means I end up serving my tokens much cheaper. And so, as you can see, we can optimize at pretty much every layer. I've just kind of talked about 2 things you can do, but there's plenty more things you can do across the stack. And I would recommend, if you're interested in this stuff, looking at our blog. And what this turns into is essentially just massive cost savings. So I've taken here the industry average to serve a Kimi model. This is taken from artificial analysis. This is the industry average. There are much more expensive providers than this. The DoubleWord serves this about 25% cheaper because we've throughput maxed using a lot of those optimizations that we talked about before. What this means is artificial analysis has this other representation, which is an intelligence score versus price. Basically, every single model, without changing the quality, we can move to be much cheaper and more attractive, much cheaper for the same intelligence, just by serving it in a way that prioritizes throughput rather than anything else. So the takeaways, and I can see we have a couple questions, and if you have more, drop them in and I'll try and answer them. We think async agents are going to be the main token driver going forward. They use so many more tokens than any other generation of application. We believe that they need an inference stack that is high throughput, high volume, and has a very low token price because they use such a high volume. And what we do is we trade interactivity for throughput maxing, and that right trade-off means that we can get a much cheaper inference price. And what I've done here is you can scan these QR codes. The technical blog is what I mentioned before. You can also scan free tokens. I think we actually are going to be having more free tokens offered, but if you scan this as like a participation award, we'll know that you've kind of come from today, and we'll send you as well a small amount of tokens where you can try building async agents as well. I'll pause if there were any questions, but I think there's already been some, so I'll look at the comments now. So this first question is the throughput about number of tokens per second or number of requests tasks per second? If it's the first case, how to make sure the token throughput optimizes the agent performance? Great question. So let me go back to Let me go back to the chart I was talking about before. Can you see this?
Yes.
Fantastic. So here is my token throughput. The way that's measured is just tokens per second. So that's all of my users added together. That's all of the tokens that I'm able to produce. So that's basically the same as the interactivity that an individual user will experience multiplied by the number of users I'm able to serve. Because we have super high concurrency here, I can serve a lot of users, and that's why my throughput goes up a lot. And then if it's the first one, how do you make sure the token throughput optimizes the agent performance? I'm not sure what you mean by the second question, so feel free to write a follow-up question. I'll try and answer that one. The next question.
It's a question about how do you know whether a use case is real time or not?
Yeah, that's a really good question. So the way we've done it at DoubleWord is we have 3 endpoints. We have a real-time endpoint, a async endpoint, which is essentially just a high throughput endpoint with all these optimizations, and we have a batched endpoint. And so depending on which endpoint they send it to allows us to rank priority. So our real-time endpoints will always kind of serve immediately. Then my async endpoints I'll serve within about 1 minute. And then they run basically real time. And then my batched, all I promise with my batched inference is that I'll get it done in 24 hours. And so that makes the batched inference really useful to fill in those gaps that I mentioned in the GPU availability. And so the way that we know is because of which endpoint they serve it to. Something that I'm interested in, based on your question, and I think is worth exploring, is whether you can have some kind of model router that based on the request you can get, it can kind of infer how real time it is. But at the moment, we don't have that. It's just kind of based on which endpoint it gets sent to.
Cool. The next question is very interesting, Miriam. Would love your take on your advice for folks that are graduating today.
So if you're graduating today with strong AI skills but limited experience, so I think I think inference is a great place to be. And the reason I think it's a great place to be is in this world where AI takes all of the jobs, we'll still need to figure out how to run these AIs, maybe. And so maybe the only jobs left will be, people serving AI models, potentially. I don't know. But I think as an AI industry, we are really understaffed when it comes to people with good inference optimization skills. It's very, very difficult to find them. We find it difficult to find great people with inference optimization skills. And so we have to train a lot ourselves. So I think that's a great place to be. But honestly, I think more generally, I think the way to figure out what skills you should be building in AI is just to build lots with AI. Because any advice that I give you will probably be outdated in a couple months. So build lots with AI, and then you'll figure out what it's getting good at, and then you can lean into that in the right way. So build lots would be my recommendation, or inference optimization.
Yeah, great advice. And I heard something along the line of that, which is you can't vibe code your way into high reliability or high throughput.
Yeah.
Right. So very true. A lot of system engineering, a lot of hardcore distributed system engineering. So definitely a place to build your skills and knowledge on.
It's also another aspect on this is like Fable, when it came out, was not good at inference optimization because Anthropic essentially nerfed the capabilities for inference optimization. And so it might be one of those that the models don't actually get very good at. Who knows?
Cool. Well, keep questions coming. Miriam will try to answer them. So now we're going to move on. Thank you so much, Miriam, for spending time with us this morning.
Thank you so much.
Appreciate it.
Bye.
All right. Next one, we'll have Abby. She's going to talk about reliability engineering for inference serving. Not sure you following Abby on LinkedIn or not, but she's known as the inference infra queen. And she has a lot of experience and work in this space. And I can't wait to hear what she's going to share with us this morning. So,
thank you so much, Ian.
Abby, morning. By the way, where are you joining from again? I forgot.
Lisbon, Portugal.
Wow. Okay. Europe somewhere. We got 2 folks from Europe this morning. And
yeah,
with that,
both of them at the very starting because it's evening for us already.
Yeah, I got you. Thank you for joining us at this late in the hours over there. And with this is all yours.
Thank you so much. Okay, perfect. So, hello everyone. Welcome to my talk on reliability engineering for inference serving. As you probably know, and I agree with everything Mariam said, which is there's so much shift happening in inferencing itself. Right now, if anybody's putting on inference pipelines in production, the big problem is how do we make them reliable? And that's an important question, which I've been thinking about a lot, and it's a lot to do with the work that I've been doing over the past couple of years. So I am the ex-founder and research engineering lead for Abide AI. Right now, I'm in an advisor capacity with them. My job is essentially building the infra platform for agentic systems. So I developed an in-house agentic system observability library specifically for this kind of work. And one of the main reasons for this was there's a lot of existing tooling that assumes stateless request, but there's not enough good tooling out there for stateful request structures, which is what your agentic systems are working on. Outside of that, I'm also doing a doctoral degree in SLO adaptive inference systems, working on compilers. So that's a little bit about me. I have a book which came out. So the LLM Ops book, I wrote that, finished it in 2024 December. So it's a little bit outdated, but it's nice to see. Okay, you can possibly track where I'm coming from, which is from like a very ops and observability kind of mindset itself. And right now I'm working on a book called GPU Engineering, AI Inference and Systems Design, which is finishing up next month, and it will come out in September this year. I teach a course on Maven. Anyway, we'll talk about that later. Let's go on to the actual talk itself. So today's talk will be in 3 parts. One is why is reliability hard? Second thing is how is inference changing? Because you would hear this, the entire industry is shifting, and it's shifting so quickly. It's very hard to be able to figure out where it's going. So I'll try to address the second part. And the third thing, what you want to measure within your inference pipelines right now and going in the future as well. So when we talk about reliability, the first thing is what is actually reliability? It's a very, you can call it an art, you can call it an engineering, depending on wherever you're looking at. I like to call it an art because, again, you can't white code your way into this. So there has to be a lot of pattern recognition you've done over a period of time. But the key goal in reliability is there are going to be failures. They're literally inevitable. There's going to be complexity because this complexity comes from distributed systems, which creates these nonlinear interactions as well as cascading failures. There's going to be trade-offs, and this is the main play which makes reliability really hard. But reliability engineering is not really about preventing every failure. That's literally impossible. You can't prevent it. It's about designing systems that can continue delivering predictable outcomes, especially when failures are going to happen. So it's about being prepared, not about curing every single thing out there. But the main challenge in modern distributed systems is there's so many trade-offs between performance, availability, as well as cost. So how do you keep all of them front and center at all point in times? And AI inference systems basically inherit all of these challenges, plus then add all of the challenges and failures with GPUs itself, plus with long-lived states and agentic execution on top. So it becomes a slightly more complex problems than we have seen till date. But I can tell you this is not a new problem. Most of the problems that you're seeing in inference systems have been here for the last couple of years. So this is a very common thing you would have seen, which is a pipeline ends up breaking, and the ML intuition will basically say, or ML engineer on the team will basically say, this makes no sense, we're well under capacity. And the infra engineer will say, well, something is holding my memory hostage, which is memory has essentially become a reliability concern. And this is not a new problem. Once again, I'll tell you 3 or 4 case studies to give you a very good idea on where have we seen all of these problems before. So the first case study is Hadoop versus Spark. So the big data world, people who are very old in this room from like pre-2014, 2015 world, you would have remembered this, which is how Spark was originally sold. They said, well, you're going to have the same data, you're going to have the same cluster, and it's going to be much faster than using Hadoop. And well, part of that was true, but there was a hidden change, which is it was not that easy. Why? Because MapReduce or Hadoop basically treated execution as disposable. If any task failed, you just restarted it. So the failure was cheap. What happened when we introduced Spark was now these executors basically held state, which is your RDTs lived in memory. So the partial progress that you were making suddenly had value. Now, a single inference request still behaves very much like Hadoop systems. You do the work, you return the result, you move on. But the modern inferencing systems, especially the inferencing systems with agentic AI that you're seeing more and more of starting from mid of this year, and you'll see more of them in the coming few years to come, they behave more like Spark as compared to like Hadoop, which is there's long-lived execution, there's persistent states, the resources will stay allocated far longer than we expect. So what's the lesson here? First lesson that you want to take away is when execution becomes stateful, the reliability assumptions are going to change. So what worked for inferencing pipelines 2 years ago is not going to work for inference pipelines right now. The second case study. So again, some people would remember this as well, which is the Lambda functions. Well, initially, we were relying very heavily on Lambda functions within cloud computing itself. And what happened was somewhere around 2010, AWS teams basically moved towards orchestrated workflow. And you would have seen this come up more often in 2016, 2017, which is we started going towards step functions, towards Airflow, towards temporal or Argo, basically the workflows. So what these workflows did for you was something very similar, which is the failures were no longer cheap. The retries were compounded across stages. Every single time you made any partial progress that stayed alive in the system, you got the zombie workflow. So it was still running, it was still costing money, and it was not doing anything useful. Does that sound very similar to you? Yes, well, that's agentic systems for you. So lesson number 2, what works for stateful systems completely breaks for stateless systems. The third one, which is simple queries versus database transaction. If you work with SQL, you've seen this as well. So as we move, as this move was happening in the industry, which is as the database engineers were moving towards database transaction, essentially, the same lesson sort of got repeated, which is a simple query was easy to operate. It ran, it completed, it failed, you retried it. The cost was predictable, the failure was manageable. Now compare that to a long-running transaction, and these long-running transactions are very similar to the self-running agents, you could say, or the agents that are trying to choose between should I trigger up a web search right now or should I call up another tool? This is essentially a workflow. So the progress you're making starts to matter, and that's when everything changes. A failed query is basically an inconvenience, but a failed transaction, that can become a system-wide problem. So the same lesson here, which is an agent is much closer to a transaction. It plans, it accumulates context, it calls tools, it maintains intermediate state, and it invests in compute over a period of time. So just like transactions, the most expensive failures will most likely happen near the end, never at the beginning. If an agent spends 60 seconds reasoning, making 20 tool calls, and ends up burning 100,000 tokens, and then it fails, well, you've already paid the bill. The work is gone, the cost will remain in your ledger for the next quarter at least. And the moment this progress becomes valuable, the priorities that we have in reliability engineering, they become much more complex. Because stateless systems, they care about successful requests, but stateful systems, this is the main thing you want to take away with yourself, which is anytime you're trying to design any stateless system, that just cares about successful requests. Any observability platform you're looking at right now, or any tracing platforms you're looking at right now, they're designed essentially with this idea. But stateful systems, they care about preserving progress. And the reliability engineering that you're going to do for them is going to be about treating progress as a reliability problem. The fourth thing, Kubernetes. again, maybe if some of you have probably worked in Kubernetes, you would have seen that, which is one bad reconciliation becomes thousands. The APIs get hammered, your clusters become unstable. Well, Kubernetes didn't fix this by making controllers smarter. It added guardrails, which is it added backoff, it added rate limits, it added idempotency, it added convergence guarantees. The entire schmoozing the world of reliability engineering. Now let's look at agents. We're trying to do exactly the same thing. So our loop looks something like you're doing some observation, then the agent is trying to decide, making a tool call, updating the state, and repeating the entire process again. The only difference is the policy engine, in this case, is a large language model. And the side effects, well, those will cost you GPU time as well as API calls. So just like a bad controller was burning in API capacity, a bad agent burns the GPU capacity. A bad controller was something that ended up never converging. A bad agent is something that never finishes. Same identical problem, which is think of agents as reconciliation loops with a GPU budget. And every agent, what it does is it becomes a control plane problem. And that's the mental mindset that you want to look at agents from. Now, traditional inference, or the inference that we were seeing, or you would still see, there's two kinds of job posts that do exist right now, which is there will be something called inference engineer, and a lot of work will be around quantization. A lot of work will be around the training side. I still call that traditional inference. And the second kind of inference that is coming up is more around agentic inference. These two inferences are very different. The way I look at it is inference as a pre-deployment concern and inference as a post-deployment and serving concerns. Both of them will have different reliability metrics. And today I'll talk about the later, which is the post-deployment one. So how is it essentially changing? Well, look at this comparison in front of you. So look at the traditional inference on the left. You have a request that arrives in your system, the model generates an answer, the request is completed, the state disappears, failures are cheap, your cost will always be bounded. Now look at what's happening within the agentic inference itself. Your execution becomes long-lived, your state is going to persist, your progress is going to accumulate, tool calls will create dependencies, and failures will happen towards the end, after the work is already done, after it has already made a lot of calls. So the cost will accumulate even before you know something went wrong. So the capacity planning suddenly turns nonlinear, and it's not a model problem anymore, it's an execution problem. So what you're looking at here is a stateful distributed system where the control plane happens to be powered by a large language model. Once you see it that way, every single failure mode starts looking very similar for you. Now, the reason I say this is traditional inference was basically asking questions. So when we build a RAG system, for example, we are still in the traditional model. We're retrieving the context, we are augmenting a prompt, we are generating an answer, and the request ends. The state disappears. Even advanced RAGs, mostly they're answering just a question. And that's the reason I'm calling it agentic inference, because the way RAG systems are designed versus the way agentic systems are designed is very different. And the kind of priorities each would have would be very different as well. Now, anytime you're doing agentic inference and your agent basically decides to continue or to loop, you're executing a program. And once you do that, you're introducing loops, you're introducing branching, you're introducing long-lived state, you're introducing external side effects. So the problem is really not just that, oh my God, LLMs are unreliable. No, they're super reliable. The challenge is that execution has always been harder to make reliable than inferencing. So what we're building is basically we're building systems that can execute instead of infer. And that's the priority shift that is happening right now. So that's the main reason why latency, cost, and failures, they all behave very differently than they used to. We're no longer thinking about just, we have a model and we're trying to serve predictions. No, we are serving long-lived execution programs that are running on top of GPUs. So when you have, I think it's a very good way to visualize it. in terms of how every single error across every single stage ends up compounding. So the challenge isn't any one step on its own. The challenge is basically knowing that every step and every layer will have a probability of failure. Every dependency will have its own latency. Every external system will have its own availability profile. So what matters now is that you're looking at reliability as across the layers, across every single dependency out there. So the execution graph, that's the where you're looking at inference serving reliability problems. It's not one step, but the entire surface area of an execution graph from beginning to the end. Now, why is that important? Well, the first thing is, even if you build up, like, let's say, an observability platform on top of it, most of the observability platforms still talk in averages, which is, let's say, time to first token, or this is your P50 latency. One of the things that really most of the data scientists here and most of the SRE people will tell you is that averages do lie. Your P50 can look fantastic, but the users will still end up being miserable. So in traditional inference, latency was mostly a user experience metric, right? But in agentic systems, your latency is also a capacity metric. And why do I say that? Because every additional second of execution will increase the amount of state your infrastructure must keep alive. And once that starts happening, reliability is not just an execution problem, it becomes a queuing problem very quickly. So this is the first thing you want to take. Maybe the second thing I've already said, there's a first thing, which is latency will create concurrency within your system. Why? GPUs are not servers, and they don't behave anything like servers. In traditional systems, we used to obsess over CPU, network, memory. With GPUs, the real constraint is often memory, not just compute itself. So the GPU can look perfectly healthy and still be unable to accept new work. That is the queuing problem that we've been talking about. Why? Because capacity is being consumed not just by computations itself, but by the state. So there are three big reliability changes that you have in these new agentic systems. The first thing is, think about it this way, which is latency always creates concurrency. When your requests are taking longer, so there's this guy, he was one of the scientists, I think, probably at MIT, and he created this law. His name is John Little. So he created this law, which became very popular as Little's law. So what he basically said is, the queuing theory states that the average number of items that live in a state is equal to the average arrival rate multiplied by the average time each item spends in the system. And you would have seen that. So for example, if you've been studying a lot of lead code problems or data structure problems, you would have seen these exact problems in execution itself. So now coming to inferencing, it's very similar. So you can take the Little's law and apply it over here, which is every concurrent run will be approximately equal to the arrival rate and the execution time of the previous query itself. And why does that matter? Because when requests take longer, for whatever reason, maybe your agent was planning, maybe it was doing tool calls, maybe it was just waiting, or maybe it was just maintaining the state itself. If you have more requests, those will overlap in time. So the most concurrent in-flight work would mean more KV cache and more session rate must be held simultaneously. So unlike a web server where a GPU at 20% utilization can already be a bad agent away from like an OOM. So the resource we're managing isn't just compute anymore, it's state. That's the first reliability metric you have to think about, which is the state is the main problem. So how do you look at the state? Well, you look at the execution graph. The second thing is the partial progress. So the partial progress is, of course, generated by the state itself, but it's a state management problem, which is how do we make sure that the KV cache is not creating more pressure on the system than is necessary? That's a reliability risk that we're talking about. Now, the reason for this, I think you would have seen this, the dashboards do lie. And right now I can say this very comfortably. I've not really seen good GPU tracers that are close to reality itself. Most of the tracers are very, very bad, and they're very isolated, which is they show you just what's happening on the GPU side. I've seen other tracers that will tell you what's happening on the request side, but they don't combine everything together. And that's what's missing in terms of being able to debug these agentic inference pipelines, which is having an end-to-end execution graph and being able to see once very quickly where the problems are happening. So the question you're looking for isn't really how busy is my GPU, but the question you want to ask is how much state is my GPU carrying? Now, those are two very different reliability questions. Most of the people in the industry are still asking that first question, which is how busy is my GPU? Is that, let me try to optimize that? No. What you want to ask about is how much state is the GPU carrying, and what's a good time to remove that state or to maintain that state. How long do you have to hold that state itself? That's the reliability problem that you would be looking at in the next few years to come. The third thing is cost is a reliability metric. Why? Well, I think it's pretty obvious to say if you have a system that you cannot afford, it becomes an unreliable system itself. So the first system isn't really an outage, it's basically unaffordability, which is the cost maintenance side of things, because every token has a price, every retry has a price, every second of execution has a price. So reliability is no longer just about protecting uptime, it's about protecting token economics. So what are the new SLOs that you should be thinking about? Well, then for the traditional systems, or for most of the observability tools you would see out there, what they're still looking at is availability, latency, error rates. No. For the new agentic inference systems, what you would be looking at beyond that is the cost per task, the task completion rate, the tool success rate, and the failure adjusted cost. And this becomes very important because if you don't measure it, it's very hard to be able to optimize it. So a successful request is no longer just the unit of value. It's basically making sure or knowing the economics behind a successfully completed task. And both of those are not always the same thing. So the best reliability teams that I've seen, what they're doing is not replacing the old SLOs. They're adding new dimensions that basically reflect how these systems are behaving in production. So what should observability do? Well, it has to evolve. It has to evolve to add visibility into all of these things, visibility into cost attribution, visibility into tool execution graphs, into the token flows, into the agent traces itself. So if you've been using, I don't know if you guys are building your own agents by yourself, and if so, what tracing tools that you're using, or if you're, let's say, using Logfire or Crew AI, then again, those are very, very limited. So they're not even combining the VLLM metrics, for example, or SGLang metrics with those ones. So right now, everything is basically sitting in silos. And we have spent years, in the last 3 years, most of the observability tooling I've seen in this space is learning how to trace request. Now, what we need to do is to go away from request and start tracing decisions, because decisions are becoming the unit of execution. If the decision hasn't been made successfully, or if the decision took way too many tokens, and if there was a failure within that decision itself that the agent was supposed to make, that is a failed task itself. So how to measure this? Well, these are the 5 numbers that you would be looking at. But before this, most teams are still monitoring request, tokens, GPU utilization. I would say these are the 5 things that you need to add on top of those ones, which is what's the peak VRAM per concurrent run? What are the number of tokens per successful task? How much complexity are you introducing through the tools itself? How expensive your failure becomes when it happens. So together, as you are looking at all of this, what you do is you have a much better picture of the system health than the GPU utilization will ever tell you, irrespective of how good your GPU utilization dashboard or tooling or tracer is. So let's go through them one by one. So if you want to take away something, take one screenshot from my talk. It has to be this one, not just because it looks like a comic, but this is one which you want to keep with you. So these 5 numbers, these are the same numbers we talked about in the last slide, but these will tell you what's about to happen, which is it will tell you when does the memory pressure become too much? How much will the real cost be? If there are too many people in the waiting, and essentially if your task becomes slow and if the system can no longer handle it, what is the system complexity like? What is the reliability waste? So all of these metrics, not one, not two, but all 5 of them together give you a very clear picture of your system altogether. So to wrap up, these are the reliability patterns that I'm seeing emerging. And the interesting part is none of these patterns are particularly exotic or new. These are the reliability engineering patterns that we've been used to for years. So the 4 examples that I gave you, the 4 case studies that we talked about with the Kubernetes controllers, with the Spark, every single team that worked on those solutions had exactly seen and adopted these patterns. So the first pattern is you need to budget over retries. The second pattern you're looking at is load shedding, which is not every request should be accepted. When your system becomes overloaded, protecting the platform is more important than attempting every task itself. The third thing is you need to do very aggressive context management itself. Unlimited context might sound super attractive, but it will very quickly become a memory problem. So the most reliable systems are the ones that are discarding the information intentionally and not keeping every single thing with them, because the state that you're holding within the system itself is a capacity problem, is the one creating the concurrency problem for yourself. The fourth thing is implementing circuit breakers around tools. And this is an idea you would have seen most likely around evals as well, which is in agentic systems, the weakest component isn't your model itself, it's the external dependency. One unhealthy tool can destabilize your entire workflow. And finally, what you need is the kill switches. So this one might sound very obvious, but many agentic systems still don't have a good way to terminate runway execution. Most of the cloud inference platforms don't have a really good way to terminate runway execution itself. So every mature execution platform eventually learns this lesson and starts implementing this itself. Because the goal here is this. The most reliable agent that you're trying to design, or the most reliable agentic pipeline that you're trying to design, is not the smartest pipeline itself. It's the best agentic pipelines I've seen are the ones that know exactly when to stop. And that should be the goal. Bounded execution, never perfect execution. If you can do bounded execution, reliability becomes an easy problem. So what are the final takeaways? If I had to compress every single thing that we talked about today into a few principles, here would be the 7 principles. The first thing is reliability is not just an uptime problem. A system can be available and still be unreliable. The second thing is if your latency is unpredictable, then the cost is going to explode. And your state will become the real bottleneck, not the flops, not the model parameters, but the state. The state in memory, the state in workflows, the state in execution graph. The state is what will limit your scalability. The third thing is latency is what creates concurrency within agentic pipelines itself. So this is one of the most important operational lessons in AI systems. The traffic isn't what is going to kill you, but your execution time is what's going to kill you. The fourth thing is concurrency will create cost. So every additional active execution that you're doing on your system is going to deplete your infrastructure. So reliability and economics, the token economics, they're basically the same conversation. Fifth thing is agents are execution systems. Stop thinking of them as model endpoints. Stop thinking of them as chat interfaces. Start thinking of them as execution systems, because execution systems need strong reliability engineering. The sixth thing that you should think about is think of GPUs as the stateful infrastructure, not accelerators, not just these devices that you have on your system, not faster CPUs, but what they are carrying is the critical execution state. And what needs to happen anytime you're carrying any critical execution state is you need to make it bounded, because bounded system will always outperform unbounded system. Every mature distributed systems team out there learns this one principle, which is you need to embrace limits. Limits on retries, limits on execution, limits on state growth, limits on resource consumption. And people who are building up AI systems in the future, and especially like inference pipelines on the serving side, they need to learn the same lesson very quickly. So while the technology might be new, while a lot of stuff that we're doing is new, but these lessons are not new. These lessons are familiar. The hardware might be different. The stakes might be higher, but the fundamentals are still the same. So that's my talk. So if there's one final thing I'll say is LLMs are system. Your performance lives in the boring details, not in the fun things that most people think about. Anyway, happy to talk about Q&A if you guys have any questions.
Abby, that's a lot of great takeaways and tips. I hope attendees were paying attention, and looking forward to your book.
Thank you so much.
We are a little bit over time, so feel free to take a look at the questions and then feel free to answer them
Perfect.
offline. And I hope you have time to hang around to answer those questions.
Thank you so
For
much.
the next, thank you, Abby, again. And for the next presentation, we'll bring up Suman. He is senior manager at NVIDIA on the NVIDIA Dynamo and Triton team. And he's going to share with us how Dynamo accelerates agent executions. So really looking forward to how to learn all about this stuff. All right, Suman, thank you. And the floor is yours.
All right. Thanks, Shane. Hello, everyone. Good morning. Thank you for having me here to discuss about what we are doing today in Dynamo for agentic inferencing. I'm Suman Tatiraju, senior manager. I run an engineering team at NVIDIA working on Dynamo, which is a open source distributed inference platform. This talk today is about like one big shift. What changes when the thing you are serving is an agent and not a chatbot? And how does Dynamo try to come up with smart solutions for this? Can skip this slide. All right. Let's start with at a very basic level. A chat request is one shot and is stateless. Basically a prompt in and a completion out. However, an agentic task is completely different. It's a trajectory. So you have an agentic task, which is like a loop where the model reasons, like think of all the green boxes as the reasoning boxes. And then it emits a tool call. The harness, in this example, you can think of it as a code agent harness. It runs this tool call and appends to the response. And then it goes back again. The loop happens where now the LLM reasons, there's a tool call again, and the sequence goes on. There is also subagents which get spawned, and then they join back once they're done, which has its own trajectory. So the key thing that we see here is in an agentic task, we have many LLM requests interleaved with tool calls. And this is something that starts looking at some kind of a structure that we can exploit. If we look at what is the common thing that goes into each of these LLMs is a stable prefix. It could be a system prompt, it could be a repo context, or as we discussed, it was the prior tool output. There is a lot of prefix match that happens. That is one of the structure elements. The second thing we discussed is this tool call itself. The tool calls generally tend to be like, it could be like a shell command. It could be running long tests, or it could be like a web search. The tool call itself can range between like a few milliseconds to a couple of minutes. That's another thing that we can exploit. There is a structural way of how agentic tasks work. First, a stable prefix. The second thing is a tool calling gaps along the LLM calls. The third is a very structure itself about how a parent agent spawns subagents. So there is like a parent and a child relationship. So there is that structure that we can exploit. And the fourth one, I think somebody was just talking about like, what is the actual metric that we want to measure here when it comes to agentic tasks? It's not per request latency anymore. It's about what is the end-to-end run that the task takes, how long does it take, and we are trying to optimize for that. So the key takeaway here is agentic inference has structure. Some are GPU bound, which is the LLM turns. And then during the tool calls, the GPU is idle. So what happens to the KV cache that the trajectory was using? It's just sitting idle there when a tool call is happening. The same thing about subagents. When subagents exist, like for example here, when we do a join here, the subagent is done. What happens to its KV cache? Should it actually stay in the GPU's HBM? Now, these are all the exploits that we will talk about in today's talk. Again, another way of looking at it is making sure, keep this in your mind because this will keep coming back as I talk, stable prefixes, tool gaps, session graphs, and what is the actual objective, which is like the end-to-end task progress and not isolated request latencies. So this is a representative perf improvements that we have seen through our experiments. Again, these are all experiments, and everything that we have done is available in Dynamo repo. And I will call out when there is an RFC or something that we are currently working on. But most of the experiments are already available. The three things that you will see is about scheduling, agentic hints, and cache policy. Let's talk about the first one, which is the scheduling. We saw there is that structure that current servers do not exploit because they consider them as individual requests. But what if our scheduler, as part of a router, also is session aware? It knows what are the subagents. It knows when tool calling will happen. Can we exploit that to optimize? And this is one of the experiments that we did with Thunder Agent. Thunder Agent is in a paper actually where they discuss some of these techniques, and we implemented some of them in Dynamo, and we saw 16% improvement. The use case here was we were using a coding agent on a 8 H-100 node, H100 node, using a coding agent with, I think, 10 trajectories and 36 concurrencies. It's an experiment which shows that this is the right way to progress. The other exploration that we did were agentic hints. I'm going to discuss everything in detail, but this is like the perf improvements that we have seen with agentic hints. We increased the performance of the number of queries per minute on shallow deep research by 3.3x. The third one is the caching policies, about what happens after a subagent is done. You evict its KV cache so that the parent agent's cache is still resident and we can use it. So that showed another 25% improvement on our KV cache hit rate. All these experiments show that we are heading in the right direction. So that's why at the end, I will actually present a roadmap of what Dynamo is doing for improving agentic task performance during serving. So to tie all of these, so think about what happens in a regular chat request. Like there's no relationship between one chat request to another chat request. But with agentic tasks, we have trajectories and they are linked between parent and child. We need to know for any kind of improvements that we need, how are these requests connected? And for that, we have established what is called as a session identity. All requests in this task have the same session ID from which you can establish a parent-child relationship. Why was this needed? Every harness has its own identity. Like Claude Code, Codex, OpenCode have their own HTTP headers for session identity. And they are unaware of Dynamo. So when you have a harness talking to Dynamo, what Dynamo does in its front end is it normalizes all the headers that it is getting into its own internal representation, basically mapping whatever Claude Code, Codex, and OpenCode may have, or any custom identity harness that the harness may be using. We normalize it to an internal representation of our session ID. And this enables us to have the same representation across everything downstream, which is our front end, which we use for generating traces, replays, and profiling signals. The router now knows like, okay, all these requests are now related to the same session ID, and it can actually figure out whether this request is for tool calling or it is for an LLM. So we use this session ID everywhere downstream. And this is a very key aspect that we want to say here is like the identity connects the requests, but it doesn't do anything on its own. We leave individual components to decide what optimization they want to do given this information. So it's not necessarily like we are saying that it has to be done a certain way. We are only an advisory where we say, okay, these are all connected. Now it's up to individual components whether they want to act on top of it. The same thing for KV cache layers. How do you reuse and prepare the existing KV cache blocks based on session IDs? And this kind of joins the whole picture of we needed a single identity to establish what are the different trajectories and runs for a particular agent task. The next thing that you look into is there is only so much that you can infer from the structure. We spoke about how there are gaps between tool calls, and there is this parent-child relationship between agents and sub-agents. But there are things that only the harness can know ahead of time. Things like, okay, is this task a parent agent, which is, let's say, it impacts UX, versus a background sub-agent whose priority is okay if there is some delay, but for something that impacts UX, the agent would know. So one way to give us hints during serving is via agent hints. So we have something called as the NVEXT agent hints for the harness to give us hints so that we can, based on this hint, make changes to our queuing and scheduling. It also impacts how we prepare our caches. So each of these, I'll go in detail now. So there are 3 hints that we currently support. One is priority. As I said, like the harness can easily tell us whether a particular trajectory is higher priority than the others. And those agentic hints are basically request intents. They are only intents. We again, the infrastructure chooses the final actuation. The router uses this priority to reorder what's in the pending queue when there is pressure, so that tasks with higher priority get queued at the beginning of the queue. The same priority is also sent to the engine schedulers if engines support this priority. The second one is the OSL. Harnesses know generally like what is a good OSL estimation. The prompt could be like summarize in 100 words or something like that. And that intent is now passed on, which we can use it for capacity tracking. The KV warmup, which is like, oh, we may want to speculatively pre-fill our KV cache blocks if the agent gives us a hint. Again, these are on top of additional structural information that we already have from the nature of how these tasks are scheduled. These are additional hints that help us. Remember the agentic hint that we gave, which I showed earlier? This is the one, which is the priority, which we are using for establishing priority reorders for our router queue. The code for this is already there in today's code, and we have tested it out across all 3 engines, VLLM, TRT, LLM, and SGLang. So you should be able to test it out today from tip of tray. So when we established the single session identity, now how do we make improvements without observability? So I think the fundamental thing that we are trying to fix here is like, given this session identity, are we able to generate traces which have all this information about, are we in a tool calling phase? Are we in an LLM phase? If we are in the LLM phase, then is it the pre-fill? It's the decode? What are the metrics? We can now establish, using the session ID, request traces with serving metrics, tool intent, and parent and child structure. Now, this diagram shows an example of what we did by using one of the deep research trees, which clearly shows that when do we have, in this agentic task, when do we have a tool call, which is doing a web search, versus an LLM call for reasoning. And you tie this whole thing up to get a clear view of where your latencies are. Once you have an observable trace, now it's about, now what do you do with it? It's very important to understand that generating this trace could have been done by the harness emitting you events. Even if the harness doesn't emit events to a Dynamo can still figure out through its metrics, and also figuring out from the session IDs, like when did a cool tool calling happen. It's basically, it can infer from all of this. So we have built a smart system where even if harnesses don't send us events, we will be able to show end-to-end agent graph. Now, what do we do with this? Now that we have generated traces, this is where we run this iteration about how do we now change routing policies or scheduling techniques. And then instead of having to use GPUs, Dynamo has something called as the Dynamo Mocker, which simulates VLLM and SGLang scheduler and also cache management. So instead of now using your precious GPU, once you have captured your traces, you can now replay them. So once you capture your session traces, Dynamo normalizes them to mooncake hash format. It replaces your token contents through and replaces them with token hashes, improves security, and also enables you to look into the prefix cache hits and all of that. So you can replay these traces and rerun them live against a particular GPU or against a simulated engine via Dynamo Mocker. That reduces the cost. You can actually iterate very quickly on your engine and scheduler policies. The agent traces that we have collected are all connected because of the session ID that we established. Otherwise, they would have been individual traces and we wouldn't have been able to link them up. It also is going to show you the exact structure of your agent. And this iteration step is going to help you with improving your engine and scheduler policies. Remember the slide where I showed about Thunder Agent router? Thunder Agent router is actually a router which is session aware. So it can now schedule worker requests based on the understanding that it is no more a generic request aware, but is actually session aware. To enable that, in our experiments, it ended up having an additional queue, which is like shown in the purple here, in addition to the current router queue, which was request aware. It was just an experiment to showcase whether a session aware router would actually improve anything. So that was our current implementation where we had an additional queue. Now that actually confuses the router where we have now a separate path for request aware and separate path for session aware. We are now moving towards a single admission gate inside our router, which uses both the session state and the engine pressure to schedule tasks. Again, this is where it's an improvement that we are going to get it so that we have one single admission gate, which is both session and request aware. And then it will schedule a bounded active set for the engine. This is currently that the team is currently actively developing. The remaining part, the previous parts of session identity, tracing, and replay, all of that are already done and available in our repo. This is something now, the next few slides I'm going to discuss are about the future and the RFCs that we have proposed. We spoke about structure, we spoke about agents, hints, agentic hints. Now we are talking to the next layer of KV cache intents that we can provide inference engines. Inference engines are stateless and they remain authoritative in this mechanism. What we are trying to propose is a KV orchestrator, which has the knowledge from the router of what are the tasks or the requests which belong to a particular session, and they produce intent related to caching. Now I'll speak a little more on how does caching actually come into picture. Remember the third slide where I showed that we were able to get about 25% better cache hit rate. It's coming from one of our experiments where we tried to see there are a couple of ways we can do here. If you remember, there was this LLM running, and then there is a tool call that happens after that. Now, during this tool call can be a few minutes long. So what can we do during this time when the trajectories KV cache is resident at GPU? Can we actually make the KV cache now go to a lower tier of the cache instead of being resident inside GPU memory? Can we, at the end of subagent, evict KV cache. So all of this requires some intent that we can send to the inference engine. So the team is currently working on APIs that we can work and give this agentic KV intent to the inference engines, so that inference engines can now make authoritative calls, or they may say, okay, this is just a hint, we may ignore it, but at least we want to showcase what is the improvement that we can get through this path. The final control of scheduling and caching at the end always lies with the inference engines, and they continue to remain authoritative. We are adding layers on top of that to provide these hints given the structure that we can exploit. This is the one that I was talking about. Now, what are the intents that we can provide the inference engines? This is about placement and life cycles. One is to share, which is like reuse a prefix from another worker. So we have shown that the very first structure that is present across calls is the shared prefix. And if we can share it across multiple runs, that's the way you can get best benefit for your KV cache blocks, which are already calculated. What happens when there was a subagent and now you're joining back to your parent agent? At that point, what happens is we can prefetch the parent agent's cache and then continue instead of like either recompute, because how can we prefetch? We could have demoted at the time of when the subagent comes in. We can demote the parent agent's KV cache to a lower tier, and when the subagent joins back, we can prefetch it. So we're trying to see how we can keep our KV cache resident inside HBM, knowing that there was a structure. The same goes about protecting KV. One is pinning, where we do bounded protection for a valuable prefix. And then there is a retain, which is like the bias eviction order with relative priority and duration. Now, these are all hints. It is up to the inference engine to either support it, or even if it is supported, it may not, like based on how you configure it may not act on it. But to enable all of this, we need to tag each of the KV blocks with the session ID so that we can do all the lookup for the router to give these intents. That's something that we are currently working on. And we will know once. I think the first experiment that we did was with SGLang, which I want to show you, like how did we get that 25% hit rate. This was the subagent lifecycle that we saw. The parent becomes idle and becomes a demotion candidate. So you can demote the KV cache to a lower tier, and then at the time when the tool subagent closes, you can prefetch the parent and the child KV can get released. This was the experiment that showed that 25% extra cache hit rate. These are all the RFCs that we have proposed, which take care of all the, or exploiting all the structure that is present. So in today's mainline source code, you have the identity, which is the session identity I spoke about, which is a header native. The observability part, which is about request tracing and replay. We are currently doing the schedule, which is like the admission control, which is both session aware and request aware. There will also be sticky session awareness here. And the RFCs that we have is like for the caching layers. Now, can we optimize for knowing the structure? How do we optimize for KV cache? At the horizon, we expect that we can bring in your own routing algorithms and profiles. But then the goal is to have one single session identity and observable policies. The engine still is the authority here. These are all hints that engine can take or not. Right. Thanks. And I'm open to some questions now. But if you want to reach out to me, that's my email address. And please feel free to connect on LinkedIn. Thank you.
Thank you. It's good to see a lot of good stuff being added to Dynamo to support agent involvement. There's a few good questions. I brought up one for you to take a look and answer. Does this mean the agent hints are not explicitly sent by the harness, but instead infer from session context to inform the routing priority?
The agent hints are explicitly sent by the harness. We expect them to send the harness, especially the prioritization, the OSL, all of that. They are sent by the harness to Dynamo. Dynamo, again, as I said, like Dynamo can figure out the structure, but it won't know whether this was higher priority than that. The agent harness is the authority there, which can tell us. It can hint us that, hey, this is higher priority, and it ends up being important for your tasks end-to-end run. So
Got it.
it can hint
Cool.
on us.
Thank you. There's many more questions, but can you hang around and answer those questions online?
Right.
Because we're gonna transition to the next presentation. Thank you, Suman,
All right.
again.
Thank you.
All right. For the next presentation, we have our very own from Momento, Kawaja. He's gonna share about all about inference. So if this topic is something you're really interested in, definitely the talk that you want to pay attention to. A lot of good stuff that Kawaja has put together. So I'm gonna hand it over to Kawaja. So yours.
All right. Thank you, Ian. So my talk today is going to kind of share some personal reflections on my journey as I ramped up on inference. My background is in distributed systems, and I honestly felt very intimidated when I started learning about inference. And it's because there's a lot of new terms. The vocabulary is very different. You go from, Byzantine failures and sharding and clustering on the distributed system side to attention heads and KV projections, CUDA kernels, tensor parallelism, quantization formats. It seems like you are landed in a new country and everybody is speaking a different language and you kind of still trying to figure out what's going on. And my talk today is going to cover why you should not, if you're a systems person, why you should not be intimidated by inference, because at the end of the day, it is all very, very similar problems. There's still a ton of routing. There's still a ton of scheduling. There's back pressure. There's budgeting involved in capacity planning, utilization. And a lot of the techniques that you've learned just building systems apply here. And they transfer over here quite well too. So we're going to go over some of the key concepts as illustrative examples of where the hard distributed systems problems are, but also help you ramp up on what is actually happening inside the inference stack when you send in a prompt. Now, when you send a token, when you send a prompt, there are two common stages. You can always break this down further, but the two common stages inside of your inference stack are the prefill sides, and then there's the decode side. The prefill is processing the request that you have. It's simply suggesting, simply processing all of the prompt, all of the input that you're giving it. If you may recall a riddle from third grade around, you are driving a school bus, and that school bus has no passengers on it, and at the first stop, one person comes in, and at the second stop, two more people come in, and at the third stop, the number of passengers doubles, and then at the fourth stop, a third of the people leave, and the riddle goes on and on and on until the final question is, who's driving the bus? Now, you knew all along who's driving the bus, but you really had to process the entire input before you can give the answer. And in this particular scenario, like listening to the story of the bus and all of the context, whether it's relevant or not, you still have to process all of that because you don't really know what the question may be. That is the prefill side. It processes the full prompt. It does it in parallel. It fills up. It generates what's called the KV cache. And it's very, very compute intensive. Once that is done, Then you start the decode phase. The decode phase is the actual answering phase. And in the long-winded school bus analogy, when you're driving it and people are coming on and off and so forth, the prefill took a lot longer for you to process than the actual output. The output was just one word. It's you. You're driving the bus. But in that particular case, the prefill to decode ratio is very obvious, right? Like lots of prefill, very little answer. The decode, the way it works is it's generating one token at a time, and you can't come up with the next token until you have the last one. And that is a very memory bandwidth bound problem. And it's the streaming response. It's one word at a time, but you can't start on the decode side until you have the prefill part done. Now, let's walk through the journey of a prompt. So when you go to ChatGPT or Claude Code or any inference provider or chatbot interface, you start with a prompt. And that prompt could be, if it's a coding agent, it could be something like refactor this function, and that converts into, well, the actual function, the code, and all the relevant context that comes with it. That prompt then goes and gets tokenized on the server side. And a little bit of text can turn into thousands of tokens. It's roughly 1-to-1 or 0.66 to 1 ratio of like words to token count. But each of your words are going to get converted into tokens. And those tokens then need to get converted into tensors. This is like basically mapping to the mental model of the LLM that you have that you're going to interact with. So you got to convert your word into a token and that token into the KV. And what happens is you immediately, when the prompt comes in and it's been tokenized, the first thing the inference stack's going to do is, have I seen this before? Your brain might have done that too when I started telling you about the school bus riddle. You thought, have I heard this before? I already know where this is going. And based on the answer, if it has never seen this, it's going to process this, the input prompt, the tokens, and it's going to generate the KV, the key value pairs for it. And it's going to populate that typically in a GPU VRAM. And once that whole thing is done, it's going to pass that on to the decoder. The decoder is then going to start answering the question. And it is really, really important to know that the prefill to decode ratio of your particular workflow, because it actually meaningfully impacts the way you do capacity planning and so forth. Now, in each of these stages, the cost is very different. So in the prefill, it's very, very compute heavy. In the KV cache side, it's just gigabytes and gigabytes of memory. It's just storage. On the decode side, it's all memory bandwidth. How quickly can you access every token that had been generated? And what the users tend to care about in a chatbot agent is TTFT, which is time to first token. In a coding agent, TTFT looks relevant, but it's actually the total throughput. How quickly can I get to the final answer? How quickly can I generate the full line, like the set of lines of code that need to happen? Now, in the case where it is a hit, you're good. You can just reuse the part, the subset, or all of the prefill that you've already seen before. Now, KV caching is very different and much more difficult than the traditional caching that we may be familiar with as distributed systems people. Usually, when at Momento, we have a lot of our customers that run very, very small objects, 4 kilobytes, 10 kilobytes. And in regards to with KV caching, you actually need to transfer gigabytes of data. So the storage footprint is meaningfully larger, and the amount of data that needs to get sloshed back and forth for each request is meaningfully larger. And you're not trying to keep all this data in DRAM. If you remember, the decode loop is very memory bandwidth intense. So during the decode, the entirety of the KV cache for a particular prompt needs to really reside inside of the GPU, lest it thrash. And we'll see some examples of where that happens. And the third part is that KV caches are incredibly hard to share across users. We'll dive into why that is. So let's take a look at a very, very tiny baby model, okay? A Qwen 3 4 billion parameter model with FP8 tensors. Like, the one word from you, like a simple word like hello or please, seems inconsequential. But that one word on this tiny 4 billion parameter model turns into 72 kilobytes of KV. That is 72 kilobytes that has to be stored inside the very, very expensive GPU VRAM. And to give you some context on that, the largest GPUs like the B200s and the they're in the hundreds of gigs of memory. The ones that I ran my experiments on, like, they only have 24 gigs of GPU resident HBM high bandwidth memory. And GPU memory is really, really expensive. That's why this simple notion of saying the word please has way more ramifications than you may realize. It's 72 kilobytes out of the 24 gigs. But why is this so hard to share? Why can't my session have some level of sharing with Hien's session, as an example? And part of that is because attention is causal. If you go back to the bus analogy, if I ended the prompt with the question, how far can it fly? You know that you are on the bus. The fact that it's a bus probably means it cannot fly, but that context was relevant. And it's relevant whether it's a bus or an airplane, and all of that kind of builds upon each other. And this is how attention works in most of these models. It's if you take a much, much simpler example, time flies like an arrow. In that sentence, time makes the word flies turn into a verb, and like is a preposition. Whereas if I say fruit flies like a banana, flies is suddenly a noun. It's not a verb anymore. So the preceding word actually had meaningful impact on what flies like an arrow or like a banana means. So this is what really makes it hard for KV caches to be shared across sessions. Everything that comes before it ends up mattering to what comes after. And there's a mapping of how important let's say the beginning of a prompt is to the end of the prompt. And these prompts really, really add up over time. And when the prefix caching happens, it kind of gets broken into a few things. In a multi-turn workflow, you typically have a system prompt. And that's going to be common between me and other users of the chatbot or the coding agent. That can go everywhere, and that is shareable. But the prior turns in my session are very limited and very personalized to me. And if I ask a set of questions that consult the same coding files that Hien asks about, we're not going to be able to share that because some things might be different along the way. So the prior turns are crucial in making sure that the integrity of the prefix is preserved. And then usually your system prompt and your prior turns are going to be cached from the last time you were interacting with the stack. But the new turn has to be pre-filled again. And then the output tokens kind of come in, and after you have pre-filled the new turn aspects of it. And to do a distributed system style experiment here, we ran a very simple thing on a very open weight model with a very accessible GPU. Like the G6 instances on Amazon EC2 are readily available. They're not very expensive, and you don't have to get in line or do a capacity block to do it. So you can go repeat this workflow yourself and load the Qwen model here. The GPU is 24 gigabytes of HP RAM, and we use VLM.2 with automatic prefix caching enabled. That's what APC is. And the workflow was very simple. We said there's a 10K of system prompts, and then 12.8K of unique session prompts. So basically, we were going back and forth with the turn, and we were just continuing to add it. And again, when you're trying to host an inference fleet, what you want to do is try to optimize the throughput that you can get out of it. And you want to find the knee where at some point adding more concurrency is actually going to have a catastrophic effect on your overall throughput and the performance for the end users. And we realized, and you can do the math here for the particular model and the HPM, but we realized that if we ran 12 concurrent sessions with this microcoder, the mini coder example, with just 22,800 tokens, our P50 for time to first token was only about a second, which is pretty good for a modest GPU, and our P99 was still 2.6 seconds. And the reason why it performed really well is if you do the math, 12 sessions times 12.8K unique tokens, that's 154K. And if you divide how much capacity there is left on this 24 gig GPU after you have the CUDA kernels, after you have the VLM overhead, and after you have some of the headroom that you want to leave behind, you end up with being able to store about 178,000 tokens for this particular model. So at 12 sessions, performance looks great. Let's add 2 more sessions. And this, if you do the math, this is exactly where your concurrent sessions no longer fit inside of the HBM. The KV cache just no longer fits. And it's almost unobservable at P50 because half the sessions are going to get lucky and run in an uninterrupted fashion. But your P99 is telling the other story, right? Where your P99 goes from 2 seconds to 38 seconds because you're thrashing. You're getting data back and forth, you're losing it and so forth, and you're just waiting for things to finish before you can regenerate. And that bimodal distribution is, just because of lucky requests being able to finish without having their data being evicted from the HBM. This is a very classic distributed systems problem. It's a capacity planning problem. And it requires you to dive deep to understand what is the memory that's available, how much memory does each turn take, and how many can you run concurrently. And if you keep going down this path with KV caching, you see that knee exactly at 12 to 14 in this particular setup. Now, your mileage may vary if you're using different GPUs or different model and so forth, but you get the point that you got to understand the models, you got to understand your hardware, and then you got to understand how the concurrency has to be planned. Now, there are tiers of caching. As we learned earlier today, the requests are going to be very lumpy. I might send a very, very large request, and then I might go get coffee, or I might just spend my time reading the output, understanding it, running experiments, and running characterization on the particular workflows as well. You cannot afford to keep my state in the GPU VRAM while I am sitting there parsing the data, running my experiments. That will become a very, very expensive proposition. So data tiering becomes really important. And there's layers of data tiering. You can, typically these nodes have an order of magnitude more DRAM available to them. As expensive as DRAM is, it's way cheaper than the GPU RAM. And DRAM is nice because you can load the data really quickly from DRAM into the GPU when I come back for my next turn. But it is still pretty expensive. It's a little bit slower than having it directly in the HBM, but it's still much faster than going down a tier, which is the NVMe tier. Now, NVMEs or SSDs, you can get tens of terabytes available to you on these NVMEs. The latency is going to be higher, but you can store KV caches for a lot of concurrent sessions locally or on a remote NVMe. And throughput on NVMe is actually quite nice. It's where you really get into trouble is the latency and how long it takes you to kind of load it. It all comes down to state transfer. How much state do you need to transfer before you can start answering the actual question or the decode stage? And the other problem with NVMe that is very unusual in this particular world is because the data is so large and because it's constantly being recycled, you really run into endurance problems, like lifecycle problems on the NVMe. NVMEs are not meant to be constantly written over and over and over and over again. So if you're not careful and if you're not empathetic to how the NVMEs are designed, you can actually wear out your NVMEs by just writing the data repeatedly as well. And remote KVs really require a real data plane, and the data plane of being able to transfer, that state transfer, that data plane makes a huge difference. It is a where it's not just your ability to store the data cost effectively and in a quick manner, it's your ability really to transfer that data across tiers, across nodes, and so forth. And we noticed that as we started integrating KV caches into the Valkey project with LM Cache and VLM, we learned that one of the biggest latency barriers here was the amount of copying that had to be done. In Valkey 8, it's multi-threaded, but the main thread has to copy the data from its memory over to a place where the IO thread can get access to it. And then the IO thread writes the data onto the network, where it then gets read by a Rust SDK, which then buffers the whole n megabyte object. And then, and only after it's done, it copies it over to the Python area for LM cache. And then the copy goes from there onto the GPU. There is a lot of copying that is happening along the way. And intuitively, it sounds like copies can't be that bad because memory bandwidth is always going to be meaningfully higher than network bandwidth. But the problem is that it creates this artificial discretization, because you can't, like Valkey 8 can't actually start writing the data on the network until the main thread has copied the data into a buffer and passed it on. So you're waiting for that 4 megabyte item to be copied in memory before the IO thread can start writing it on the network. And that copying, you want to be able to utilize your network entirely. So that copying creates these spikes in idle time, and you don't want to waste that bandwidth. So Valkey 9 has a very interesting capability where instead of copying the entire object, the main thread just tells the IO threads, hey, here's where the item is in memory, and here's how large it is. Please just go write it over the kernel buffer. And that eliminates one copy along the way. On the client side, we've done things like pre-allocated buffers and so forth, so that we're not copying from Rust to Python and so forth. As you start optimizing the state transfer problem, the biggest thing that, at least for me, that I've been finding is just find all of the copies along the way and get rid of them. And one thing that comes as a very natural injection here is RDMA, remote direct memory access. So what if we could read the object from a remote DRAM or without even saying, get me this particular item? Then there's no copies at all. You're just literally reading the data and bringing it back. And just to give you a sense of how quick these numbers are, like we are able to deliver on a very modest node, like a CAGN 16XL on AWS EC2 that only has 200 gigabits per second of network bandwidth, right? And it only costs like $3.50 per hour. Very modest cost. These nodes are able to transfer data between each other. A megabyte over RDMA is only taking about 56 microseconds for an entire megabyte to be copied from one remote RAM onto the local RAM of a node. Now, to do this, you have to use EFA, you have to build RDMA on top of libfabric and so forth. There's a whole lot of things that you have to do, but by eliminating these copies and eliminating these extra steps of distractions along the way, you are actually able to meaningfully speed up the data transfer. And like 16 megabyte KV chunks are taking less than a millisecond to transfer over the network. And once you get the KV cache, once you solve the problem of transfer being fast, then you can start asking the question about, hey, is it faster for me to transfer the data, or is it faster for me to recompute it? But it gets a little bit more nuanced too. It's not just, is it faster for me to recompute it, but it's also, do I have the capacity to recompute it? Because if I don't have the compute capacity to recompute it, it may still be better for the overall system for me to transfer instead of recompute. And we talked about the experiment that I ran earlier and how the concurrency number of 12 was the right number for that specific workflow. And the key lesson here is not to come up with the actual number of concurrent sessions. It's actually the KV cache. Like your admission control criteria has to do with how much KV cache can you fit in the GPU concurrently. And this can create, we talked earlier today about reliability issues and what metrics really matter. Adding a, not being observant about the KV cache size that you're admitting can really cause problems in a multi-tenant environment where one long prompt can basically cause an eviction for everybody else. So be very, very mindful as you design the admission control criteria to keep KV cache in mind, and not just the size of the KV cache, but how it breaks down. So if you have like a single turn QA session, you might have a 1K, 1,000 tokens that are shared, but each unique session has 1,000 tokens as well. Whereas in a summary session, your shared prefix might be 2,000 tokens out of the 40,000 tokens. So the more sharing you can do on the KV cache, the more sessions you can store concurrently as well. But again, like just keep thinking hard about at what point does my GPU have to recompute or look elsewhere compared to its own HBM to continue the decode session. And one of the most tempting things is to always go after the last. So if my request was answered by node 3 last time, a very tempting thing is to just take my next request to node 3. And because the requests are so lumpy, I might request now, I might request in 2 minutes, or I might request in 20 minutes, or I might request right away. You can create these hotspots where like all of the sessions that had used node 3 in the past show up at the same time. And then you create queuing problems. And then you will actually really create the latency regressions for customers. And this is how you cause outages as well. So being able to confront the state transfer and being able to say, hey, I can reallocate my KV caches along the way. I can monitor for hotspots, and I can predict which nodes are going to be heavier and start making copies so that I can do, pick between the nodes in terms of where I'm going to route the request. These are all distributed systems problems, and there's a lot of really good work being done across the industry on how to not be too afraid of the state transfer and how to optimize it accordingly. And the other technique that the industry is really embracing is, let's just assume that prefill and decode are happening on two separate fleets. This is called disaggregation. You have a prefill fleet that can consult your cache and regenerate only what's missing. And then it's just going on to the decode fleet afterwards. And it creates this really nice separation of concerns. And it complies with this really nice distributed system tenet around do constant work. Because now you're always transferring data. It's not like an anomaly, and you eliminate the kind of the modality into your system if you're having to transfer states sometimes, but not the other. So the same distributed systems instincts apply here. Do bounded work. We learned that earlier today as well. Balanced by pressure, and the pressure is really by the KV caching. Pitting the roles, like having a disag fleet where one is, set of nodes are doing prefill and one set of nodes are doing decode. And by the way, that needs to be very dynamic as well, because the workflow characteristics might change and your prefill to decode ratio might change. And VLLM makes it easy for you to make a node, prefill 1 second and then only doing decode the next second and so forth. And don't be afraid to transfer the state. Just embrace the fact that the state needs to be transferred. And I'll leave you all with this. Even if you're not running your own inference fleet, as you go out and use Claude Code or whatever coding agent that you really love, think hard about how your context is going to be used, and apply a little bit of mechanical empathy in the system. Every token becomes state that somebody has to keep inside of their RAM, transfer across their network and so forth. So as users, long contexts are powerful, but use it wisely. Like resist the temptation to type please. Be like Kevin from The Office. Why use more words when few words do trick? It's surprisingly effective in letting the LLMs not get distracted as the context gets too long. Capacity plan for the KV and locality. If you're building these systems, locality is not an optimization. It's respect for the work, the pre-fill that's already been done. So go forth and design for the state that you are going to create in your inference stack.
Cool. Thank you, Kawaja.
Wow.
That was a lot of good stuff. And get your hands dirty, and that's how you learn. And a lot of concepts to grasp, but once you get your hands dirty, then it will all come naturally.
It was surprisingly easy to set up the inference stack. I mean, there's like it's a rabbit hole. Like you can keep going and optimizing and so forth, but it's actually surprisingly easy. Mike Callahan, who's he leads marketing at Momento. He actually like saw a LinkedIn post from me where I said, "Hey, it's really easy to set up your own inference stack." He went and did it too, and it worked. So if you really want to play with this, like really, like if you want to learn it, like go set up your stack, and you'll learn way faster by doing that.
Yeah, cool. So I see a few questions. I think that's one's very interesting. So let's talk about that one, which is show here. For teams running agents in production, how do you handle the gap between requests succeeded and agent actually did the task? A very interesting question here. Token metrics don't show if a 5-step agent hit its goal.
Yeah, so separation of concern is really important. Like there's one side of the fleet that, if you're running the inference stack, it's up to you to kind of monitor how many tokens are being consumed, how many tokens are being generated, and what the capacity management is. Then, and you, if you're running the inference stack, you really care, especially if you're charging by tokens, you really care about the token efficiency. But if you're writing the harness and if you're writing the actual agents, you care about whether the agent hits the goal or not. It's almost doesn't concern the inference service if you hit your goal or not, because I mean, there's a perverse incentive, right? Like if you don't hit your goal, you're going to come back and buy more things too. So generally, you want the agent to be able to assess and emit its own set of metrics around whether it met its goal or not, and how many tokens did it consume. Because in some cases, you might find that bigger models are more expensive, but they actually end up consuming fewer tokens to get the job done. That is not a concern of the inference fleet. That's the concern of whoever is building the agent. So you got to have your set of metrics and perspectives there to run your evals to see whether you succeeded or not.
Cool. We're hitting a lunch break, but let's take one more.
Okay.
This is a very interesting one, and then we'll go lunch.
Okay.
If you had to ban one buzzword from AI conferences for the next year because it's hiding real engineering problems, what would it be, and what should people discuss instead?
If I had to ban one word, if I had to ban one word from Claude Code, for what it's worth, it would be please. Like stop saying please to your coding agents, and I hope the coding agent stops saying honest. Like Claude Code just tries to go out of its way to say honest. But from a conference, that's an interesting.
Yeah.
Do you have an opinion on this?
I don't know. It's a tough one. Buzzword from AI conference next year is hiding real engineering. Token maxing? I don't know.
Token maxing? Yeah. Tokenomics? Oh, okay. Yeah. Tokenomics. Yeah. That's a pet peeve of mine. Everybody, like a lot of us are really interested in getting tokens to be cheaper and to reduce our cost per token. But really, what you want is not necessarily cheaper tokens. You want stuff to get done quickly. And sometimes you will do things faster. Like if I had to carry, what do you call it? If I had to carry like 50 books across the street, I'm not going to go rent a U-Haul truck. It's going to be faster for me to just walk and do it. But if I have to carry like 500 books across the state, maybe a U-Haul truck makes sense, right? So like using the right models for the right job is the key. And I think over obsession with tokenomics does hide the real engineering problem of the evals. Am I making progress towards the goal I have and so forth? I want to not keep people from their lunches. So I think what I will do is I'll stay back and type up any other answers that are here. Okay. We're going to be back here at 1:00 with another exciting session. Who's up at 1?
This is going to be from folks from Base 10. Talk about inference engineering. And the speakers actually wrote a book on this. So I'm very excited to hear about what he has to say.
All right.
Cool.
Enjoy your
So,
lunch break.
yeah, thank you. I already share a message. So we're going to take a break and we'll come back at 1. So please join us at 1. Thank you.
Okay.
All right, welcome everybody. Welcome back to the second half of the Infer Summit. We have a full lineup this afternoon with 7 sessions from companies like Base 10, Radix Arc, Databricks, Pinterest, and so on. So very exciting second half. I hope you had a good lunch, and hope you had grab some coffee. So we're gonna have a lot of interesting sessions for you to hang on for the rest of the afternoon. So for the next presentation is coming from Phillips, he's working at Base 10. And by the way, he has written a book on inference engineering. So I think he's going to show that book. I probably would talk about it as well. I've been meaning to read his book, and it's on my to-do list, so I will definitely get to it. But looking forward to his presentation talking about inference engineering for product differentiation. With that, Phillips, all yours.
Hey, thanks for having me, and thanks for the introduction. Hi, everybody. I'm Philip. I work at Base 10, and yes, I am the author of Inference Engineering, which is the first sort of large-scale guide to doing inference in production. But today, I'm not really here to talk so much about inference. I'm here to talk about products, and so let's get into it. You know, when you send a picture of yourself, you know, you should not do a group photo, because then no one knows which one is you. So I'm going to let you guess which one of these people is me. I'm from Base 10. Base 10 is a inference company. If you're in San Francisco, you've probably seen all of our pink and green buses all over. At Base 10, I have the privilege to work with a number of the best AI product teams in the world, companies who are taking the amazing capabilities of these large language models and other generative AI models and using them to deliver a very novel experience in a new form factor that wouldn't have been possible before. So today, what I'm going to talk about is, you know, a little bit of the history, the rise of open models, and why these AI native product companies are moving toward owning their own frontier models. We're going to talk about something called the trilemma of rather than a dilemma, because there's 3 things that we're trading off when it comes to building AI products. And we're going to talk about some of the inference engineering techniques that help you navigate that, as well as the sort of increase in the last few months of training specifically for inference, and how new inference techniques are making the sort of overlap between inference and training bigger every day. So let's get into it. Let's get into open models. I never know whether or not I should like include one of these slides anymore, because sometimes it feels like everyone's on open models already. Obviously, GLM 5.2 was enormous news over the last week or so. And a lot of people have been trying that model out and having really excellent results. But open source has actually been here for a while. I've been with Base 10 since early 2022. And I remember I was working with open source models for embedding, for image and voice, the early Whisper model, for example. But they didn't really get a ton of prominence in the industry until the last 18 months or so, with, you know, the DeepSeek, the Llama family back in the day. Now we have new models from Quen and Kimi and GLM, of course, the AI. And then we also have folks like Nemotron out of NVIDIA, Gemma out of Google, training open models all around the world. And what's exciting about this is that not only are these models viable alternatives to the closed models for basically any AI workload, especially cost-sensitive and latency-sensitive, but they're now forming a foundation on which you can build these specialized models. So while the industry as a whole has been going through this transition, we also see, you know, when I talk to hundreds of companies, and what I see consistently is the exact same journey of, you know, initial adoption through scaling, through integration of AI into their products. And it's throughout this journey that companies are really thinking about differentiation, which is the whole point of what I want to talk about today. 2 or 3 years ago, you could build a ChatGPT wrapper for anything and have people pretty excited to use it. Today, customer standards have gotten a lot higher very, very quickly. And so companies are thinking about, how do I move beyond just putting a language model in front of whatever service I was providing before, and start to think about extracting user signal from the things that they're building and refining that user signal into more and more specialized and effective intelligence at these specific tasks that the product is trying to solve. And you can think of this movement as almost like owning the frontier. We talk about a frontier model as a model that is at the efficient frontier of some combination of cost and intelligence, or latency or intelligence, or any combination of two factors that you want to talk about. And usually this label of frontier models is reserved for your latest GPT model, your latest Opus model, and occasionally a handful of open models as well, your GLMs, your Kimi K2 back in the day, DeepSeek R1 before that. There's moments where the open source and closed source frontiers kind of meet. But what we're increasingly seeing is companies defining for themselves what frontier intelligence looks like, and then building the infrastructure and the processes required to own that frontier. So what we're finding is that the best products come from mixing closed, open, and custom models. Sometimes you just want the off-the-shelf intelligence of a GPT or an Opus. Sometimes you want the speed and efficiency of an open model. And sometimes you have enough conviction in the way that you're using AI in your product to invest in building something custom and delivering it to your users. So a great example of this is Harvey. We were fortunate to work with them recently on some legal agent post-training work. And they have been building on open models, or on closed models for quite a while. And we're noticing kind of three problems with generic frontier models. The first was domain expertise, because these closed models are getting really good at a handful of tasks like coding, but they're not necessarily amazing at legal writing. Another issue is cost. As usage explodes, your token cost is going to scale linearly with that. And so with Harvey, they're obviously a fantastic company, a fantastic platform that's getting a ton of adoption, and with that comes a ton of cost. And then the final thing to think about is governance, is being able to own every single aspect of the operation of the model, understand the traces, understand the reasoning that's happening, not just look at the outputs that you're getting. And so a long-term strategy for good governance requires end-to-end ownership of the infrastructure. And so what Harvey did with us is they post-trained a very small Quen model, actually. So starting with a small model is great because you're going to, out of the box, get incredible performance and cost characteristics. And by combining the training run with the actual harness and environment that they're going to be using the model with, they were able to get really fantastic results in terms of the intelligence of the model on their specific well-defined benchmark against some of the best models in the world at the time. And along with this, they were able to do something. We're going to talk about this a little bit at the end. This is a preview of some of the inference-aware training techniques that we're using. They were able to implement a form of compaction to improve performance on long sequences of legal documents, as well as, of course, improve latency and cost characteristics. So why does a company like this make that kind of investment? Like, what is driving them there? And the answer is that they're just trying to do the same thing that engineers have been trying to do for a long time, and that is trade-off between speed, cost, and quality. So you have, of course, speed, the latency of the system. This is incredibly important for the user experience, because this is going to be how the user perceives the service that you're offering. You have cost. As AI companies are scaling, obviously the most important thing is just growth. This is a brand new market. Everyone's well-funded. We all want to go win big chunks of the market. But at the same time, companies are getting to the size where you really have to think about cost. Token costs are very material, and you want to make sure that you're building a viable and sustainable business with strong unit economics. And then possibly the most important piece is this quality piece, where users want to have trust in the models that they're using, feel like they're getting access to the best intelligence in the world, and make sure that the outcomes that they're getting from the products they're using are really, really high quality. And the inference serving piece is important for maintaining that. So each of these things is actually like very challenging. A lot of times when we talk about inference optimization, we're just talking about speed. How do you overcome the fundamental limitations of the GPU compute, as well as the memory bandwidth and memory amount on these cards? But there's also challenges and levers for improvement elsewhere, like in cost, with trading off latency for throughput, and with quality and making sure we're doing accurate serving and making sure that our techniques scale to serve larger and larger models. So let's take a look at inference engineering, and inference engineering specifically in the context of how each of these techniques relates to the cost, quality, and speed of the products that we're serving. So what's exciting about inference engineering, the reason that you need 256 pages to talk about this topic, is because it's not just one thing. It's not just how do you get VLLM up and running on a GPU. It's not just what do you know about PyTorch. It's not just one silver bullet model performance optimization technique. It's a series of performance and distributed systems problems sort of layered and composed together into a stack. And there's a lot of pieces to the stack. Like there's the whole other half of this problem, which is the infrastructure half, which I'm not going to talk as much about here today. It's very, very interesting and has a lot of horizontal scaling problems. But my solution to each of those problems is, just come use base 10. And so it's a little bit less interesting to hear that over and over again. What I am going to focus a little bit more on is some of the different trade-offs within the runtime and when each of these techniques is going to be appropriate for the performance profile that you're trying to hit based on your product. So the first place where sort of product specific and highly differentiated inference engineering comes in is speculative decoding. We've had the idea of speculative decoding for a couple of years, and it started out as just a basic draft model. Let's say you have, Qwen 0.5b and you have Qwen 200b, and they're running side by side. You use the small model to guess what the larger model might put out. And if those guesses are correct, well, then you've done a forward pass through a small model instead of a big model and saved yourself some time and resources. Speculative decoding is a very fun technique to start with because it's also a lossless technique. You're verifying every single intermediate output, which means you run no risk of quality reduction. But it is there's a lot of orchestration work around running those two models side by side. And it turns out that small models off the shelf are not very good speculators. So recent speculative decoding work has focused a lot more on training specific speculators for a model. Two of the major techniques for that are Eagle3 and dflash. And in each of these, you're asked to sort of train a speculator model based on the hidden states of the target model that is good at generating either a single or a sequence of draft tokens. And then, these models are usually 1 billion parameters, speculating against a model that's 1 trillion parameters. So you do save a lot on inference time. Now, the thing is, when you are training a speculator, the question is, what do you train it on? Well, it turns out that speculator performance depends a lot on the actual nature of the input sequences and output sequences, not just the lengths or the patterns or whatever, but the actual context. So this is one of the early places where you can look at your actual product and come up with a differentiated inference win. is saying, okay, I either have the ability to train on actual data that's passing through my product, or I have the ability to create a synthetic data set that very closely matches the type of information that my language model is processing. And I'm going to train a speculator just for that. And when you do that, you generally see much, much higher token acceptance rates, which ultimately leads to improved tokens per second and improved overall system latency. Now, speculative decoding is mostly a latency thing. It is not so great for throughput because you are, adding that second model and the orchestration between those models to your system. So if your product cares mostly about quality and about speed, this is going to be a great optimization for you. If you're mostly concerned about cost and high throughput, it's going to be potentially less valuable in some cases. Now, a sort of optimization on the other half of the puzzle of speculative decoding is all about tokens per second. KV cache reuse is all about first token. Now, this is another place where the product decisions that you're making matter a lot, because in order for KV cache to be reused, the prefix has to be identical, not one token different. You can have a prefix that is 100,000 tokens long, and if 99,999 of those tokens are the same, but the first token in those sequences is different, you have a complete cache miss. So you want to always move new tokens as far to the right in your input sequence as you can, to make sure that the sort of theoretical possibility of a cache hit is as high as possible. Now, actually delivering the cache hit, that is the input system's responsibility. That is the infrastructure's responsibility. And a lot of that in today's system comes down to routing as well as KV cache sharing. Because if you think about a system that's running at any reasonable amount of scale, you're going to have more than one replica of each model. And so the hard challenge is bringing each request to whichever replica is going to have the longest prefix match that it can serve to skip prefill for all those tokens and massively accelerate your time to first token. This is going to help with everything. It helps with throughput, helps with latency, helps with cost. I mean, it doesn't really do anything for quality, but it certainly doesn't make it any worse. Now, speaking of quality, everyone's least favorite inference optimization, quantization, has the opportunity to improve both time to first token and tokens per second, making both prefill and decode faster by operating certain parts of each inference step at lower levels of numerical precision. Now, the thing to understand about quantization is it's not an all or nothing type of decision. You can quantize only the linear layers or only certain layers within model weights, or you can get more aggressive and quantize activations, KV cache, even attention if you're feeling real crazy. The thing with quantization is that LLM output, or really all generative AI output, is fairly non-deterministic. And so while you can kind of do intermediate rounding throughout the process of generating a token, you don't always know sort of which bit of rounding is going to be the one that throws off the whole outcome. So in some cases, you see absolutely no impact. In some cases, you see quite a bit of impact. Usually where you see the most impact is due to two reasons. One, you have a distribution within the weights that has a very high dynamic range. So it has both very small values and very large values. And it's hard to encode that difference with lower precision. Or two, because you have relatively few weights or few parameters. And so there's very little information to calibrate against. We find that, with today's large language models, generally, especially weights-only quantization, produces benchmark results that are within the margin of error in either direction. Sometimes your quantized model performs better on a benchmark by half a point or whatever, and that just clearly is noise in the benchmarking system. But the way that we're able to be comfortable doing this is because of a data format called NVFP4, which addresses the first issue. So NVFP4 has dual scale factors. The scale factor is what you multiply the quantized value by to kind of get back to the original range. And by using 2 scale factors instead of 1, at the expense of using slightly more memory, which the Blackwell architecture is designed to counteract, you are able to preserve quite a bit of dynamic range and generally keep really, really strong performance between that and having a very small block size. So each scale factor is only applied to a small number of values. You end up with a system that records basically the same information as the unquantized model, but just in a more efficient manner. And so again, this delivers wins across latency, throughput, cost, everything. You just have to be careful with your benchmarking and your calibration. Finally, parallelism is a place where you get to make some big decisions around latency versus throughput. Generally, most large language models today are going to be mixture of experts models. There are a handful of dense models out there that reach the size where you'd want to parallelize, but for the most part, it's going to be a mixture of experts models. For these models, you have the choice between a couple different types of parallelism. There's tensor parallelism and expert parallelism, including something called wide expert parallelism, which is just EP across your NVL72 instead of across a standard 8x node. And the thing to keep in mind is that with different parallelism strategies, you can either improve latency or throughput and thus cost. We generally find that for most workloads, tensor parallelism is going to be somewhat more of a latency optimization, and expert parallelism is going to be somewhat more of a throughput optimization. But as you kind of profile a given workload, you can test against multiple different configurations and see which blend of it gets you to the point along that efficient frontier that you're looking to hit. And then a newer optimization, something that we've been rolling out in recent weeks and seeing really great results with, is disaggregation. So disaggregation is the idea that, okay, we have prefill, that time per first token, we have decode, the tokens per second afterwards. These are very different workloads with different constraints. There's going to be different optimizations that help one or the other. And so why don't we just put these two things on separate nodes, separate sets of GPUs, and just share the KV cache between the two? Now, obviously, this creates a bunch of orchestration issues. We use NVIDIA Dynamo as the toolkit to protect against this. But what you get out of it is you get quite a bit of efficiency on both prefill and decode, especially on prefill. You get some big steps up there. And we found, for example, on SGLang 5.2 that in our system, we got about a 2x improvement on tokens per second in decode through disaggregating the inference. So this is a really promising technique. The trade-off here is scale, mostly. Like, you get better performance, you get better overall system throughput, but you need to be running at a scale where not only one node makes sense, but having 3 to 5 nodes so that you can do multiple prefill workers per decode worker and operate at that kind of scale. That's what allows you to kind of get these excellent results in production. Now, these are all kind of the standard inference techniques that I've been talking about for a year or more at this point. But what's kind of new and exciting in the field of inference engineering today is training for inference. So we have these two factors coming together. One is that more and more companies are fine-tuning models, they're training custom models, they're investing in the process of creating the model that they want to use. And on the other side, they're getting really good at inference. They're understanding these inference engineering techniques and understanding the impact that inference has on their product. So when these two come together, you get the idea of, well, if we're training a model anyway, and if we know we're going to have to do inference optimization anyway, how can we do something in the training process to make that inference a little bit easier? So, in the sort of traditional approach in the book, for example, inference engineering assumes that the weights are final, but that isn't the whole story. A lot of recent optimizations come from training. So spending some time and compute upfront on training can yield big savings on inference. And I'm going to give you a quick overview of some of the optimizations that we've seen from that. So a big one is quantization-aware training. again, we talked about with quantization that you have the ability to, just directly do post-training quantization of weights into these high precision, highly specific floating point data formats that preserve quite a bit of accuracy. But if you're still seeing loss from that compression process, quantization-aware training allows you to train into that precision natively rather than running the quantization afterwards. And if you do that, which we're increasingly seeing open models come out with quantization-aware training to certain precisions, you eliminate the chance of quality loss from that quantization work while still gaining the benefits of the smaller data format. There's also, like we spoke about with Harvey, KV compaction. We just published, the post-training team at Base 10 published a new paper about STIL, which is a method trained with on-policy data to retain KV information through compaction steps. Obviously, like we discussed with KV-aware routing, the KV cache is very valuable. And if you're able to keep your input sequences the same from step to step, you're able to see a lot of savings on prefill. But holding KV cache is expensive, sharing is expensive, routing is expensive, and sequences can get very long, and occasionally you might even run against the context window limits of the model itself and need to compact the information, which voids the KV cache because you've changed the token order slightly. Doing KV compaction at the model level and doing it in training so that you're able to teach the model how to do this compaction and how to retain information provides some relief against some of these KV cache challenges during inference. And finally, DFlash. We mentioned this during the speculative decoding slide. So DFlash and Eagle 3 are the newest speculation methods. DFlash is a bit newer, and it's overall a higher performing method. So like with Eagle 3, you still need to train a DFlash speculator, and you actually train it to generate an entire sequence in a forward pass from hidden states rather than individual tokens like Eagle 3. So you remove the sort of auto regression bottleneck out of your speculation. So lots more to come, I think, in these training-based inference optimizations. Again, if you're training a model anyway for quality reasons, you probably also want to train in the speed optimizations, the latency optimizations, the throughput and cost optimizations that you're ultimately going to need to do at the inference step anyway. So there's a lot of work that you can do up front by understanding what inference is going to look like in order to set yourself up for success after the training is complete. So thank you for having me Infer Summit, folks, and thanks everyone for listening through. If you'd like to find out more about inference, you can connect on Twitter and LinkedIn, where I'm publishing our inference work as often as I can. And then you can also read Inference Engineering. This is the book that I published about 4 months ago. It's a very good introduction to the field in general, and it is free at this QR code at base10.com/inference engineering. And these paper copies are also available for purchase in more than 20 countries. So thank you so much for your time today. And that's inference for product differentiation.
Thank you, Philip. That was a lot of good stuff there about optimizations, techniques. And this is one of the reasons why the inference area is very fascinating to me. But at the same time, it can be a little bit overwhelming because of all these options that we have, right?
Yeah.
There's a great question that I'm going to bring up, and maybe you can take and answer this.
Yeah, so this is kind of the holy grail of inference optimization, right? Is in the past, we thought about inference optimization very statically. It's like you come up with the appropriate configuration, and then you run it. And the world that we're moving toward is one where rather than automatically deciding up front what optimizations you use, you just run the system against traffic, observe what is happening, and adjust your optimizations. Today, that's still at least semi-manual process of, picking a configuration that you think looks pretty good, deploying it, getting feedback, and then iterating. But a sort of ultimate self-improving input system would sort of automatically A/B test different configurations and iterate and sort of hill climb toward the optimal serving method.
Got it. Okay. Yeah, so thank you for sharing your book, and attendees, if you are interested in this area, definitely grab a free copy of this from Philip. Another great question that we're going to bring up here about what would your recommendation for a book that shaped your thinking as an AI engineer?
That's a great question. I think that I recommend a bunch of great resources in Appendix B. I think that one that does a good job of diving a lot deeper into some of the technical aspects of this optimization work is Chris Fegley's new book. And then, yeah, a lot of what I've learned has come more from blogs and more from just like on the job learning versus out of books. I feel like the space is so new that there's not a lot. Most of the books back here are like Stripe Press books or science fiction, but I like to read very broadly.
Definitely, continuous learning is a part of the job, and because this field is exciting as well as evolving at a pretty high velocity.
Yeah.
Cool, Philip. Again, thank you very much for spending time with us.
Thank you.
We're gonna move on to the next session. Appreciate it.
See ya.
So for the next session, we have Chen Yan from Radix Art, and he's going to share with us SGLang Omni in terms of how to serve multimodal and agentic models. So Chen Yan, all yours.
Okay. Hello. Everyone could see my screen and hear me.
Yep. Yep.
And let me do this. Is my showing the whole screen, or it looks like something weird? Okay. That'd be good. Yeah. Thanks.
Yep. We're good to go.
Yeah, and thanks everyone for coming in. Quite intensive today for a lot of inference and experts and the knowledge. And I want to make my talk rather more intuitive, and we want to share a new trends of model that is happening, and we are planning for new kinds of inference interface for those kind of models. And I'm naming this kind of thing the inference engine for multi-stage generative models. Yeah, and thanks so much for my teammates from MC.org and the SGLang Omni team. And I'm on behalf of like 30 people working on the community. Okay, so to be quick, the contents of today, I want to share 4 things to follow the first principle to design an interface. The first thing, like what kinds of model we are optimizing, what's the computing progress they are using, and given their computing progress, what kinds of computing characteristic does it have? By computing characteristic, I guess you have already familiar with the words like mem intensive or like computing bounded or like kernel function or those kinds of things. But to our end, I think this kind of thing is purely computing characteristic, and new characteristics should have new serving framework to make it quick. And after getting the computing progress and the characteristic bit, what kinds of system do we design to make it quick, adaptable, and easy to use? And the final thing, given the system we have right now, what kind of thing we are working on and where we are headed to. So we can go over. Yeah, and the first topic I like to introduce today is the multi-stage decoding. So I here listed 2 models. You may not hearing their words, but I can give you some context. The first one is like the Qwen 3 Omni, is yet the best, we call it multi-modality generative model so far. So I can give a concrete idea, like you are using Gemini. Say, I tend to using Gemini when I was in a stack house, since a lot of those kinds of menu, I did not know what their means. So I use Gemini and I open Gemini's Omni mode. In the Omni mode, I can turn on Gemini's, I can turn on the camera of my phone, and then I can talk in audio to Gemini. So in this sense, Gemini is getting my video and my audio input, and then Gemini like gets my input and think it inside, and then output with me. First, type the text answer to the screen, and the second, he like he gets audio output. I mean, to pronounce the text output loud to me. So that is Gemini Omni. So as the Qwen 3 Omni. It is like a multimodality model that supports video, audio, text, and of course, picture input, and give us text and additionally audio outputs. Okay, so that is those all we call it Omni models, and the other models we're optimizing on is like those TTS models. So what is TTS? In short, TTS is trying to like following the sounds to produce another sounds. Give a concrete example. You input your sound to TTS model and you give it a text. Then the TTS trying to use your tone and your motion to pronounce the text you given. So TTS model is like purely text to audio model. So those kinds of modalities seems to be new, but underlying those models, they have showing different kinds of inference, or we say like computing progress. We name it like multi-stage computing progress. So the first one, Omni models, is widely saying that Omni models, most of them using the thinker-talker architecture. So what is a thinker-talker? Thinker, you can treat it as a vision language model, but thinker continue to put the input of is hidden dimension and is text token to the talker, and then talker try to pronounce the text thinker given loudly. So that is a thinker talker. One used to think and another used to talk, right? It's purely intuitive. But another one, like the slow AR and fast AR. So this is rather less intuitive. So in a short explanation, slow AR and fast AR is like something that put them together, they can put them together. They give the slow AR is like try to decide what the contents of the audio should be, and fast AR is something that used to modify the contents with some verbal, with some emotion, with some tone. So that is slow AR and fast AR. So compared with traditional language models, what's the difference here? Most of the times, traditional language models, specifically, they have only one autoregressive loop. But here, for the thinker-talker, thinker is autoregressive loop, and talker is another. And the slow AR and fast AR is so far. Yeah, for slow AR is a big autoregressive model, but fast AR is a smaller autoregressive model. In essence, traditional inference techniques we are mostly facilitating those kinds of single autoregressive loop. We have like MTP, we have like continuous batching, and we have like page attention, Redis cache, those kinds of techniques, right? But directly adapting those kinds of techniques for single autoregressive models inference to here shall not work, since right now we have two autoregressive loop, or even more. So that's the problems we are tackling. And in another sense, we can compare it like this. First, as I said, multi-stage models, they have rather than one autoregressive loop that makes it complex. But most of the models, they still have one single stage decoding, or they even do not have decoding, they only have the prefill, like I said. The diffusion models, they are mostly like the prefill. So what kind of thing we are specifically talking about to optimize in our framework? And here I listed several models that they have maybe similar namings, but they have been tackling different frameworks. The first one is like the Mimo Omni and Nimetro Omni. They have the same name like Qwen 3 Omni or Min Omni, but they are tackling a different thing. Mimo Omni and Nimetro Omni, they are like adding a new dimension, audio dimension, to traditional vision language models, and they do not produce audio outputs. So in this means they only have one decoding autoregressive loop. So they are putting in SGLang. And for the Qwen 3 ASR, Mimo ASR, those kinds of great ASR models, even though they are like working on audios, but still they only have one autoregressive loop. So we put it in SGLang. And another thing is like the WAN model, the Quen image model, those diffusion models. Most of the diffusion workload is like denoising, and denoising is nothing related to autoregressive model, but they are like a one-time preview workload. So we put those kinds of one-time preview workloads still in SGLang. And the left parts, all those kinds of models with multiple stage or specifically multiple decoding loops, we put it in SGLang Omni. So the point behind this, as I have said, what matters is not the modality. What's the matter is a actual computing progress. The computing progress. If the computing progress to get one output has to run into several autoregressive loops, then those kind of models should be put in SGLang Omni. But if it's still one decoding loop, then we put it in SGLang. Yeah, SGLang Omni is a specific building up framework of SGLang to utilize SGLang's already established techniques like continuous batching, KV cache reuse, those kinds of things to facilitate the multi-stage model decoding. Okay. Yeah, and after we get the computing progress, in short, multiple autoregressive loops or multiple stages, what kinds of computing characteristic we have? So the first computing characteristic I want to share is like, as we know, traditionally speaking, we think that prefill is a compute bound progress, and we think that decoding is a memory bound progress, right? So take that into Quen 3 Omni. As we said, Quen 3 Omni's thinker is like a large model that dominates most of the prefill workload. So we tend to see that the thinker is computing bounded, and we say that maybe the talker, how about the talker and how about the MTP layers to accelerate the talker? Indeed, the talker and the MTP layers, they are neither computing bounded or memory bounded. Per workload of the talker and MTP is really tiny. So the real cost is actually the latency, the launching time, the kernel fusion, and the synchronization. If we run all of those into one scheduling, if we use one scheduler to manage the schedule problem of the thinker and talker, it is totally damaged, since we see that the thinker is like computing heavy, but the talker is like a latency sensitive one. So our first design principle is we say scheduling decouple. Since there's multiple autoregressive loop, we give different scheduler, and they use different scheduling policy to facilitate the scheduling of each AR loop. For Quen 3 Omni, concretely speaking, we have one scheduler for thinker and another scheduler for the talker. Yeah. And the second thing, we call it like communication layer. So if previously we only have one scheduler, then we do not need to care about like inter-scheduler communication. But right now, different stage has different schedulers. So between those schedulers, we have to design new communication principles. So concretely speaking, thinker and talker are loosely coupled. The talker reads from a buffer from its own space, and talker and MTP are tightly coupled. So each single step, the talker and the MTP layer is concatenated together. So we put the talker and the MTP layers in one schedule. Okay. So in that sense, we design a control plane and the data plane to facilitate the data communication between the thinker and the talker. In short, the control plane using ZMQ to only sending those kinds of communication information like the metadata, like where the data should go to and where the data is from. But the real data is sent from the data plane, maybe most of the time using Nico or using RDMA, those kinds of communication protocols. Yeah. Okay. And after that, as we said, each autoregressive loop has its own KV cache. Yeah, say thinker is one autoregressive loop and talker is another. So autoregressive loops heavily rely on the memory on the KV cache. So we have to build different KV cache memory pools for those two models. So that's introduced the last problems we tackled today is the memory isolation. Yeah, and apart from the thinker talker's KV cache, there's other components like to encode audio into audio token and to decode audio token to realistic audio wave. There's still some neural networks that works in this scenario. So we still have to thinking about their memory requirements. So that's rather makes the memory layout complex, and that's the problems we want to figure out. So far, we have reviewed what kind of model we are optimizing on. Their characteristic is like not only one autoregressive loop. So there's more loops, more scheduler, and more stages. And the computing progress, we define it as someone is memory efficient, someone is computing bounded, someone is memory bounded, but the small components, those kind of small autoregressive loops, they are latency aware, but neither bounded by any of the memory or computing. Okay. And after we get the computing progress and model we are optimizing on, we are starting to building on the optimization. The first we think about is like scheduling, and the second thing we think about is like communication between the scheduler, and the last thing is the memory. Different schedulers should have different memory layouts and how we are tackling this. Yeah. Yeah. I have used half the time. So are there any questions that I should? Yeah. Are there any more questions? Yeah. If not, I can continue. Yeah. I think I will still have like 10 minutes to finish my talk. So, is that okay? Yeah.
Yes.
Okay. Cool. So coming back, the first thing is like we say scheduler decouple. As we said, a text model is encoding is purely by text tokenizer. So it is pretty simple. And right now for audio models and audio vision action models, they have to using neural network to encode audio and to encode video. So we have to put the pre-process and the encoding a separate stage to facilitate it. So in this sense, we put 5 stages for Quinn3 Omni. The first one is the pre-process. It's like wrapping up a batch to process to load the wave to wave files and send it to the following parts. And the encoder, most of the time we encode the image and the audio. Note that image and audio encoder, they are neural networks. Okay. And behind this is like the thinker, is one autoregressive loop, and is use our Omni scheduler to make the scheduling process and manage the KV cache. And also the talker and MTP part, we fuse them together and putting them together to get information from the thinker and run its own autoregressive loop. The talker and MTP autoregressive is a little bit different than traditional language models autoregressive loop, since the talker and MTP input is like a think token and the hidden dimension of thinker, but we can still adapt SGLang's already established KV cache magnets. And the final one is the code to weave, is like the inverse of the encoder. Encoder is like to take audio into audio token, and the code to wave is like get the audio token back to the audio. Yeah, but indeed there are like some words like the codec token or codebook. We may not go so deep into that, but as we say, as we are putting more neural networks running together, we have to using different scheduling policy for each of them. Okay, and another thing is like the communication layer. The concrete example is like as we said. In this figure, we fuse the talker and MTP together. But why we have to do this is like starting from the communication protocol. If we split in this figure, if we split the talker and MTP into 2 stages, we have to build up the actual communication layer between the talker and the MTP. So they can either be using relay with ZMQ or using RDMA, but it still lags a little bit, and we say talker and MTP is in a concrete loop, and MTP layer after its generation should send back what is generated to the talker. So in essence, we tend to fuse the talker and MTP together to make it into only one stage. So this So there no cross schedule overhead happens for the talker and MTP, and note that thinker never need to get the information from the talker. So there's no backward information from the talker to MTP. So we put thinker and talker differently into 2 stage. So right now, the communication is quick from thinker to talker, and there's no need to communication from talker and MTP, and everything is good for our design. Okay. And one last thing is like the memory. Yeah, you can see where there we have a stage configuration, and we can put concrete memory configuration for the models to say what kind of thing you want to make it, like how much is the TP size and which GPU you wanted to use to. Yeah, and that actually helps us to isolate each stage's memory. And another concrete example I want to share is like multimodality is really memory consumption consuming. So take one example. Right now, people use like language models every day, and language models most of the times they're purely text. Yeah, most of the times it's purely text tokenizer, and text tokenizer do not consume any of the memory. But if we are using Omni models to produce the video, input a 1 minute of video to the thinker shall create over 30 gigabytes at peak memory for the encoder if we do not do offloading or streaming or chunking. So that means the encoder is rather complex, and we should put specific place for the memory for the multimodality encoder to withhold to produce multimodality information. So and so far for the audio. Yeah. Yeah, and that's the notes for memory isolation. And so yeah, that's the 3 things I want to talk in concrete. So following the trend, we can take back. So this page shows what kind of model we are optimizing. The shift differently, like there's more autoregressive loop, and we should treat each autoregressive loop and the independent stage, but we're using stage communication to put them together. And the other things like we discussed, given those kinds of models, what characteristic they have and how we should optimize and what should take in mind, and we should optimize that. And after that, we set three interesting points that we design. The first thing is the scheduler, and the second thing is like the schedule, the communication, and the final thing is like the memory, given all those kinds of multimodality information and the schedulers. Okay, and here we show one by one our scheduler and our communication design and our memory isolation strategy. So that's all the information or the context I have today. Yeah, and the final page is we put SGLang Omni's roadmap. So in short, we should definitely embrace more models. As we say right now, the trust fusion or those kinds of interleaf generation model is getting to be more and more trending. So we are heading towards those kind of models. And the other things like we want to support cross-nodes multi-stage pipelines. Is right now all those kinds of we are seeing a trend as this kind of model is getting to be bigger and bigger, as big as those kinds of language models. So we should have cross-node support still. And the other kind of things like the diffusion stage, like supporting diffusion like a stage machine into SGLang Omni. And also the and also we see the reinforcement loop for those kinds of Omni models. Yeah. And the production level serving those kinds of cloud infrastructure things. Yeah, and if you feel interested for those kinds of model and its characteristic, please feel free to join us and scan like the codes here, and you can go to our projects. Yeah, and thanks for the hosting today. And are there any questions for this?
Chen, that was a great talk with lots of interesting technical aspects for supporting this. I have a first question, and then I'll queue up the other questions that the audience have shared here. Have you seen any interesting use cases from SGLang customers for this particular feature?
You mean the project I'm making on?
Yeah.
Okay, I can share is like not from our customers, since I cannot share the customer information, but I can share my personal utilization.
Okay.
I using those kind of techniques when I go to the market and to buy in, especially vegetables. So since most of the times I do not know what those vegetables their name there is, so I use my phone and as I said, I turn on the camera and I chat with it like Kun, could you tell me what's the vegetable it is? I mean, I'm yeah. So that's one interesting thing I'm using. Yeah, it actually works really good. Yeah, especially when I was like buying. Yeah, another thing like I was buying stack since I'm not familiar with the kind of stacks they are. Yeah. I don't know how to differentiate like New York steak or Philly, so I just discuss with the model and this gets the video input and chat with me.
I see. So that's your personal use case there. So let me bring up a question from the audience, okay?
Okay.
So the question is, if we use a VLM that is used to modify prompt before sending things to a diffusion model, then is SGLang Omni good for that use case?
Sorry, I was quite not sure what the question is.
Yeah, I'm not sure about the modified prompt part.
I was thinking about like you were saying about some rumors like how the GPT image 2 is being made, like they have one model first to modify the prompt and then send the prompt to the diffusion model. That may be possible, and it's also some kinds of we can also say this is some kinds of multi-stage models, but we do not. But right now there's no open source model that actually do this. And from my perspective, I understand that there's a lot of the those kinds of something like the filmmaking companies, they are using diffusion models to generate short films, and they have a bunch of people working on prompt enrichment. They write prompts like 1,000 times more complex than us. So
I see.
Yeah, to make it like fine-grain control the screen. Yeah.
Okay. All right. The next one is very interesting, so I'm going to bring it up, and we'd love to get your thought on this. Essentially, because of your experience, which unsolved inference bottleneck do you think is valuable enough to become the next billion-dollar AI infrastructure company?
Thanks. If I have that question, I gotta make that company myself. Okay.
Exactly.
Yeah.
But what's your thought?
Sorry to say that of course I do not have a really confident question. Yeah, but I have some possible solutions to the question. Like the first one, as I said, is the multimodality. I guess a lot of people has been watching Thinking Machines blog. I mean the new model, the interactive model. I think that is one thing really interesting. And as I said, there's a lot of the model usage happens apart from coding. Not everyone codes, right? I mean, across the United States, I do not believe there are like 1% of the whole population codes, but at least everyone go to the market and to buy vegetables. So I think why I love those kinds of interactive models. The interactive models. Yeah, and that's one thing for the interactive or those kind of multimodality things. And also another thing I want to say is like there's a lot of company called the R&D companies. Am I right? Like the auto research companies. The final points for machine learning research, as I said, is like if we can make machine learning research automated by themselves, then humans are finished. So yeah, I think that could be a great thing to working on. And this year I have seen a lot of people, as I'm a reviewer for machine learning conference like NeurIPS or Academia ML, right?
Self-improving.
Yeah, there's a lot of papers there, and they are demonstrating they are making self-improving agents, not self-improving researcher. But so far, I do not think they are great. Okay.
Got it. All right, so let's take 30 seconds for you to answer this question, and I think you will like this one. That was a great talk. Could you give some insights into how one can participate and contribute to SGLang?
1 year before, I may say welcome anyone, but right now I feel really hard to say. So the first thing, like coding. I mean the cost of coding is really cheap. You can always using coding agents and maybe wrapping up tens of thousands of PRs and sending to SGLang community. But that's not the good thing. So I think the first thing, I think there's only one thing keep in mind to contribute to any open source project. That is responsibility. Anyone should feel responsible for their PR. That this PR should, this PR should be responsible. But some ways, like first, you should know what this PR is making out, and the second, if this PR introduce some failure, you should solve it rather than say, "Oh, AI made this. It's not my business." No, you are submitting the PR and you are the owner of that PR, and and the credit goes to you. So my answer to this question is like, first, as long as you are responsible and has a long minds of contribution, reading the code base is really something easy. And right now we have coding agents, and it can help you codes and reads 100 times faster. And after that, after you get the basic dialogue of what the project is heading on, then it's your time to start building. And as we say, SGLang is massive projects. Possibly there's over 100 people working on SGLang. So you do not need to know all the people what they are working on to start building. You can start building something tiny and then when we're getting to the core, right?
Yeah. Okay. All right. With that, Chen Yan, thank you so much for spending time with us this afternoon. Appreciate it.
Yeah, thanks. And
all right.
Yeah, thanks so much.
Thank you. All right. For the next presentation, we have Emilio, who is a co-founder and CEO of Wafer. And his presentation which is one I'm really interested in. It's state-of-the-art LM inference on AMD. We'd love to see how to help AMD to be successful. So with that, Emilio, it's all yours.
Thank you. Awesome. I'm excited. So just to make sure this is how okay, perfect. Got it all under control now. Okay, awesome. So I'm going to quickly, like 1 minute, going to give background on our company. So we run very high performance LLM inference. We build the software from the actual like intrinsics of the GPU. So if you're on NVIDIA, that would be like PTX. And we build up custom inference engines. We use existing inference engines and to optimize them and make them run as efficiently as possible. We focus on AMD because there's so much to do there, and there's so much value to extract from making this hardware better. There's so much compute scarcity in the world, and people are starting to use AMD now, but we've been experimenting and optimizing AMD for about a year now. When the company started, this was our kind of like the first thing that we were doing, and we've learned a lot along the way. And I'm excited to share some of that. And specifically what I'm going to share is specific examples where our engineering team has grabbed the out-of-the-box software that comes with AMD and instead rewrites and optimizes, mostly using coding agents, to make the hardware run as efficiently as possible. And it's very surprising how far you can push it. I guess it's not surprising from the hardware sense, because if you compare the hardware statistics of like an MI355X to a B200, let's say, you'll see that in terms of like petaflops for, let's say, FP4, which is what most inference runs on, MI355 has 10 petaflops of FP4, while NVIDIA B200 has 9 petaflops. And I think this is a bit higher for Ultra, for like B300s. But generally, it's very comparable hardware statistics. That's enough of me saying all that. That's kind of like the background on us. Let me talk a bit more about the technical stuff. So yeah, that's me. We don't need to focus too much on that. Okay, so the first thing is what I was talking a bit about before, which is like AMD inference, running AMD inference well is actually a software problem. As I said, the P-flops are comparable. You can, in theory, if you have the same, like in a path of FP4, if you have the same or more number of P-flops that you can support compared to what NVIDIA has, in theory, you should be able to run inference at, let's say, equal throughput, just to normalize on a number. So in terms of HBM, the capacity and the bandwidth is already there. What's missing are sort of like everything after that, which is, okay, can you have a really good runtime so that you can actually run these operations performantly? Can you have these kernels that actually define how you can run code on a GPU as efficiently as possible? And then this all trickles down into your tokens and call it TCO per token, call it TCO is total cost of ownership of a GPU. You can call it perf per token. There's so many terms that people use. Generally, we'll define some terms that will be useful for the conversation. So the general, again, I've already kind of like, I'll go quickly over this one because I've already kind of talked about this, but the stock paths of today, if you just get VLLM running on an MI355. An MI355 is the latest AMD generation available today. It's comparable to a B200. If you just get the path running today, it really gets you, in general, it gets you much worse performance per token, call it, or TCO per token than NVIDIA. So there's a lot of work that you need to do on the software stack to actually to have this not be the case, so that you can actually run AMD at equal or better TCO than what NVIDIA can provide. So there's three things here. The first one is the generality tax. And this also applies for NVIDIA, which is the kernels that come out of the box for most LLMs are actually pretty general. And there's stuff like page detention, there's stuff that has solved this, but in general, there's a lot of room to improve on just tuning the kernels and writing the kernels that are specific to the dimensions that you care about. The second one is there's a lot of overhead from small operations that are not fused or using parts of memory that you shouldn't be going all the way to. Like sometimes you can go to cache instead of going to call it like HBM, right? So there's a ton of things that you can do on kernel fusion and generally just improving your memory layout. And the third one is when a model gets launched on AMD, normally it doesn't have the same support that NVIDIA has. So you'll see stuff like maybe call it like SGLang 5.2, or which is a model that recently came out. SGLang 5.2 was immediately supported on Blackwell GPUs, but there was a lot of work that we needed to do, or that the VLLM team did in this case, and the SGLang team too, to actually support the model as fast as they could. But there's still a lag between how fast NVIDIA supports models and how fast AMD supports models, even though AMD is the close like second contender to like day zero support. Because if you analyze all the other chips, the like tail of like Google TPUs, AWS Trainium, they require like months of work. Even like Cerebras, think of Cerebras. Their latest GLM is 4.7, and there's a reason for that. It's really hard for them to support new types of attention, changing from dense to sparse attention, which GLM did with the new GLM 5.2. It's kind of like a tangent, so I won't focus too much on that, but it's still an interesting topic of like how fast can you bring a model to a chip so that you can use it in production. So that you can use it in production. So our solution at Wafer is, what if we just build a completely custom AMD inference layer? And completely custom is kind of fake here. And what I mean by that is we use existing inference engines, we use existing runtimes and sort of fork them to create like better things and support for a broader range of things that we care about. So AMD has an inference engine, which is kind of like the equivalent of, for the people that know NVIDIA's TRT-LLM, but it's called Atom. And Atom is a very new project, but we think it sets a pretty good foundation for what an inference engine on AMD should be. So instead of rebuilding what the Atom team is doing, we fork our own version of Atom and we add stuff on top. So some of the stuff that we add on top is goes all the way from kernels. We write HIP kernels. HIP is the equivalent of CUDA in AMD hardware. So we write HIP kernels to support operations that are not natively supported sometimes to increase the speed. Aider here, mentioned over here, is the equivalent of HIP. Aider is the equivalent of, maybe a good equivalent here would be like Qtile or more like QDNN. It's like abstractions that give you easier ways to define like common operations in kernels that are used for LLMs, for MOE, etc. And then ROCm is like the runtime. So it would also, like the analogy in the NVIDIA world would also be CUDA, but CUDA is both used as a language definition and as a runtime definition. So the thing you can do on top, once you like write very custom kernels, the thing you do on top is model-specific decode paths. What this means is like a spec decode path. What this means is basically training a small model to predict the outputs of the big model. It's a common technique used now in basically every frontier LLM, where you have the small model do maybe, let's say, 3 token prediction, and then the big model will just verify the tokens that are that would be the ones that it would have predicted. The reason this is much faster is because verification for an LLM is much cheaper than generation. So this works very well and has been, I'd say this is like a solid 30 to 40% of like the lever you have to pull when optimizing models to like their full potential at the moment. Then the layer on top of that is basically the runtime and cache. I think, as we all know, like context lengths and sort of these like long agent trajectories have become basically the normal thing to when you're running agents. Like most people I talk to are running like these coding agents. They're running this like ChatGPT on like this chat that's like 15 or even more, like 25, 50 like prompts in. And so you have this huge context and you have this huge pre-fill that you need to fill. And you get to think about like, okay, what are the semantics? What are the strategies that I could use to cache this most efficiently so that I don't have to actually re-input the entire prompt every time a user adds something else. So the concept of like, similar to the concept of a KV cache, where you don't have to go redo the entire key value cache when you're like actually doing the decode in LLM attention. There's also things like prefix caching and other strategies that great projects like VLLM and SGLang do, so that you don't have to re-input your prompt every time you are actually adding stuff on top. And there's a lot of interesting engineering that comes from our team and from many teams around the world on how do you actually optimize the cache to be as efficient and maximally useful as possible. And then on the last layer of that, there's the serving APIs and the load balancing. And this, I would say, is interesting, and it's getting more interesting as more sort of like as you scale, basically. There's like a lot you can do in terms of load balancing. Obviously, it gets very interesting when you have a runtime scheduler like Dynamo or Mooncake, where you can actually do prefill disag and have different GPUs do prefill and have different GPUs do decode. And it gets interesting on what type of load balancing you can do, because you can start independently scaling both the GPUs that do prefill and the GPUs that do decode. Whereas before, when you didn't have those separated, you'd have to scale those uniformly. So there is something more interesting here on serving APIs and load balancing in general. But I will say Wafer, for the time being, mostly focuses on the bottom 4 of this stack. And serving API and load balancing are something that we use because we have to have a serving API to serve our tokens. But it's not a massive sort of like focus for us. So now that I've talked about like the general solution here, I want to talk about some like specific optimizations that we've done on models and what exactly we did to achieve what are the like highest speeds on AMD that have been publicly achieved for these models. So for reference, we were the first company in the world to get AMD to #1 on any artificial analysis leaderboard. And this was a great technical achievement by the team, and it took us months of effort to do. But once we did it, we're sort of like trying to increase the speed of the flywheel so that we can keep doing this for AMD hardware, and we can keep increasing the TCO to give people another choice. Our general thesis is like people should not be locked into CUDA just because they were so early to the game, especially with how important AI infrastructure is becoming. So let me talk about this first example. There's actually, this is kind of like an overview, and I think I'll skip this because it's more interesting to actually, I won't skip this entirely. I'll just go over it fast, but it's more interesting to actually look at the specific examples and what the exact technical achievements were. But generally, what you could see is that there's 3 levers, or I'll actually talk about the first 2 levers, which are very interesting. The first lever is, can you sweep over the search space of possible configurations in VLLM and SGLang and Atom and TRT-LLM to find, if it was NVIDIA, but on AMD, to find the most optimal configuration? I imagine a lot of you guys have used something like VLLM. And when using this inference engine, you've probably noticed that there's a ton of hyperparameters and flags that you can set. I don't know if you've ever used it on AMD. I assume very few people, compared to the amount of people here that have used VLLM, I assume a very small minority of those people have used it VLLM on AMD or SGLang on AMD. But what you'll see is that to get actual performance, there's like 10x the number of flags that you need to like permute, and finding the best combination of those is a huge permutation problem. So we have a lot of techniques for being really efficient in our search and being really efficient in the way we sort of go over this problem and find the configs that are most optimal. And then once we go to the bottom of that for the kernels, there's there's a lot that we can do in kernels, and we'll talk about it. But generally, I think these numbers are like not super meaningful because you haven't seen the actual optimization that we do. So I want to just skip over this. I was just talking in general about the strategies that we can do, but now I want to go to the actual like examples. Okay, great. So this is one of our first examples with Atom. So we got Qwen 3.6 to state of the art, and for the graph that you see here, I didn't include the providers, but it's the common providers like Alibaba Cloud, like Base 10, like Fireworks. I don't know who exactly is on the leaderboard right now, but at the time, we took a recording of like what the leaderboard looked like, and we recorded it while blanking out the name of the other providers. But we were able to take the speed of Qwen 3.6 to state of the art by basically doing purely runtime configuration. And this might seem like low-hanging fruit, and in some way it is, but also in another important way, there's so much that you can do by searching this permutation space efficiently. If we had just searched this permutation space naively of like, what are the flags that we need to set in Atom to get this to state of the art, it had taken us like, let's say some absurd number, right? Like, it had taken us like a year or like 10 years to go through like the full like spectrum of choices. But if you build systems that can efficiently use basically AI, ML in some ways to prune specific parts of the search tree and do this sort of targeted optimization or targeted search where you're going over certain configs that make sense, and you can do this very well, and you can do this very well with agents. You can have an agent that benchmarks across the search space and checks if, okay, will this flag make it more efficient? And if I do make it more efficient, what does it mean if I add this other flag in this path? And this is the process that humans would run. But agents are getting so good at autonomous sort of like long horizon tasks and performance engineering that this is actually something that that we're using like every single time a customer comes to us with an inference request. We will run an agent through you to get the absolute max performance we can out of your hardware. And this is something that usually traditional inference providers are not as good at as because they're bottlenecked by humans. So this is kind of like one of our core thesis of like, can you use agents to search the space and get to that optimal configuration performance without even having to get into kernel work, which is, it could be very high ROI, but it's also a big sort of like input and much heavier work that takes longer. The second example that I think is probably my favorite by far is when we actually got down to the kernels. So again, in this one, we did include the providers, so it's kind of ironic, but this one was our first result ever where we got #1 on artificial analysis. And this is the one I was mentioning to you guys before, where this was the first time, at least publicly announced, the first time that someone using AMD managed to get a frontier LLM to #1 on artificial analysis in terms of speed. And the way we did this was with this optimization path that I've laid out here. The first one was the config sweep that I talked about, which is basically, can you load in the FP4 weights? Do the kernels exist? If not, you have to write them, but do the kernels exist? Can you quantize the KV cache without losing accuracy? And can you add support for MTP, which is a form of similar to speculative decoding, where you have multiple heads of the model predict different outputs, and then at the end you do verification to decode more efficiently. Then what took us from 260 to 300 was actually writing custom MOE kernels. We did a fusion that fused 6 launches into one, so that there was no intermediate HBM that we had to go all the way to, which managed to speed up the tokens per second from 260 to 300. And then for the last optimization to really get in front of the other providers like Eigen, Nebius, DigitalOcean together, what we did was router fusion plus MOE, so more kernels. And I'll talk more about each one. So one interesting one here is MOE surgery. So MOE is mixture of experts. So what we were thinking about is, how do we remove the empty work? Basically, there's this routing that you do over 512 experts, but generally the mismatch is that these 512 experts give you only about 40 active expert token pairs. What that means is that you can replace you can replace these separate operations. So you can write one HIP kernel that instead of doing input-output for all of these things and going all the way to HBM, you can fuse all these operations, which are gem, CELU, down gem, reduce, and dequant, into one single fusion, one single big kernel that instead does everything and then returns the result. So instead of going input-output, input-output, you can just do input, do every single operation on the GPU, and then output the result. And this was one that was very high ROI optimization. As you can see here, 1.84 faster per mixture of expert call. And this added about 30 to 40 tokens per second end to end. The second one here was another one of the fusions we talked about, where we did the router plus a shared expert. Now, what this meant before is that we used to dispatch the router so that we had the separation between the logits and the shared expert gate up. And these were two separate gems. And you can see this illustration here where we're hitting the before as you have the hidden states as one gem here times the W router. And then on the other side, you have the hidden states times shared. So these are two different matmults, which are gems, just generalized matrix multiply. After we did that, we concatenate the weights along N so that we were able to merge this into one single fused gem that actually ended up producing the same exact result. So this was one of like a very creative optimization by one of our engineers that we were very excited about. And to be clear, this only sped up like 10 to 20 tokens per second. But we like to think of performance as just like, there are a lot of like performance matters more and more as AI infrastructure becomes bigger and just like permeates every aspect of basically the world, where a 10 to 20 tokens per second increase can mean millions of dollars of saving for a large enterprise because you can run stuff faster, you can finish stuff faster in the GPU. So faster equals cheaper in the GPU world too, because most of the time you're renting or you're buying depreciating hardware that you could be using for something else. The last one I'll talk about is caching the state the model uses. And this one's a really sort of like simple one compared to the other ones, which might be a bit more daunting. This one is simply a model like Qwen 3.5 has these full attention layers. And that recurrent hidden state, the recurrent state of the GDN, lives outside the page attention, like the KV cache. So the fix is to build this other cache that's a snapshot of the recurring state. And you also save the KV blocks. And what you'll do is you'll mix both of them and you'll invalidate them together on cache hits and evictions. So you can keep these states aligned on your cache so you can have this speed up. Look at these massive speed ups. And this is just a cache trick, right? So this was also something that we did that helped a ton on just thinking about how do you actually save specific parts of memory so that you don't have to go to the expensive memory like HBM and you can instead hit the most cache as possible. I'll finish up with this and then I'll open up to questions. I don't know if I left a lot of time for questions, but like I'll try to go faster for this one. What we care about at Wafer is, can we close a loop? Can we close the loop between what the agent can do and what the human input it needs so that you can just run these autonomous loops that agents can just search the space for optimizations. The space could be implementing a custom kernel, quantizing specific parts of the model without losing accuracy, training speculative decoding models, smaller models that predict what the big model will output. It could be all the way down to like, if you make this really futuristic and like years down the line, it could be all the way to like, what's the cooling in your data center? What's the power efficiency that you're using from the grid? You could even take it all the way down to like, okay, how should I actually design my chip if I want the maximum performance in this workflow? So I think there's a lot of interesting things to think about in where this model could go of like, what if you could just give an agent a closed loop system where it can search, where it can identify bottlenecks with validity, it can write the kernels, it can write the code to patch it, and then repeat and benchmark that it's actually faster, benchmark that it's numerically correct, and then just go on repeat. And I think this is a very, very powerful thing that even to this day, people are underestimating how powerful this would be. And sort of like if you take the exponential and the scale. So takeaways here, just to finish off, the mode is moving up the stack. There's so much to do in terms of alternative hardware that we want to add compute capacity to the world, and this is a viable way of doing so. MI355 from AMD can be frontier class with the right engineering. day zero support is still NVIDIA monopoly, still NVIDIA active, but there's something we now have a path to reduce this and to actually make other hardware day zero support native. Custom kernels still represent a big part of the moat of serving inference efficiently. And then agents are a great way to scale this so that you can do this for every model, for every hardware, and in the future have an actual democratized market where we don't have a company that is just 90% of the market like NVIDIA. They make a great chip and we highly respect their engineering, but I just think the world deserves kind of like a choice and like, what chip should I use? And that choice means the world for prices to come down. And eventually what we care about is how do we maximize what we call intelligence per watt? And our focus is building AI that can optimize AI infrastructure. And we think the best opportunity today is with AMD Inference. So yeah, I don't know if I have time, but I'll open it up to questions.
Thank you for a great presentation. Lots of interesting optimization, hardcore engineering that you guys are working on. So kudos to you guys.
Thank you.
Looks like the questions are coming in, but I'm going to start with my question.
Yeah.
The closed loop optimization that you talk about, sounds pretty exciting. Have you thought about even like make that available for both NVIDIA and non-NVIDIA chips?
Yeah. I mean, to be completely frank, we use a lot of NVIDIA chips still, and we do use these closed loop optimization. I think the reason I'm so excited about AMD is I think there's a lot to do with AMD and NVIDIA already. Like if you think about NVIDIA, I think the estimate is like they have like 4,000 CUDA engineers already. So it's like AMD has like a tenth of that. So it's like 400 ROCm engineers. So it's kind of like the arbitrage and the opportunity that exists in AMD is much higher. So it's much more interesting for us to think about like how much we can help there in terms of like where the delta is, because the gap from AMD is purely software. As I said, the petaflops is the same. It supports the same. So we do work for both. I think the more exciting thing to think about though is like what happens in a world where you can actually do this for any chip and make it equally performant as NVIDIA.
Gotcha. Makes sense. Yeah, certainly it's good to have healthy competition. That will be good for everyone, right?
Yeah, exactly.
I'm all for that. There's a question from the audience, so let me bring that up and then you can take it. Okay. Do you train your own draft models and what method you are using?
Yeah, we do. We do a lot of Eagle. We also do a lot of like normal MTP. But yeah, we generally like, I think there's a big part of what I talked about is day zero support. And I think if you don't want to train your own draft models, you should also be okay with waiting like many days or even weeks for like the community to bring one up. Sometimes NVIDIA, AMD, other companies like Snowflake, Red Hat will open source like a draft model and you can just plug that in. But for our customers, we've seen that they really, really care about day zero support. Like, hey, this model just came out. Like when GLM 5.2 came out, our Slack was just like flooded with people being like, oh my God, I'm seeing on Twitter that this is like the best open source model. Can we host it today? And it wasn't supported on AMD and nobody had released a draft model. So it was kind of like on us to figure out like, okay, we need to go train our own draft model, figure out how to actually like do this so that our customers can use it. So yeah, we do train them. It's pretty fun. It's a pretty interesting challenge overall.
Yeah, I bet. Awesome. Thanks a lot for giving us your time. I'm sure you're busy, have a lot of stuff to do. Appreciate you taking time out and share with us all the interesting stuff that's happening at Wafer.
Yeah, thank you so much. It was great.
All right. Okay. For the next presentation, we have a few engineers from Pinterest. They've been busy building Pinterest VLM serving stack using NVIDIA Dynamo. We have Selena and Christian. And with that, I'm going to hand it over to both of them.
Great. Thanks so much, Hyun. Yeah, welcome everyone, and thanks for attending our talk. We are here on behalf of Pinterest, and today we're going to be talking about building Pinterest's VLM serving stack using NVIDIA Dynamo. So this is a quick overview of our agenda for today. We're going to do quick introductions, and then I'm going to talk about VLMs at Pinterest, why we have them, why they're important, how we use Dynamo to serve our VLMs. And then Christian is going to talk about benchmarking with AI perf, what kind of product use cases are enabled, what we have planned for the future, and then a quick wrap up. So first things first, for introductions, my name is Selena. I'm a software engineer at Pinterest, and I work on the machine learning serving team under the AI platform org. And I am focused on building out our generative AI serving infrastructure. Later, you're going to be hearing from Christian, who is on the same team as me and also working on building out the Gen AI serving infrastructure. So a little bit about visual language models, or VLMs, at Pinterest. So as hopefully most of you know, Pinterest is a visual discovery platform. This means that we require AI systems that reason over both language and visual content. So VLMs are foundational for our next generation product experiences. And these products include Pinterest Assistant, hybrid search, multimodal ranking, signal generation, and content safety. Part of our model strategy is to customize open source models to align with product and scale needs. For example, we optimize Qwen 3 VL model for the Pinterest Assistant product. This requires low latency VLM inference over rich multimodal context and reworking open source VLMs with proprietary multimodal embeddings to cut runtime costs while improving performance. So there's a lot of unique serving challenges for serving VLMs compared to text-only LLM workloads. VLM requests can carry multiple or many images, require extra vision encoder computation, incur larger and more variable prefill costs, and create higher KV cache pressure. I'm going to walk through each of these serving challenges a little bit more in detail. So we have complex payloads and pre-processing. So VLM requests can include text and images. So images can be URLs or base64. This requires image loading, pre-processing, and complex prompt building. And the complexity of this scales with the number of images. We have expensive prefills. So encoding visual context is pretty costly. So these workloads are very prefill dominant and generate much larger and irregular KV caches compared to text-only models. We have multi-turn workloads. So we need to combine long dialogue history with repeated or evolving visual context, which drastically increases prefill load and complicates state management. All of this kind of leads to KV cache memory pressure. So large visual contexts create much bigger KV states per request. And this necessitates multi-tier cache offloading and KV-aware routing. Finally, at Pinterest, we have a lot of custom requirements for our products and workloads. So our VLMs require model-specific support for image fields, projector layers, and custom routing, which is a little bit different than standard text-only APIs. Next, I'm going to talk about how we use NVIDIA Dynamo at Pinterest and why we use NVIDIA Dynamo at Pinterest. So Dynamo provides for us a distributed inference orchestration layer that gives us the flexibility to optimize multimodal workloads across the full serving path. And this includes support for things such as disaggregated encoder prefill decode serving, multimodal support in the Dynamo front end, multimodal KV-aware routing with custom payloads, and KV cache offloading. So to kind of step through these benefits a little bit more, first of all, Dynamo is Kubernetes native, which fits in well with the internal Pinterest infrastructure. It's framework agnostic, meaning that it supports many different inference engines, and we have the flexibility to choose which one to use under the hood. And this is really crucial for us because we believe there's no one-size-fits-all solution. Performance and requirements can be different depending on the use case. So we're able to use the most efficient one depending on the use case, model characteristics, etc. We also leverage Dynamo to do disaggregated serving easily, which helps us tailor workload components for specific SLAs. I'll go over this more in detail later in the talk. Dynamo Planner is another feature that helps us do auto-scaling based on SLA. And this is a lot more flexible and performant than traditional CPU and memory-based auto-scaling. We also leverage in Dynamo KV cache-aware routing. This is kind of a must for large-scale multi-worker scenarios. And we actually also collaborated really closely with the NVIDIA Dynamo team to build out multimodal support in the KV router. We also rely on Nixle to accelerate and optimize network communication. And we also use KV cache offloading features, and in particular LM cache, which is supported by Dynamo. And this allows us to handle multi-turn high QPS scenarios and manage memory pressure for long context workloads. So kind of at a high level, these are some of the main components of our solution. Our infrastructure is centered around NVIDIA Dynamo as the serving orchestration layer, which helps us address a lot of the VLM serving challenges that I mentioned earlier. And just to go back in a little bit more detail, this is kind of what our architecture looks like. So we have Envoy-based traffic routing. We use WAN-B for our model registry. We are able to fit this in with the Pinterest infrastructure ecosystem. So we use an internal deployment infrastructure called PinDeploy. We use the Pinterest-specific internal EKS infrastructure for Kubernetes. And for our hardware, we use NVIDIA GPUs, including more recently Blackwell architecture. And of course, our workloads are Dynamo deployments that are deployed onto our EKS clusters. So this gives us a smooth client experience, simple SLAs, and lower cost per token, along with freedom and flexibility to evolve our models. So I'm going to talk a little bit more in detail about how exactly we support VLMs with Dynamo and the specific benefits that some of the features give us. So I mentioned earlier EPD disaggregated serving. So this basically allows us to break up the distinct computational phases of the LLM requests and scale each phase independently. So this is really important for hardware allocation and scaling multimodal workloads, and it helps us relieve hardware pressure from image encoding specifically. So we're able to independently scale workers based on vision workload, reduce the GPU memory pressure on prefill and decode workers, and relieve worker bottlenecks. And this is particularly crucial when specific GPU families are in short supply. I'm sure most of you have had to deal with this in your day-to-day. GPUs are hard to come by, so this is really important for us. Next, we have KV cache offloading. So specifically, we use LM cache, which is supported by Dynamo. So LM cache basically supports multi-tier cache offloading, which means that it moves KV cache data from GPU memory to CPU and disk, which is really important for high QPS and multi-turn scenarios. This tiered storage across GPU, CPU, and local disk also preserves generation latency. And some optimization features include async prefetch and compression to improve the throughput and reduce TTFT for long context workloads. This also helps with resource management because it prevents visual tokens from overwhelming our VRAM, which also fits very well into Dynamo's integration options. Of course, we really wanted to use Dynamo because of its multimodal support. We actually worked really closely with the NVIDIA Dynamo team to share our use cases and workloads to help develop a lot of the multimodality features that are now present across its stack. And they have helped us greatly in meeting Pinterest's multimodal serving requirements. So multimodal disaggregated serving helps optimize the vision encoding step. The front-end image decoder handles complex multimodal payloads and performs image preprocessing directly in the Dynamo front end. And the KV router is multimodal compatible, and it tracks prefix cache overlap for visual content, which helps reduce recomputation for VLMs. Next, I will hand it over to Christian, who's going to talk about custom modality support.
Yeah, so I'm going to be talking about how we support a custom modality, projection embeddings, as an input to our visual language models. So as Selena mentioned, at Pinterest, use cases are often image heavy. So it was important for us that we could support sending large image context efficiently. But we found that sending raw images was expensive and unscalable. So our solution was to create this new modality path. For starters, projection embeddings are embeddings that represent image content in this case, and are pre-computed using an internal Pinterest encoder model. So now during serving, a user can send these embeddings, which would then be projected into visual tokens using an internally trained projection model, allowing us to skip the expensive encoder step in VLMs. So what this required was creating a new chat completions request format, a new artifact format for packaging the projector, along with the VLM weights, and actually implementing this code path instead of the engine, which is currently VLM, as well as in the serving platform Dynamo to support things like KV-aware or multimodal KV-aware routing. Yes, next slide, please. Okay, so the results were extremely strong. On average, compared to just sending images, we saw 85 times faster TTFT, 7.3 times faster end-to-end latency, and 1.1 times faster time per output token. But the peak improvements we saw were 369 times faster TTFT, 44 times faster end-to-end latency, and 2.6 times faster time per output token. So overall, this enables much larger visual context windows. For example, at the same latency as sending 10 images, we can now send 250 images as embeddings. So 25 times more visual context without a change in latency. So here are some more of our benchmarking results. But I won't go over any of those anymore since I already covered the highlights. So that leads me into our next topic, which is benchmarking with AI-Perf. So AI-Perf is an OSS benchmarking tool by NVIDIA. It's highly configurable and flexible enough to cover our range of use cases. For example, one of our main use cases is an agentic use case, which can be represented loosely as a DAG. And through collaboration with the NVIDIA team, we were able to unlock DAG benchmarking support using AI-Perf, leading to a much better representation of our use cases compared to a traditional multi-turn or single-turn benchmark, for example. Additionally, the tool is flexible enough to allow for benchmarking on our own modalities like projection embeddings, even though they are not supported in the default chat completion schema. And we use the results from AI-Perf to create our own custom dashboards, which make results persistent and also make the analysis a little bit simpler. So we use weights and biases for a single benchmark report, Superset as a comparative dashboard across all of our runs, and LangFuse for logging the input and output of each request during a benchmark run. So on the left section, or on the left is a section of our 1DB report, and on the right is our Superset dashboard. You can see like the model leaderboard, and also some other dashboards that we use to compare these different benchmark runs. So next I'll be talking about some of our product use cases we support at Pinterest. The first and the main use case is Pinterest Assistant, which is a client-facing real-time agentic collaborator in the Pinterest app. The main features of this use case from a serving perspective are that it is real time. There's a large amount of visual context being input, up to 1,000 images in a single request. It is one of the multi-turn agentic use cases that I already mentioned, and it is backed by a fine-tuned OSS model, of course. So another use case is signal generation. So both of our main signal generation use cases are multimodal and single turn. The search tree ranker use case generates signal by taking candidate search results, sending them to a VLM, and then basing the ranking of the candidate on the log probabilities output by the model. The pin OCR use case is a non-VLM model and returns text and layout regions in a given pin or image. The notifications use case is, of course, responsible for generating notifications. It's currently text only, it's single turn, and has a large serving footprint of around 300 GPUs, which have made some of the Dynamo features like KV-aware routing pretty important. Lastly are the use cases around safety. So these use cases are single turn and once again multimodal, which you can see is an obvious trend at Pinterest. The report auto-ignore use case is used to determine if user reports can be ignored, and the unified safety use case is a use case used across a variety of VLM use cases for safety classification. And it has to be real time because it's used as a gating mechanism for other real time use cases like Pinterest Assistant. So what's next? AI Configurator is one of our next main focuses. It's a deployment optimization tool used to identify the best serving config given a model, hardware, latency, or some other SLA. And it will sweep a variety of these different variables involved in serving settings like TP, DP, draft token count, even the engine type like VLM, SGLang, or TensorRT, the prefo count, etc. And it predicts the performance of each of these different combinations. And we also plan on using this tool for cost estimation, which we have also found is an important gap to fill for organization planning. Another area of focus is using Dynamo Planner, which is an auto-scaling planner for Dynamo. It will dynamically scale deployments based on traffic latency and capacity targets, and supports a variety of optimization targets like throughput, latency, or other SLA. Yeah, so to conclude, Pinterest depends heavily on VLMs, which have a unique serving challenges. NVIDIA Dynamo provides a strong foundation for our VLM serving stack and powers our emerging multimodal use cases. And to evaluate real-world multimodal scenarios, we built a custom benchmark tool using AI Perf. And thank you to all of our coworkers at Pinterest, as well as on the NVIDIA Dynamo team. They've been super responsive and always willing to implement features that we suggest. So special thanks to them. Any questions?
Okay. There we go. All right. Thank you, Selena and Christian. We have a few questions from the audience, so I'm going to bring it up for you to see here. How do you handle online evaluation when building VLM agent? Is there any difference from building it for agent that uses pure text?
So if the question, I guess, is like based on the quality evaluation, I don't think we have much context into that since there's kind of a separation of priorities. So since we're on like the AI serving platform, we don't really do much about quality evaluations, if that's what the question's asking.
The online evaluation, I guess the differences between, text versus VLM agent, is there anything that you would do differently, I guess? I think that's the gist of the question.
Like, is it in terms of, I think what Christian is saying is there's evaluation of the quality, like result quality, but also of benchmarking. So, also to echo what Christian said, most of the quality evaluation is done by our clients. They have specific tooling to do that. Christian, do you want to talk about like how you handle evaluating like specific like VLM performance in your benchmarking tools?
Yeah, I think that's a great point. Yeah.
Yeah. So if we're talking about in terms of performance, how we evaluate that, like I mentioned, most of our evaluation is done using AI Perf, and we try as best as we can to model the actual client use case. So like I said, for Pinterest Assistant, since it was a agentic use case, it was a bit difficult to model that with a traditional multimodal benchmark, which initially AI Perf only supported a multi-turn and single turn. But with collaboration with them, we were able to also have support for DAG. So now we can kind of represent these agentic use cases as a DAG. It's a bit of a loose representation, but still is a lot more representative of the use case compared to like a multi-turn use case. So hopefully
Got you. Yeah. Yeah, I guess the questions depend on what type of evaluation that is. If you're doing end to end, then it's kind of fairly independent of whether that's text or VLM kind of thing, right? Because you evaluate based on the success of a specific task or something like that. But are there any interesting challenges in terms of development wise because of the VLM? Like
I guess
from testing, internal testing or component testing and things like that.
Yeah, I guess yeah, during our evaluations, I think the biggest issue we ran into was the vision encoder step. It was really expensive, especially at the amount of image inputs we wanted to have. Like I said, there was a use case that wanted to send 1,000 images in a single request, and it's also a real-time use case. So it was basically impossible to support that using a traditional setup, traditional VLM setup with the vision encoder. So that's why we had to implement the projection embedding solution, which enables us to skip that expensive vision encoder step and actually makes 1,000 images in a single request feasible.
I see. Are you guys using the model that have a separate encoder for multimodal versus text, or is it one combined like for the recent Gemma, I believe, that has one encoder that takes care of both more images and text?
Well, we've been using only Quen so far for the projection embeddings, so it's been a separate encoder.
Separate encoder.
Yeah.
Got you. Okay. I don't see any more questions, but I have my own interest questions. I think in the presentation abstract, it talks about VLM workloads are uniquely prefill heavy. So in terms of like serving these, do you guys have like interesting setup to deal with this?
Yeah, I think to kind of that's where a lot of the Dynamo features come into play to help alleviate some of that. So you can also go back to yeah, so the disaggregated serving certainly helps because we can kind of scale that prefill component separately. Also, the KV cache aware routing and cache offloading also help because we can basically manage cache and manage state a lot more easily and efficiently, and also especially because Dynamo now supports these features with multimodal requests in mind. That also helps address those issues. Yeah, I don't know if you had anything to add, Christian.
Yeah, I guess another big thing would be like the LM cache support. That's another thing we've been looking pretty closely at. That's also helped a lot. Yeah, I think another area of focus we've been looking at is having a distributed or a remote LM cache instance backing our Dynamo deployments. So,
are you guys using in not a remote LM cache right now?
no, actually, we weren't. I don't think, Selena, right?
Yeah, we weren't, and that's an active kind of avenue of exploration right now. I think LM Cache recently came out with or / is working on this new offering. So that's something we're working on.
Fascinating. Okay, I see one question from the audience. I'll bring it up. What else did you evaluate before deciding on NVIDIA Dynamo?
I think we also evaluated LLMD. There were a couple more. I can't really remember. It was like over a year ago. It was a while ago. We started working with Dynamo pretty early. I think LLMD, I think their like traffic offering or traffic setup was not as flexible as NVIDIA Dynamo, and it wouldn't work as well with our internal Envoy-based traffic routing. I think that was the main reason why we didn't end up going with it.
But that was a year ago. A year is a long time in this space. I'm sure these engines have evolved quite a bit since then.
Yeah, certainly. I mean, NVIDIA Dynamo itself has evolved a lot since then.
Right.
I'm really proud of the collaboration we have with them because I think it's resulted in a much more robust multimodal offering from their end.
Got it. Okay. Let's take one more question, and this one you guys can help here because a lot of folks are trying to get into this space. How do you get a job as an LLM's inference engineer who has experience in serving open source LLMs with inference engines such as VLM and such? Any suggestions or recommendations?
Christian, do you have any thoughts? I have to think about this.
Yeah, I think on my end, I don't really have any suggestions. I think I just got very lucky, to be honest. I don't really know. Yeah, when I joined the team, it was just a recommender system, and then I joined as an intern, and then I kept coming for like 2 summers, and then GenAI started happening, it became big, and then the team evolved from there. So I just got lucky to be at the right place, I guess.
Yeah, I do think some of it is luck. I don't know if this is great advice for myself. When I started my career as a software engineer, LLM inference is not a thing. AI was just starting to become big, but I actually was not even working in the machine learning space. I was a front-end web developer. I also feel like I got lucky because I was able to do an internal transfer. I don't think I would specifically offer that as career advice, but I think that is just to say it's definitely a difficult space, and yeah, I do wish you the best of luck. But I guess also maybe it might be some the silver lining of the fact that LLMs and LLM inference is blowing up right now is because it is a new space. So I think if you're able to carve out your own space within and gain expertise, everyone is kind of learning right now. It's super new. So
yeah, I completely agree with that. This space is fairly new, and if you continue to learn, get involved in the open source community, participate in these kinds of forums, and I'm sure one day you're able to find the right opportunity. One opportunity will come to you. So I feel the key thing is keep learning, keep building, keep practicing. So that's some of my thoughts. All right. Thank you, Selena, Christian, for taking time out to share the learnings and the journey from building these VOMs serving stack at Pinterest. Thanks a lot.
Thank you.
All right, for the next presentation, we have Ying Chen from Databricks, and she is going to discuss about how they building their LM serving infrastructure from scale. So I'm very interested in this and hearing all the interesting learnings and challenges that they in their journey. Ying,
Yeah.
I'm going to hand it over to you.
Yeah, thanks for the introduction. So I'm Ying, happy to talk today. I'm a software engineer at Databricks. Today I'm going to talk about some of the things we built and some of the hard-earned lessons we had during serving large language models at scale. Let me change the slide. So some people might be surprised that Databricks serves large language models, and we actually do, and at a pretty large scale. In May alone, we have served more than 125 trillion tokens per month. This is spanning across customers such as Grammarly, Epidata, Fox Sports, and a lot of different domains in their production systems. And also a lot of Databricks AI products. We use our serving stack to power high concurrency scaling for fine-tuned models provided by our research team. So a lot of challenges may arise for serving inference at scale. One potential thing is GPUs are expensive and hard to come by. Even if you have a lot of GPU capacity, you have more demand that you can supply. So you need to make a trade-off between over-provisioning the GPU but have a very low GPU utilization and letting the GPU sit idle. Or on the other hand, if we don't scale the GPU fast enough to supply the demand, it may run into 5xx errors and increase latency, which is not great. So we must be able to estimate the scale and provide rate limiting across different workloads and customers. Another challenge is that the engines, the models, everything change very quickly. So this is a very quick space to catch up, and you need to have a lot of optimizations as well. So this is a lot of code that is shipping every week. And we need to make sure that we have some robustness in our system to make sure that even if something wrong goes wrong in production, we can fill over and recover very quickly. The last consideration is that this is a large system. As we evolve the system, it may have more components interacting with each other. So a local issue may become system-wide failures and cause cascading issues. So we need to be able to pinpoint these and provide a holistic solution for these reliability issues. So starting by talking about capacity, the trade-off between over-provisioning GPUs, or maintaining good high availability or versus reliability. So starting from scratch, if we are serving a model, the easiest way to start with is to have several pods running in a Kubernetes cluster. We will have the models of different sizes. For example, model A may be a model that requires 2 GPUs, and we may have different number of replicas of these models depending on the demand. For example, maybe B is a larger model, but not many people are using it, so we aren't scaling it up. And we may still have some headspace in the GPU cluster that we can scale up on. So across like this serving engine, we need to make sure that there is some reliability across this so that this can be running and be maintained by Kubernetes and our infra to recover. And on top of the model deployments that runs the serving engines, we may also have some router that is able to do cache-aware routing or session-based routing and do load balancing between the pods. On the other hand, the autoscaler will be able to control the scale up or scale down of the model pods so that we can scale up or down depending on the demand. And this is what we call the data plane. On the other hand, when requests come in, this is a multi-tenant system. We have many different customers or our own workload running on this entire cluster. So we need to have rate limiting to do some managing of how much load each request gets and each customer gets. And we also may have some capacity management, which will look at this entire system holistically, collect signals, and decide whether to scale up or scale down, and tell the autoscaler to orchestrate the requests. And this is what we call the control plane. So as a request comes in, it first goes through the rate limiter and gets routed to the data plane, and then the router in the data plane will send it to the model and the specific pods according to the routing algorithm. So as we can see, a lot of these parts in the multi-tenant system requires a good way to estimate how much load it is. And there are some obvious load signals that we can imagine, but that may not satisfy our requirements. For example, if we look at request counts, it is not a really good load signal because in LLM serving, each request may have different shapes, input, output, cache hit rate. So if you don't account for how much it request cost, then this is not a good signal because 10 very short requests is definitely less expensive than a very long 1 million input tokens request. On the other hand, if you look into the engine itself does provide some metrics for you. For example, when requests get into the engine and there are a lot of running requests that are saturating the KV cache, you might get the requests that are queued in the engine. But the queue depth itself may also be not a great load signal because it may be reacting too late to the incoming burst of workload. And when you finally scale up, it may already be too late. Resource usage also isn't great. For example, CPU, GPU utilization or memory utilization itself isn't a great signal about how much request is coming in and how much headroom you still have. So on this end, we need a good way to estimate request load. And the way we think about this is if we assume that there is a total number of throughputs, number of requests that can run per minute on this GPU deployment, then each request will have a share of the server throughput, and we will call this the request cost. Whenever we bring up a new model on a new type of hardware, we do an offline sweeping based on different input and output shapes, and we get the throughput of each shape so that we know an estimation of, for example, a batch of requests that have this input and output shape may have this throughput. So each request may have some kind of shares of this entire throughput. So during online serving, as new requests come in, we keep accumulating this, or when requests come in or after requests complete, they are removed from the accumulated cost so that we know when to scale up, scale down, or do some rate limiting based on the currently running requests. However, any kind of cost model is not comprehensive, and the cost model would definitely keep changing. The actual cost of a request may be drift from the request that was initially benchmarked. For example, if you serve GPT OSS and you increase the throughput or latency of it, and it is some significant optimization, then apparently with the same input and output shape, the request will complete more faster and you can run more requests at the same time. So this means that the cost model is you're overestimating the cost. On the other hand, multimodal requests with its CPU overhead and visual encoder overhead, it may cost more than what you initially estimated based on just the text-only data. Other factors such as prefix hash hit and mixed batch also will affect the actual cost. So request cost is just a prior that you can feed into the system. We need to keep updating it, and we can't rely on it alone to do all the scaling decisions or like rate limiting. So going back to the engine part, we can talk about engine a little bit. So here I pasted some screenshots to show how fast the road is evolving across the engines. One of it is SGLang's release, one of it is VLM's release, and another is the scale of models that the number of models that come up every week. So with these kind of bi-weekly or even weekly changes to the engine road and the models we are going to support, there is a huge service area that we need to be testing, but testing alone may not be enough. So we need to have reliability around the entire system to make sure that anything wrong in the engine doesn't bring down the entire system. Typically, an inference engine such as VLM or SGLang is a multi-process system, and it is really easy to have some parts of the system, for example, one of the process to be down due to some query of death. The query of death is a term that these are some queries that bring some bad patterns of the system that crashes parts of the system and make it start hanging. And these kind of irregular workloads is not something that you can typically have a full test coverage about. This may be something that you didn't predict. It can be some sort of multimodal patterns. It can be some sort of grammar patterns that cause parts of the inference engine to fail. So if you start an engine, it crashes, it's very easy to catch. But what if the engine is silently failing, but you can't tell it from the outside? So the way we detect it is super simple. This is just a health check request. We just send a hi to the engine as a black box, and as long as it returns a token, we know that it is working. So we build a very thin layer across all of the engines that we support and make sure that this layer can do all the reliability checks, such as health checks here, and provide the signals we need. One caveat of this is that we need to make sure that this kind of health check request is of the highest priority. Otherwise, if the health checks just times out when the server is having a very high load, it is not a great signal. It is a false positive, and we will just restart the server and it just keep crashing despite there is nothing really going wrong, just a high load. So with this mechanism, we can leverage Kubernetes' own health check and readiness checks and restart on failures so that we can recover this kind of query of death within minutes. And as engineers, we can decide whether to roll back or make some patches for hotfix offline without the production system really going wrong or the customer really noticing a huge failure. So we talked about the entire multi-serving infra a little bit. We also talked about the engine itself. And as a whole system, these two components, or all of the components in the system, is actually highly coupled, and it's very likely that stability can go wrong when certain components are under load, and it may cause cascading failures. So let's look at an example here. For example, if some of the requests cost much more than predicted, such as multimodal requests, then we will have the control plane services, such as the rate limiter, the capacity management, assume the servers can take more load. So the rate limiter lets the request come in, and the autoscaler does not make decisions to scale up the pods. So there are more loads hitting our inference engines than expected. Then we will see that in the inference engines, latency keep rising from like seconds to minutes, and eventually you will see some requests being queued up as the KB cache being saturated. You will also see some requests reaching timeouts that doesn't satisfy the SLA. And then the client or our batch inference service may just need to retry and send the same request over and over again, adding even more load to the system. And this will become more severe over time and cause cascading failure. There are several parts in this entire graph that can be improved to break this entire loop. For example, what if we just adjust the cost model so that the request cost can actually be similar to the predicted cost? By doing this, we need to do more benchmarks when more modality we support, or different patterns or different like grammar or tool calling patterns show up. Then we need to address these additional overhead by addressing the cost model and increasing or decreasing the request cost. And this is something that is very feasible for certain things that are deterministic, but there may be some unexpected changes that may cause request costs to be different than predicted. So we also need more robust mechanisms to detect this. Also very generic way and also very useful way to do this is have some load shedding to break the loop. When we see that requests are queuing or timing out, we can just raise 429 errors to the control plane saying that we are currently under a high load, and 429 errors meaning that is we are going to rate limit it. Then in this sense, the control plane can adjust the load, either not sending as much requests to the serving engine or decide to scale up. We can also cancel some requests that didn't actually reach the be running and are just queuing, and make sure that they can be scheduled again so that this time the serving engine doesn't have as much load to process. But any of those mechanisms doesn't actually change the actual issue, which is why did the request cost much more than predicted in the first place? Sometimes it's something you need to improve in the cost model, but sometimes it's your GPUs actually sitting idle and the overhead is elsewhere. This was a case when we were supporting multimodal requests at first. At that time, for some models in Hugging Face, there is a slow image processor that was enabled by default, which is backed by Pillow. There's also the fast image processor based on Torch Vision, which should be faster in theory. But when we enabled fast image processor, it suddenly became much slower and the overload issue just became worse. And the reason was that is actually because when we split the entire GPU node of 8 GPUs into several different pods for like 1 GPU per node, we need to set the containers to have the OpenMP number of threads correctly. Otherwise, it will cause CPU throttling for Torch Vision. After we fix this issue, by doing some CPU profiling to find the root cause, we could just see that the request per second 3x after we deployed the fix. So sometimes we just need to look into what is the actual bottleneck and fix the issue accordingly. And then it will help the entire system alleviate the load. So here I talked about the 3 aspects, the capacity of thinking about a multi-tenant serving system, and engine hardening itself and how these components may work together. So my takeaway to building a reliable LLM serving infra are 3. First, when building the infra itself, we need to build from first principles, and we might not expect it to work perfectly when the production workloads and paradigm shifts happen. We need to keep iterating based on new paradigms, new workloads, etc. Second, we also need to build safety nets for the unpredictable so that we can maintain shipping velocity, but also maintain reliability. Lastly, we should always understand the system as a whole. For people who work on engines, we might not care about the entire serving infra that much, but sometimes this can signal then this can cause a huger problem than engine slowness. On the other hand, if we work on infra, we might not care about what actually is going on in the engine that is causing the bottleneck. So we need to also be able to pinpoint these things. And sometimes these can be the solution to a system's problem as well. So here is what I have. Happy to take any questions.
Ying for the great presentation and lots of interesting learnings that you share there. I'll start with my own question here. A fascinating journey. I didn't even know Databricks got into this business, by the way, until recently from your blog. So it's great. That sounds like you guys are already handling a lot of businesses. 125 trillion tokens per month. That's crazy. Do you support all kinds of models or certain kinds of model at the moment? What is that like?
So right now we support some Quinn models, GPT OSS. We are also bringing up new models for potentially this or next week. So stay tuned for the news.
Okay. There's always new models coming down the pipeline.
Yes.
In terms of the journey, how long did it take? If I missed that, I'm sorry, but just curious. Because it's a huge endeavor, right? This is like a very complex system, multi-layers and everything. So
Yeah, a lot of these things were even built before I joined the team. These things like evolve a lot during the history. So first it was like not even a multi-tenant system. And then people in the team built a multi-tenant system to make sure that we can have more GPU utilizations as there are like more customers. So this was one thing. And the reliability battle itself is also something we like kept learning from
Yeah.
years.
Yeah.
So yeah, that was like at least 1 or 2 years.
Wow. Okay. Gotcha. I see one question from the audience. I'll bring it up. How do you handle cold start problem in production stage?
Oh, interesting. Can you clarify what do you mean by the cold start problem?
Yeah, I was curious about that too. Hopefully they're still around, but while we're waiting for that, so what's next for you guys now that you guys have it in production? What was the next phase?
Yeah, so there are a lot of things that are coming, like Kimi and GLM 5.2 has all the buzz nowadays. So we're also doing like more large scale serving. So previously I didn't really cover the disaggregated serving, although that was part of the like router in the picture.
Yeah.
So that is one thing. And we are also like trying to get more capacity so that we can serve more demands, because there are a lot of like internal and external use cases that we want to support.
Got you. Okay, I think that that person reposed a question. Let me bring it up. How do you find where the bottleneck is during production level inference, whether it's CPU, GPUs, or Kubernetes?
Yeah, first of all, we need to have very good observability and also very good logging. So if we have good logging, we can typically just do a profiling. We can know in the trace to see where the request starts, where is it in the running queue, or is it already running, or does it even get into the engine? So once we have the good traces, it's typically something we can know that is where the signal is. Yeah.
Okay, I see. So now that you have customer, obviously 125 trillion tokens a month, how are you guys thinking about competing with the other inference providers? It's a crowded space.
Yeah. Well, yeah, we're definitely thinking about this a lot. But I don't know if there are things that is like interesting to the audience.
Well, I think the Databricks has an advantage in a way because Databricks has lots of customers or enterprises as customers.
Yes.
So there's already established relationship. So it's probably easier to sell into those existing customer base.
Yeah, there are a lot of trends. So for existing customers, we are building like AI Gateway. That was a huge announcement in our Data AI Summit recently. We're building this governance layer so that people can not only just use like Databricks hosted models, or they can also like point their Anthropic or OpenAI models to here and get the governance. We're also like trying to improve on performance optimizations a lot. So that's also a trend that we're like competing against like the inference providers.
Yeah. All right, another question came in. Regarding the cost estimation of a request, what are some of the strategies that we can use to do that?
Yeah, so offline benchmarking is a really good source. You can get actual data when you run on GPUs and on your actual engine with your actual version. For example, different versions may have variants. And this is a good starting point. And after that, there are several things that you can do. First of all, whether you want to estimate the output, like output tokens is one thing. If you don't do that, sometimes it can be a huge variance to the system. So if you have good previous workloads, previous patterns, you can derive some heuristics or linear like regression models to do that as well.
Got you. Okay. So I'm gonna bring back a question, which is a good question, and I think you heard it when you were in the backstage, which is about how to get a job SGLang Inference
Wow.
engineer. You've been in this space, so hopefully you can provide some tips for this listener.
I think that is a really good question. I feel like this is actually pretty hard. Yeah, because I feel like learning is important, definitely, and like being able to contribute to like popular open source projects, whether you're focusing on the engine itself or caching or multimodal, there are a lot of things you can do. Even like orchestration, Dynamo is also a great place to contribute.
Yeah.
But these are also like, if you're just contributing open source, you also don't have the production experience.
Right.
I think the easiest is doing team transfers. If your company already have an inference team, and you also are a strong contributor, not only your team, but also in open source projects, then this is a great conversation to have.
Yeah, if you're fortunate enough, like you work in a company that they have an inference team, that's probably the easiest way to get in, to learn and build your experience, and then go from there. I agree with that. But if not all companies have that, unfortunately.
Yes.
So that will require a bit more work to get a job in this space.
Yeah, but even like having a really solid contribution in open source, that could also be a great starting point.
Absolutely, it'll be a good starting point. All right, Ying, thank you so much for taking time out and sharing with us some of the journeys and learnings from Databricks. So appreciate it.
Yeah, thanks for hosting.
All right. Next up, we're going to start a little bit early for our special guest, Daniel. Welcome, Daniel.
Hey.
Daniel is
good
going
to
to
be here.
share with us a presentation about the question that we want to ask. Should you self-host Inference? And he's going to share with us a bunch of learnings and tips and whatnot in this space. So looking forward to it. Oh, yours, Daniel.
Thank you so much. Well, it's great to be here. I'm just curious, are you pulling the slides up or should I? I definitely
Alan, are you
can.
there?
I can do it. So I'm
Okay.
already sharing
Oh,
screen.
yeah, there you go. I see your deck.
There you go. Okay, cool. So we get to see the HTML version, not the PDF, so the animations actually move. Oh, all right, cool. Also, I'm in Prague right now, so it's about half an hour past midnight, so I have about 2 brain cells left, but I'm sure we'll get through the material. So, hey, everybody. I guess you have heard a lot about the problems that are involved in serving the largest, greatest open source models out there. I'll take it from a little bit the opposite side. I'll focus on smaller models that are maybe easier to self-host, and we'll talk about whether you should and what the use cases look like that match that. I'm Daniel. I'm CEO of Superlinked. We have an open source inference product out there, which I'll kind of share some learnings from building, just in terms of architecture and what you may want to do when you build your own inference infrastructure. Okay, let's get going. So basically, the basic math of self-hosting versus like paying for GPUs versus paying for tokens basically has to do with kind of a couple different elements. So there is the element of cost. If you can saturate the GPUs, if you can use them properly, if you have enough volume, then you'll always basically save money compared to paying per token. Then there was this famous case study, for example, with Intercom, saving a bunch of money, kind of switching to open source models. You get more control of arguably the most important feature of your system if you self-host the models. So you will not just like lose access, or you will not be susceptible to pricing changes of your token suppliers. And kind of maybe not so obvious benefit is that when you build your product, you build your platform, you get to kind of bundle the inference into the platform, and you can really integrate it with what your specific platform needs, right? What the shape of your traffic is, where that traffic is coming from, or how it's interacting with the rest of your system, the tighter you can integrate inference into your systems, the fewer network hubs you have, and the more kind of tailored it can be in terms of the tuning. And you typically already run on few different clouds, few different environments, so adding that to the mix is not necessarily that hard. So those are some kind of high-level thoughts around self-hosting. And honestly, you have to kind of start by reflecting. And there are some patterns that, like if you, for example, have, let's say, less than 5 million requests a month, if you don't, already spend, let's say, at least like couple thousands or 10K a month on the APIs, or if you absolutely need the latest proprietary frontier models, those are the kind of scenarios where self-hosting probably doesn't make sense. But then when you go past those limits, so let's say past 10 million requests per month, if you are okay with the quality provided by open source models, and we'll talk about what that means, how to think about that. Or if you want to bundle inference, as I said, into your own platform, especially if you deploy, we work with some platforms that deploy their software into customers' environments. And if you want to basically bundle inference, bundle the models into that, and have your platform actually work in those environments and all the agents still perform, then that would be another kind of scenario where self-hosting makes sense. Okay, so first question that probably everybody is asking is on the model quality, right? Are the smaller open source models that are easier to self-host, easier to deploy in these different environments, are they good enough? How should we think about that? And by the way, when I say small, I mean, let's say under 40 billion parameters. Basically, those are the models that you can serve on one GPU that's even, let's say, 2 or 3 or maybe 4 generations behind the cutting edge, right? So that's what we mean by small. So this is kind of a first chart that I'll share. And on this chart, we see kind of 3 groups of models, even though the middle group is somewhat subtle in its coloring. So I split it between kind of proprietary models, large open weight models, for which, let's say, you need the latest GPUs and often multiple GPUs to serve one model, and then the small open weights models that fit on one GPU comfortably. And the chart shows the artificial analysis blended intelligence index over time. And I think, if you squint really hard, there are 2 things to notice from this chart. The first is some kind of convergence, right? So the frontier models are kind of not climbing as steep, let's say, as they used to. Then you have the largest open source models, and then you have the small models. And they're sort of still climbing pretty steep. So there is some sort of convergence happening between all the way the largest proprietary models and the smaller open source models. And then you can kind of zoom in and look at, for example, GPT 5.1 and Qwen 3627B. And I think they're like 48 versus 46 in this score, basically. So they're practically indistinguishable in terms of performance. So let's say this was maybe 5 months apart between release of GPT 5.1 and Qwen 3627B. So if you can basically wait for 5 months, you'll get equivalent performance to the frontier in a form factor that's actually very easy to work with. So if your workflow already, let's say, works with this one, then it should be very easy to migrate. So that's one way to think about it. Now, if you use open source models, of course, you are not just left to kind of consume the model as it is off the shelf. You can augment it, right? You can improve it. And just to give you some idea of kind of, is this expensive? Is it complicated? Here is just like very simple demonstration of using a LoRa to fine-tune an embedding model. And I'll mention embeddings a couple of times because we see that it's one of those model types that people self-host first. It's the easiest one to maybe get into self-hosting with kind of search-related models. And so for this experiment, we took the Arctic embed kind of base model, 500 million parameters, and it's a multilingual embedding model. And we ask ourselves, what would it take for it to perform better on legal documents in German? Can a LoRa adapter move a needle on that? And after spending about $1 on the GPU time to train that adapter on basically train split of this first data set, we see that on that specific data set we got, if we use a combination of legal data and general German data, then we have 18% lift of NDCG at 10, which is like a metric of quality of retrieval. And then even on a totally different but still legal German data set, we have a lift of 8%, which is substantial, right? So this is like beyond frontier. If you look at the generalist frontier embedding model, this pushes past that on legal German documents. And then you have to kind of play with, that there are trade-offs, right? So if we boost the legal German, maybe we lose on totally generalized German tasks. That's why we blend the general German in, and we have, like 0.6 and 2% regression on those tests, but we have those lifts to compensate. So that's kind of the addendum to this story that, okay, this is the basically base models on the open source side, but then you can adjust them to your problem as well. And you can do LoRa adapters, not only for embeddings, of course, but also for re-ranking models, for generative models. If you use generative models to do classification or other types of structured output generation, this also works, right? And the adapter is like super cheap to train. It's very small. It's in this case about 10% of the model size. And modern serving engines can load into memory not just the model, but also multiple adapters, and you can switch between them. So you can have different adaptation for different language or different domain. And again, this works across different model types. So that's just kind of like a quick side note on, when you see these kinds of charts, don't take them as kind of the final state, right? Because open source models allow you this kind of augmentation to approach or even push past the frontier on the problem that you actually care about. Okay. Now, in terms of the total output of the open source AI community, we have, I think, maybe this chart is like a little bit old. Maybe we have already crossed 3 million models uploaded to Hugging Face. I think there is maybe 100,000 models uploaded per month. Of course, not all of those will be state-of-the-art models, but they're, let's say, on the order of hundreds of models uploaded every month that are basically state-of-the-art in their specific niche, right? So there are any amount of niches for models that you can imagine. They're task-specific, so they're OCR models for receipts adapted in different languages, right? And of course, anything related to search, vision, speech-to-text, just the really broad spectrum of models being available. And most people, don't really take their time to discover what's available. And then it's not always so easy to actually run those models, right? So those are the two barriers that kind of make this not that easy, but the models are there, right? So we have kind of shown that the small models are pretty good in terms of quality. You can even improve the quality quite easily. And there's just so many models available that you for sure have one that solves your problem, right? So that kind of should, take care of the thoughts of like, okay, but small models, will they work for me? So then the next question is, how do we actually use those small models, right? And so we need, you guys heard about different architectures, different setups for inference, for serving. So I'll tell you a little bit about kind of how we see this. This is still back to the economics, right? So we said, let's say 10 million requests a month. per GPU in your fleet. That's, let's say, the break-even point. And then past that, you are not paying extra money because you have that one GPU for a month, right? Now, of course, it also depends on which kind of GPU and on which kind of price you can get it. But when we talk about small models, I really mean it that those GPUs don't have to be large. So you can start from kind of NVIDIA L4, A10. Then for models that, let's say, go past 4 or 8 billion parameters, you can grab A100, or now the RTX Pro 6000 is pretty good. And these are, on the order of $1 to $1.50 per hour, of course, based on the provider. These are typically kind of half that. And then you have the H100s and beyond. And that's totally fine, right? So you don't need to go anywhere near anything bigger than those, right? So if you stick to kind of the sub 40B on the model size. And just to give you some idea on kind of, okay, you have that one GPU and this kind of back to embeddings. If you have like some state-of-the-art reasonable models, you can expect on the order of from, let's say, 50 to 250, 300, or even more 1,000 tokens processed per second, right? So if you have a corpus with a billion tokens, on one GPU, you can make vector embeddings of that in, like an hour or something, because you are doing a million in 4 seconds. So that's going to be 4 times 1,000, right? Basically an hour. The latencies, of course, will be much better than any managed provider. And the price will be, something on the order of a tenth of the managed provider cost. Of course, embeddings, again, it's the easiest case, right? It's the easiest to serve. They're typically pretty small. So that's, an ideal entry point to self-hosting. Now, in terms of the topology, we talked about kind of where can your tokens be coming from. So it's either, both the model and the infrastructure is proprietary. So those would be your foundation labs, or the models are open source, but the infrastructure is proprietary. That's all your favorite, third-party inference providers. Or you have an open source based stack that you actually run yourself, and you bundle it into your platform, you bundle it into your cloud, and that's where VLM or SGLang based serving solutions, some kind of Kubernetes wrappers come into play, and that's where also our open source product exists in that category. And here I have a quick comparison. So I think, maybe this is like kind of trivial, but there is a difference between the runtimes and the cluster setups, right? So let's say if you are looking at what's running on the individual box, you would be looking at VLLM, SGLang. There is also TensorRT LLM. And then for embeddings, there is the Tay from Hugging Face, very cool project. So those give you the runtimes to run on individual machines, but then you need to build the cluster around it. And the cluster, kind of open source clusters, of course, are also available. So we already heard about Dynamo from NVIDIA. There is LLMD, and which basically now focuses on VLLM. There is Kserve, and then there is Superlinked Inference Engine. So as you can see here, we don't focus on the large models as most of the other players. We focus on these small models that we have been sort of describing so far. And then we try to make it as easy as possible to serve those models, kind of one-click install into different clouds and that kind of thing. So that's a little bit the landscape. If people are kind of looking at open source inference solutions, I think this is like a good set to start researching from. And in terms of kind of, if you are building one of these clusters yourself, I wanted to share a couple different tips. So one thing that has worked for us is that if you are doing small models, and if the requests are very quick, we are talking 50 or 100 milliseconds in latency, If you take the approach, the traditional routing approach, where the router has a very deep understanding of the worker state, and then top-down decides where each request is going, and then each worker has a local queue, as we see on the left. The problem, if you have many small requests coming in quickly, it's really hard to actually fill up the batches on these GPUs, and therefore you are not using them very efficiently. Because like half a size batch and a full batch takes almost the same amount of time, except half size batch processes half of the data, right? So instead, we work as much as we can with a centralized queue. We have a NATS Jetstream-based queue. We have a gateway that annotates the requests with some metadata, and then the workers pull from that queue based on them, being available and being able to form a batch, right? So this way we don't fragment the traffic into the local worker queues, and that alone helped us improve the throughput by more than 50% for these small model workloads. I should say as a side note that the system can also create kind of a direct channel to a worker if the local worker cache becomes important. But we still insert the request also into like a global shared queue. So if that one worker becomes saturated, other workers can start picking the work up. And next, as we start to disaggregate the different stages of inference, we have that kind of shared queue element that can be easily used to chain these different steps. So we really sort of enjoy this design that there is a kind of stateful queue in the middle, and we chose something that has like very little overhead, so no Kafka, nothing like that. Something much more kind of bare metal and fast. And then you can also have this kind of centralized telemetry attached to that queue, which is quite beneficial and handy. So because then you can do scaling based on that and so on. And then the second trick that's really important with small models is put more of them onto the same GPU. So you have, we talked about LoRa's, you have different models, you have different LoRa's. You don't want to have worker pools that the whole pool is serving one specific model, and then another pool is serving another model. You want to kind of aggregate all those workloads into as shared of a cluster as possible. You want to load multiple models into the VRAM of the same GPU, ideally, because then if you have a traffic that has a bunch of different models, you can serve it much more effectively. So that's kind of the added trick that's important to keep in mind. So then this is how the cluster looks like. You have your gateway, you have your queue, and you have your workers that run different inference backends. We, for example, in our product, have our own inference backends written in PyTorch and Candle in Rust, but we also have other open source backends available, and we kind of sweep through the parameters and we choose whatever is best for each model that we support. So that's kind of the topology that has worked well for us, and maybe something you can emulate in your projects. And I wanted to mention kind of something about user experience. So if you are thinking about building an inference platform at your own company, for me, the rule of thumb of kind of how can I make people more productive, more efficient, is when they don't have to talk to each other. And there is, the AI engineers in an organization and the infrastructure engineers. And if they don't really have to talk to each other to achieve their goal, then they can move much faster. So, in our product and in the best products we see out there on the market, the infrastructure engineers, they kind of understand the quotas they have in different zones, different locations. They are there to kind of recover if the cluster hits some kind of big problem. They own the account, and they deal with sort of billing and all of that. And then the AI engineers, they are the ones who come in and they want to create, let's say, pools of compute that their project needs. They want to maybe pin some models, but for other models, they just want to lazy load them into the cluster because they are comparing different models. So they need kind of lazy loading with eviction for certain models, pinning, and kind of capacity reservation for some workloads that they already know they want to be doing, and then of course they want to do the inference calls, right? So in our product, everything that happens on the left side is done against the API, and it's super easy for any engineer or data scientist to get done. And then everything on the right is kind of infrastructure as code, Terraform, Helm charts, all of that, right? So two different worlds, and they don't have to interact with each other. And then then our inference cluster kind of sits in the middle. So I think that's a really good design for any kind of internal platform that you might be building. Just treat the AI engineers as your internal customers, basically, and give them a good experience. Okay, and then finally, let's say you are now bought into using small models. You have some idea of how your cluster should look like. Now the question is, okay, what can you build with this, right? So I'll talk quickly about one example agent. We have in our repo a couple different examples. So in this agent, it's actually written in, I believe, OpenAI Agents SDK. But of course, there are other harnesses that you can use. This one is a contract review agent. It extracts facts from contracts. It has some vision capability to see if contracts are signed, for example. It has some OCR. It has some parsing of entities. It can flag risks or inconsistencies across different contracts, so it's kind of full review. And it can, apply different policies on top and so on. And surfacing obligations that those contracts define and so on. So that's one kind of self-contained agent. Now, when you use small models, these task-specific models, you'll find that you use actually a bunch of them to build the agent, right? It's no longer, okay, let's send everything to the same LLM, but you basically identify these task-specific models. They are sort of tools for the agent to solve all these different problems. So in this agent, we have basically a state is in some SQL database, and then contracts come in, we extract things, we store it into the SQL database, and then we do queries against the database when we want to verify different clauses. So there is like a text to SQL model that's doing that. There is an OCR model. There is the Gliner model for entity extraction. There is bigger generative model for some clause risk analysis. And then there is like a planning model over there. There is safety guardrails with the Granite model from IBM and some kind of synthesizer at the end, right? So this agent, I believe, uses 9 models. And that's why it's important for your cluster to be able to handle traffic that's kind of a mix of 9 models. And that's just one agent, right? If a bunch of different teams and people in your organization build a bunch of these agents, now you have traffic that maybe touches 20 or 30 or 40 different models. And that's why, kind of pooling all the compute capacity, loading the models, multiple models on the same GPU, that's the thing that allows you to deal with this super heterogeneous traffic, right? Okay, and this agent, we ran it on some data set with 500 plus real commercial contracts filed with the SEC, and it found some inconsistencies in different contracts, and found was able to flag that it didn't know how to decide if a document is signed or not. So the guardrails kind of work, and so on. This code is available on our repo. So just to finish, basically, when to self-host. I think these are the axes, right? So if you want to process way more data than you are processing today, and you calculated what the bill would be, and the bill is crazy, then self-hosting might make sense. If you are latency sensitive, right? So it's some kind of user-based interaction, and user wants kind of real-time feedback, or the agent is doing so much work that you want to reduce the number of the time it takes to wait for every single round. You can get big gains by self-hosting and tuning. As we said, the small models are kind of pretty much as smart as GPT 5.1 right now. So if you are not, solving the Riemann hypothesis, but like you are solving some kind of enterprise workflow or support use case or something reasonably contained, then these models are plenty smart. And then, potentially, most importantly, the deployment is yours, right? So you have full control. You will not lose access. If your GPU provider, you don't like them anymore, you just take your thing and put it somewhere else. You are much more robust. You have less platform risk and so on. So I think those are kind of the, if you remember anything from this presentation, then these are kind of the orientation points. So yeah, I think that's it for me. On this QR code or on this URL here, you see the repo of our product. It's Apache 2.0, totally open source cluster for self-hosting of small models, and we would love your feedback and collaboration on that.
Awesome. Thank you, Daniel. Thank you for all that details and information. This is a topic that's close, dear and close to my heart. And I have a lot of questions for you, but I know it's midnight over there, so I won't ask you too many.
We can do.
Yeah, okay.
Yeah.
We have about 5 minutes ish. So my first question is, I definitely believe that moving forward, more and more companies will do self-hosting for all the reasons that you listed there, and probably more. What do you see from your research and working with companies? What are you seeing? I'm just curious.
For us, actually, one of the surprises has been that it was the platforms that themselves deploy into different kinds of environments and want consistent inference capability. Those are some of the ones who are picking this up the fastest, right? If you are big enterprise and you have been kind of a little bit addicted to the LLM APIs, and it's just quite easy to do another, commit and another buy, and you just kind of keep going. But if you are a company that's either like hitting the hyperscaling inflection and suddenly the bills are crazy, or you are a platform that deploys into environments where you would ideally want to take the inference with you, those were the two cases where people really care.
Gotcha. Yeah, makes sense. Like different companies, they have different level of experience. And then I think I definitely would check out the your Git repo that you share. But I'm sensing that if there is an example that makes it very easy to set up this entire stack, right, as a starting point. And I think that's what you showed earlier. Is that right? Do you guys have a GitHub repo to help with that?
Yeah. So one of the ways you can get into it is you can just take the runtime, the worker, and just start it on your computer. And in our latest release, we made it also natively compatible with the Metal, with Mac Silicon. So if you have a MacBook, you can run the runtime locally. And that's exactly the same runtime with just some dependencies swapped around that then gets deployed into cloud. It's the same models available and so on. So that's an easy way to get in, that you just run it locally. And then the same thing, you run Terraform apply, Helm install, and boom, now you have a cluster that's auto-scaled, all of those different features available in your cloud. So that's one way in. The other easy way to get started is you send me a message, and I'll give you an inference grant for one of our test clusters. So we have test clusters. There is a bunch of capacity. And we are working with independent projects, people sending us cool ideas like, hey, I want to process all this data. I want to build a search system for, German, whatever, legislature, stuff like that. We are happy we have this kind of banknotes that we hand out in person. And it's one zettaflop of compute. And we are very happy to sponsor and give people access to those test clusters. So I think those are the two ways.
All right, sounds awesome. I will definitely reach out to you in person, personally. Last question before I let you go. I think I don't know if something like this already existed, but it feels like if there's a course that talks about all these steps that you in this session, you walk through all how to set up stuff like that. Have you considered doing a course like this?
I have joined other people's courses. Actually, one of your presenters today, I think, will join her course. Yeah. And I have joined courses about kind of AI-powered search also. Yeah, I mean, I ran the company. We haven't figured out the way to, because course is a big commitment, but
Yes.
I kind of slip the teachings in my social media content, so I
Okay.
try to be very active and very hands-on practical, pointing out data sets, pointing out, gotchas and stuff. So I guess the closest approximation to a course is just give me a follow on Twitter or LinkedIn.
I see. I feel like this course like this is gonna be very, very popular. But awesome. Thank you so much for spending time with us. I know it's really, really late, and appreciate your time and effort of giving us this presentation. Thank you.
Likewise. Thanks for having
I'll
me.
let you
Have a
go
good one,
and
everybody.
get some sleep.
Thank you.
Thank
Cheers.
you.
Bye.
All right. For the last presentation of the summit, we have, I hope I pronounced his name correctly. Otherwise, he's gonna give me a hard time. Sinan? Close enough?
And yeah, I know you got it. You got it, Sinan.
So Sinan from Fireworks, he's gonna give us this presentation on the cheapest token is the one that you never generate, which I completely agree. And he's gonna discuss all the techniques how to do that. So with that, I'm gonna hand it over to him. And I was told that he's gonna have something interesting at the end for us. So pay close attention.
I wonder what it could be. Thank you so much. Welcome, everybody. I know it's been a long day, and I promise we're almost done. And I am going to take us through to the finish line today. So my name is Sinan Ozdemir. I am so happy to be here. I am head of AI education at Fireworks as of only a couple of weeks ago. But for those who may be familiar with my work in the past, I'll give you the long story short. I built so I'm a former mathematician. I got my degrees in theoretical mathematics from the Johns Hopkins University, where I also taught for a number of years. I actually built one of YC's, as far as I'm aware, YC's first generative AI company in 2015, where we were building agentic generative models. Yes, before the transformer even existed, those existed. We even patented the agent in 2019. Since then, I've also authored my own set of books. I know, at least a few people have mentioned them. They're available. You can find it. I have a pretty unique name, so they're pretty easy to find. I won't. But that's not why you're here. You're here because you want to hear about how you can optimize your model inference. And I think I want to take a little bit of a different approach today to a lot of the other wonderful presenters. And there's no question that on the serving side, with better kernels, smarter caching, faster hardware, better networking systems, without a doubt, these are crucial components of your inference side of your LLM usage, your AI usage. But what do we do with that speed is what I want to focus on today, because a lot of what I do at Fireworks and a lot of what I've been teaching over the last decade and a half at this point is the techniques behind the AIs. What techniques do we have in our tool belt to make our inference more optimized, whether that is for quality, for cost, or for latency. So I'm going to be focusing more on the model side of optimization today, because again, you've heard, over and over again, we want to make sure that we're getting fast throughput, lower latencies on the serving side. But what do we do with the speed of those models once they are ready for us? So I'm going to talk about three different applications, and I write in order of effort, but that's a little subjective, and I think that's people will find that they'll grasp onto one of these different categories a little bit more, however you want. So, but we're going to go through three different levers today, and these aren't the only levers at your disposal, of course, but they're the levers I had time to talk about in my 30 minutes with you all. So we're going to talk about capping, distilling, and routing, and we're going to start with a pretty kind of straightforward one, in my humble opinion, which is capping. And the idea behind capping is that these days it's almost harder to find a model that is not a reasoning model. And for those you might remember a few years ago, it was the opposite. Most models were non-reasoning, non-thinking. And then there was this kind of period in which we had a few LLMs that had some reasoning. You could turn it off, you could turn it on. It was low, it was medium, it was high. And today, virtually every LLM that comes out of a frontier lab, open source or closed, has some kind of reasoning enabled. And I think that's kind of an expectation. Now, here's where I want to make a kind of a big claim. And one of the first things I noticed when reasoning models came out was we had already been implementing reasoning as prompt engineers, context engineers, as LLM engineers. We had this concept of a chain of thought prompt, meaning you ask the AI to reason through what it is before actually answering the task. So the concept of having the AI think out loud before answering the question, that's not necessarily the new thing. Now they're just built into the model. That's what's new. But here's the kicker. Most models will have some kind of a range between low, medium, high, or maybe you'll see like a max and X max, these different levels of thinking. And some models will give you the benefit of turning reasoning off. Not all models do that, but some do. Kimi is one of those models that will actually let you turn the reasoning off entirely. Now, I know everyone's watching virtually, but raise your hand if you are someone who is very likely to say, well, if you're going to let me reason more reasoning means better results. And if my serving side is optimized, then I should be able to see those fast reasoning tokens come in and see my better results even faster. But here's the problem with that. Even though it's only one line to change your reasoning effort from low to high, high to medium, you actually are potentially staring down some not so great results. So to put this in perspective, I'll give you an example. Many of you are probably familiar with this benchmark called tau squared, the tau squared benchmark. Basically, it's an agentic benchmark in which the AI is acting as a customer service agent, talking to another simulated user who is also an AI. And the idea is that you are judging the customer support agent, the LLM agent, in its ability to either help or refuse to help in some situations what the human is asking for. It's a pretty common benchmark. You'll see it actually reported on a lot of the frontier AIs these days. So I chose it as an example. So what I did was I took a model on the Fireworks serverless system, Kimi in this case, and all I did was I ran the Kimi model through the benchmark at varying reasoning efforts. So in Kimi's case, I did none. So no reasoning whatsoever, low, medium, and high. Everything else stand exactly the same. Same prompt, same benchmark subset, same everything. But here's the kicker. When I ran this 3 times for each question, so we call that pass at 3, the results were pretty, in my, when I've done this in the past, not surprising to me, but can be surprising to a lot of people. The non-reasoning turned out to be just as good, just statistically speaking, within a single standard error as low, medium, and high. So even when you turned up reasoning all the way, the LLM did not actually get any better at that benchmark, which is counterintuitive. You would assume, well, reasoning should make it smarter at doing the task in front of it. But that's just not always true. In fact, if you look closely at a lot of benchmark scores, you'll often find that the difference between medium, low, and high is a lot smaller than you might think. But if you look on the right, what you really will notice as you turn up the reasoning levels are the amount of tokens being shoved out of that model, and therefore the latency, the speed that you're experiencing from that system really drastically changes. So from a P50, a median latency of roughly 40 seconds to solve a task, it would go to 60 seconds median when the reasoning is turned up all the way. And again, you're not getting any accuracy quality bonus here. So with all that speed, you're still not getting any results. Now, again, this might seem like a simple experiment, because it is. That's kind of the point of what I want to be getting across today, which is what we do with the speed of these models is it enables us to run these kinds of experiments a lot faster than we could even a few years ago. So given that, there was no reliable gain, frankly, in this case. Now, I'm not saying reasoning never will help. I'm saying in this particular case, as it might be for your particular case, reasoning might not help. There's actually another case study I do in my, I think it's my most recent agents book that I published a couple months ago. The same thing I could find with computer use, vision models. Vision models did not benefit from having more reasoning outside of maybe 1 or 2 percentage points in their ability to use a browser. But it sure did double the latency of actually running that task in some cases. So when you have this speed in front of you, the first thing I want people's intentions to be with that speed is experiment. Try different things as quickly as possible to see what works best for you. So let's move on then to the more harder aspects of what you can do with that speed. And this is going to sound very similar to some of the other talks today, because now we're getting into some more fine tuning, some training aspects of what you can do with that speed. So if you've never heard of distillation, or you want a quick refresh on distillation, the concept of distillation can actually take on many different forms. People can mean different things when they say distillation, even more than these two things on the screen here. But the general idea of a distillation task is to transfer the knowledge from a usually much bigger frontier LLM into a much smaller LLM who can do that task, and usually only that task, but just as well as the frontier AI and at a fraction of the speed and cost. Now, from there, you can get more specific. You can talk about distribution distillation, data distillation, on policy, self-distillations. There's a lot of different types of distillations out there. Fireworks supports a good amount of those types of distillations, namely distribution distillate data and in some cases that on policy distribution. Now, what's most common is the data distillation. This is what most people think of when they hear the word distillation. The idea is that you have an AI, a bigger frontier model, generate some output. Generate some output, and then you use that output, that completion, as training data, supervised training data, to train a student, a smaller model, not necessarily the same family or same tokenizer, which is what makes data distillation very attractive. The idea is for some kinds of distillation, not that it requires it, it gets much harder to do when you have different model families and different tokenizers. With a data distillation, you have the big model answer a question, you grade it, hopefully that it's correct, then you use that as data to train a smaller model to say, do it like this, follow these instructions, do the conversation as I'm showing you here. So this is data distillation, and arguably it's the simplest kind of distillation out there on the market. And again, it's what most people think of when they think of distillation. So how do the numbers work out? I mean, as you might suspect, the numbers work out quite well. And just kind of using some, picking a model off the shelf on Fireworks and giving you the prices here. If you were using a model like Kimi, K2.5, with the price and cost and everything that you see here, you would, in theory, be saving thousands of dollars a day simply by distilling a certain task into a smaller model. And we have a lot of case studies in of our customers who do work like this, and I link to some of them in the final one pager. That there's a QR code at the end. But this kind of distillation, again, is really enabled by the speed of the serving side. So everything that people have been talking about today, and better KV caching, better kernels, all of that is for something, and it's not just for generating completions and agent rollouts, but this is also what enables Fireworks to be one of the fastest training solutions on the planet as well. Because we serve models so fast, we can also train them a lot faster as well, and a lot cheaper in most cases. So the conversation around training models is becoming an easier one to have. And I can say that confidently, having had these conversations for 15 years with people, it's never been easier to bring up the concept of fine tuning a model than it is today. And that for me makes me very happy. And that's why I love, being a part of this world and being a part of this ecosystem, because you don't even need to use fireworks to get a lot of these benefits. You can run a distillation completely on your own local hardware using open source frameworks and infrastructures, and you will get very similar results than if you do it on some inference provider like Fireworks. Of course, we just want to make it easier for you with bigger models, but it's not like there is a proprietary type of distillation that some companies employ. These are the same kinds of techniques that are simply enabled by better, faster serving architectures. So again, I can show you case studies. I can let you read them for yourself. But the idea of distilling tasks from a large model into a small model is often not only does it work, but it's also usually part of a multi-stage process. So at Fireworks, we often call this a recipe, the idea of using multiple techniques in a sequence so that you can run one technique like supervised fine tuning and then potentially a reinforcement learning after the fact. So you can distill as stage one and then take that distilled model and even imbue even more behavior that you want through a reinforcement learning loop. So distillation is becoming a more common use case for people as they realize we're just using, we're driving this Ferrari to the grocery store, and maybe we can train a smaller car just to do that instead. So when you start to hit these scale problems of we're running basically the same task over and over and over again on this frontier model, it might be time to have that discussion of how do you take that task and teach it to a smaller LLM that you have at your disposal. And that's going to bring me to our last technique here, which is routing. And I know this has come up a few times today. So, there might be a little bit of a refresher here, but routing, the concept of routing, picking the right model for the right task is much easier said than done. But I would like to present to you an extremely simplified version of this routing flywheel that has absolutely no human in the loop, but can still show results and something you can get started with literally today. And to show the example, what I did was I took a benchmark called BIRD. And if you've never heard of BIRD, I don't blame you. It is a text to SQL benchmark. Basically, it's a 33 gigabyte database benchmark with 12,000 plus questions across 95 different databases. And the task is relatively simple. Here's the schema. Here's the question I have. Write me SQL that will answer the question. And surprisingly, you might be surprised to hear this, there's still room at the top of the leaderboard for this benchmark for even the frontier model. So I like to pick this benchmark because it sounds very easy once you hear what it is, but it's actually quite difficult for even some of the frontier models out there. And what's also nice about it is that there's relatively objective scoring, meaning there is a right answer. I asked a question. I know the answer is in the data. I know what the answer is. There might be some wiggle room in how the model writes the SQL query, but generally is very objectively scored. And more importantly, as you'll see in the next slide, the questions themselves are embeddable, meaning you can take the short form questions of what is being asked and run it through an embedding model for the purposes of adding them to a vector store library. So here's the flywheel that I constructed in the visual format, and let's walk through it left to right. When a question comes in, first thing is we embed that question. Fireworks has embedding models hosted. So for this case, Qwen3, 8 billion embedding model. We then run it through our library, which may be empty, but let's assume it's either empty or not. We find if there is a similar question that has been asked in the past, and we use the embedding similarity as a proxy for that similarity. If the similarity reaches some threshold, like 0.6, there is a question in the database, in the library, that similarly matches the one that's incoming, we route it to the small model. That small model will then attempt to answer that question, and it never goes to a frontier model in the first place. But if nothing matches that question in the library, it goes to the escalate, meaning now we're going to ask both models to answer this question. The user will see the answer from the frontier AI, kind of assuming that the frontier AI is just better at this task. But while that's happening, the small model also takes a crack at it. And this is where you can improve on this flywheel, quite frankly, because there is no human in the loop. If the small and the big model agree with each other, that answer, or that question rather, is added to the library because the small model agreed with the big model. That for me is enough to add it to the library so that if a similar question comes in, we're going to send it to that small model instead of the big one. Now, in a real life situation, ideally, you double check the small model's work before adding it to the library. Some human in the loop should be able to check, or some panel of LLM judges, however you'd like to handle that. But in this case, all I did was say, if the big and the small model agree, that's enough for me, add it to the library. So I simulate this over time, and I find a few very interesting things. So if you are looking at cost per query in $, because we're talking about a query is going to be very few tokens compared to what Frontier Labs will charge you, but the cost differential is pretty obvious on the left here. It is 4 times cheaper to use the flywheel versus always using a frontier model. It is almost 3 times faster, 2.5, a 58% reduction in latency, and the accuracy actually was slightly better actually by using the flywheel than always asking the frontier model, which yes does imply that sometimes the small model actually got something right where the big model didn't. So that can happen, don't get me wrong. So the flywheel actually ended up being just as good, slightly better than always asking the frontier model. So if you look at it on a graph like this, on a kind of a Pareto graph like this, we have cost on the x-axis and accuracy on the y-axis, you can see a pretty clear story. I'm not claiming this flywheel alone gets you to Opus and Sonnet level performance. It's not too far off, don't get me wrong, but you can see how it's on par with the Frontier open model that I used, DeepSeek, at a much cheaper price. And it is still better than always asking the small model, the Qwen 9 billion. So again, with speed, we have now this concept of, well, I have to ask the models twice. If the similarity is under 0.6, I do have to ask both of these models, and I have to very quickly add it to the library before the next question comes in. So with that speed, we can start to enable these kinds of experiments, which even further optimize our quality, speed, and latency. So none of this was a better kernel, a better GPU, more money being thrown at the serving side. I'm simply using the speed already granted to me to run these kinds of rapid experiments. Another interesting part, by the way, that I wanted to add was, and people usually see this and they think, they get scared away at first, but the idea of a flywheel is that it does have to warm up a little. So in the beginning, there's nothing in the library. So everything keeps getting escalated to the frontier model, which means your costs will start off pretty high. Relatively, you're looking at relatively here. But as the library gets filled with examples that the smaller model is now more confident in tackling and handling, we see that the accuracy, which starts off very, very good because the frontier model is handling most things, settles to that roughly 41% accuracy at answering the question, as does cost and escalation rate. So you start to build this kind of mental model of how often does it actually escalate. And for the numbers here, if it was never escalated versus 15% and 100% escalation, we see all the way, these are pretty big price differentials in more than 4 times cheaper using our flywheel versus always using that frontier model. And again, this was just 2 models off the shelf, DeepSeek V4 and Qwen 9 billion. I personally tried about 5 different model combos before settling on this flywheel, but that took me about an hour. Once I had the workflow ready and I had the data set to simulate through, it only took me about an hour to try 5 different combinations and settle on this one. And this was just for this talk. If this was my job, if my job was to be better at text to SQL, I only need a couple of days to run through virtually every model combo on the Fireworks catalog, and I'll get the best possible option I can get from that one catalog alone. So again, faster serving enables faster experimentation, which for me is how you win at the end of the day. Your techniques, how clever you are in how you use the speed of those models, that's what's really going to let you win in the long term. So it's how you use your models. Capping reasoning is just one example of experimenting with inference parameters. A lot of people will experiment with temperature or top K, top P. Reasoning effort should be another lever that you experiment with, just like any other inference parameter at your disposal. But if that's not getting you the results that you need, which again, capping is not meant to win on quality, it's meant to save you on cost and latency when the quality was already there to begin with. But if you do need to potentially increase quality, maybe you'll need a routing situation in which your routing might actually give you better results than simply asking one model all the time. Or distillation, another part of a potentially 2-3-step process in which you train a smaller model to act like and be as good as a big model at a certain task. So with that said, I'll say thank you all, of course, for sticking around and making it through the day. And if you did stick around, and I do have a gift for you for sticking around the whole day, at this QR code, you'll find our one-pager basically about this talk. And the first 50 people who get to the one-pager, there is a $50 credit to Fireworks if you do actually want to try some of these experiments. And please, if you do get these credits and build something, please find me on Twitter and LinkedIn. I promise you it's not hard to find me. I have a very unique name, and show me what you've built. I would genuinely love to see what you are building with these models. And more importantly, I would love to see how you experiment with these models on our catalog, not just how you use them, but what experiments did you try to get to where you are. So I'll stop there and happy to take a question or two, but thank you all so much. And I hope you have a wonderful rest of the day.
And that was a lot of good stuff, lots of good tips there. I very much agree with you on some of those suggestions, because a lot of time people just, by default, just hitting these API with not paying attention to the level of intelligence that's needed for their particular tasks or use cases. So I have asked the attendees to post questions, but while that is showing up, I have a few questions for you.
Please.
You talk about distillation, right? Definitely, one option to go with.
Sure.
My question is about doing distillation. Is at least for me, it's not easy. So, do you think is this very accessible to AI engineers at the moment, or still very much in the realm of like machine learning engineer?
I think it is rapidly, 10 years ago, it's squarely in the field of machine learning engineers. But one reason that I joined Fireworks was their commitment to making machine learning engineering as simple, quote unquote, as software engineering. And I think a lot of what my role is, my new role at Fireworks, is to build that curriculum to convince people to say, this is now in your hands. This can be in your hands if you want it. Yeah. And we are rapidly approaching that threshold where it is as easy it is to code, it is as easy it is to fine tune a model. And that for me is exciting, because having built my first YC company 10 years ago on fine tuning, YC would never take my company today because they'll say, fine tuning a model, that's nothing. But 10 years ago, it was one of the hardest things you could do, quite frankly. So we are getting there. I wouldn't say we're exactly at that one-to-one, but I feel like it's never been easier.
Yeah, I agree with that trend with fine tuning. Now it's a lot easier. I mean, Fireworks have done a great job in that space of providing that service. And similar with RL as well, right? It used to be very, very challenging to do RL. Now it's becoming easier, definitely.
Getting easier. I'm not going to tell you it's a one-click solution, but it's getting easier. Yeah. And that's my job, is to walk you through it.
Yeah. All right. That's a question from the attendees, so let me bring it up. As you are doing warm-up, which requests?
For the flywheel, I assume.
Yeah, go for it.
Yeah, as you're doing warm-up, what requests go to the smaller models, and how do you choose that smaller model? So during the warm-up, so the basic simplicity of the flywheel is that the decision of when to go to the small model is purely mechanical. If there's something in the library close to the question at hand. Now, that alone, you can disagree with me on, as you should, because as I will always say, everything is an experiment. If you think the better way to do it is to have a grading, a generative grader answer that question for you, I don't disagree. You might need to fine tune that grader to be faster, cheaper, better, but we can have that discussion. To your other question of how do you choose that smaller model, everything is an experiment. The easy, naive answer, which is true, is try them all. If everything is so fast, it shouldn't take that long to get a good sense of which of those models are going to be better. Now, that assumes you have a data set in which you can compare that against. Now, if you don't have that, you can always do what, frankly, most people do, which is find the benchmark scores that best match the task you are trying to do, and then filter it by those benchmarks. Like I said, BIRD is not a very widely reported benchmark, but it is a benchmark. So if you want to benchmark a model on the BIRD benchmark, you're allowed. No one's stopping you from benchmarking models on a benchmark. In fact, Fireworks even has an open source framework called Eval Protocol that will help you do that. So by finding benchmarks that closely match the task you're trying to do, simply experiment and find the right models with the right benchmark scores. And if you can't find the benchmark scores, benchmark it yourself.
Awesome. Thank you for that. Thank you, Sinan. Again, thank you for your time. Thank you for taking time with your busy schedule and share your expertise and knowledge in this space. Really appreciate it.
So happy to be here. Thank you all.
For the next minute or two, I'm going to do the closing of the summit. And again, first of all, thank you to all the speakers. Without speakers, we wouldn't have this summit. So I'm going to quickly call the names out for you from the top to bottom. Mariam from DoubleWord, Abby, Suman from NVIDIA, Kawacha from Momento, Philip from Base 10, Jen Yen from Redix Arc, Emilio from Wafer, Selena and Christian from Pinterest, Ying from Databricks, Daniel from Superlink, and Sinan from Fireworks. Those are the speakers for this summit, and without them, we wouldn't have this summit. Next, attendees. It has been a long day, and we have attendees from all over the world for this topic. And thank you for hanging out with us. The recordings and the slides will be made available to you, obviously with the permissions of the speakers and so on. And also thank you to the Momento, the company that be putting this together, and the team that put very quickly spin this up within a short amount of time. And in terms of the next steps, as you can see, there's over 500 signups for this summit. Obviously, this is a topic that is very popular, and a lot of people have interest in this. So undoubtedly, very likely, we're going to have the next summit, Infer 2.0, and we're going to be announcing that in the coming days, whether that's going to be virtual or in person. We'll still have to work that out. But very likely, we're going to have the next one. So stay tuned. And with that, I'm going to conclude this summit. Thank you, everybody, for attending and participating. Have a great day.